Check 1 2. Mic check.
Turning the microphone on. I've heard that technology works so much better when you unplug it and plug it back in. So thank you very much to the AV team for getting us set up. I think this is the first year that we've had a genuinely working presenter screen as well. This is going to make it much easier than staring up the corner. So great. We are going to be starting essentially imminently. So glass of water, grab a chair, settle in. We'll try and pull people in from the hallway and get started here in just a moment. And for attendees who are here for anything other than GNU Radio Conference, you're in the wrong room. Wonderful. There is late registration, it's true. Grand, that's the hallway clear. So thank you very much and welcome to the GNU Radio Conference. My name's Derek Kozel. I am one of the GNU Radio leads, and I'll be showing you many other faces throughout this presentation, as well as some of what's going on during the conference. This will definitely be the least technical talk of the entire event, I think. So we'll get it over and done with, and I will hand it over to the people who have done so much excellent work over the last year and want to share it with us. So I was actually a student the first time I came to GNU Radio Conference. That was about 8 years ago, and I was presenting some of my own work. Some people, the audience was lovely, very engaged, and then at the end of it, very quietly, a couple people pulled me aside and said, "Did you know that in order to measure bit error rate, you have to synchronize your streams?" Now, that explains a lot of the results. So if you're new here, if you're a student, if you're new to GNU Radio, if you're new to comms, welcome. You're in a great space. This is a friendly crowd, and I hope you really enjoy the week. If you would call yourself a regular GNU Radio Conference attendee, then you already know what's in store. It's a phenomenal week of great talks. We have more workshops than I think ever before. We have a great room full of people who have brought their equipment and services to show off, and a set of socials that are great fun. So be sure to check out the schedule. I'll be showing that in a moment. And yeah, try to have a great week. This one doesn't have a power button to it. I said I wanted a clicker in order to brandish something, but I guess all I get to do is brandish. Hey, there we are. So this was me at my first GNU Radio conference. You can't quite see it, but Martin Braun is actually down in the corner. I believe he was community manager for the project at this point in time. So there are certainly people volunteering with the GNU Radio project who have been around much longer than I. And one of our keynote speakers, in fact, has been here since the very beginning. All right, well, I guess I'll stand slightly to the side because that appears to be where the clicker works best. So yes, this is the GNU Radio Conference 2023. This is, I believe, the 13th time that we've run this event, one of them being online. For the folks who are catching the live stream, this is all streamed onto YouTube. All the videos are freely available immediately after the event, and then we'll slice them up nicely afterwards. Same thing with uploading the slides to the website. My job here is to introduce what is the GNU Radio project and what have we been up to for the last year. A whole bunch of this is going to be references to other great talks throughout the week. So we are, unsurprisingly, in Arizona State University. If you're here in the room, you've found it. If you're online, then this is a little bit of a detail, but we have been amazingly supported and hosted here at ASU, particularly by WISCA, the Center for Wireless Information Systems and Computational Architecture, as well as the Global Security Initiative here. Sitting in the corner is Brittany, who has been an amazing support throughout the year, and we really are quite grateful for her, as well as Julianne, Lonnie, and Dan Bliss, who have been supporting the event and encouraging us to be here. So it's great to be here, and I hope that you enjoy the rest of the campus. We were looking at floor plans of the Memorial Union and kind of squinting and saying, This looks either really big or really crowded, and I'm really pleased to see that it's quite big and quite nice. So the schedule for the week. We have been a little bit lax on pre-event emails. I do hope that you did find the information. The entire schedule, along with helpful information, is available on the conference website. So head to events.gnuradio.org/e GRCon23, and this is our overview of the week. We have 4 days of technical talks lined up. They basically run from about 9 o'clock to 5 o'clock. Got lots of breaks, lots of lunches, as well as on this calendar 2 socials. One more has snuck in on the Wednesday night, so I'll present that. On Saturday, we shift gears a bit. The technical talks pull back, and the hands-on component really goes wild. So we have a Capture the Flag event running throughout the week. I definitely encourage you to join that, no matter your level of experience with signal processing and wireless. There's a lot of great challenges. It starts from very simple and moves up to nigh on impossible to solve. So we have a room. It's just halfway down the hallway. You'll see the banner, Capture the Flag, and people can help you get GNU Radio installed there, as well as get set up with the various tools needed to participate. On Saturday, there'll be a presentation explaining the solutions to a bunch of those puzzles and answering questions. As well, we'll be talking a lot about GNU Radio 4.0 and what the architecture looks like. There's a series of great talks throughout the week, and on Saturday, we'll be doing a lot of discussion of, do we need to make modifications to that? How can we best meet everybody's needs without creating an overburdened toolkit? So the workshops. You're not going to be able to see all these because of the closed captions, but we have, I believe, 9 workshops this week. The way that the workshops work are that we have 2 rooms throughout the week set up, and these are all scheduled. They fit about 60 people sitting down at the desks, and more along the side if you're just interested in listening in a bit. There is no pre-registration, so if you're particularly interested in a talk or in a workshop, definitely show up a few minutes early. In practice, we've usually seen that 1 or 2 throughout the week will be, completely full to the doors. Most of them will have space to fit in. So try not to stress, and apologies if you don't quite get a front row seat. Meet and greet social. I just realized I didn't start my talk timer, so I'll just go as long as I want. We have 3 main events throughout the week. These are the ones that I mentioned earlier. This evening, we have our meet and greet social. It is down the hallway, so don't get lost. It starts immediately at 5 o'clock, right after the event, right after the main talks, and it's a chance to, have a hallway track with, some soda, some wine, some beer, and 2 hours of time to really get to chat. This is nice and casual, and all of the GNU Radio leads who are here in person will be kind of clustering up at the beginning of that event. And if you're new, if it's your first time coming to the event, please do drop by and say hello. We would love to meet you, and we would love to, help direct you and answer any questions you have about the event. If you don't feel like waiting until this evening, you've already found our lovely registration desk. They also act as our info desk, and the people there have been at more GRCons than I have, so they can certainly help direct you towards any questions. Then coming in, we have our Breakthrough Listen SETI reception. This is tomorrow evening. It's slightly after the event. It's about 6:30 start, and that's a short 5-10 minute walk north of here. They are welcoming every GNU Radio conference attendee, and it's going to be a great event talking about radio astronomy and a lot of the challenges and techniques that they're using. The folks who are running that have some talks beforehand, so you'll have a great idea of the type of things that they're interested in ahead of time. Free beer and wine. That's the main organizer there. Hi, Well. So then also finally on Thursday, we have our community dinner, 7 to 9 at the Arizona Heritage Center. This is about a 10-12 minute drive north of here. Apologies, there is no transport to it, but hopefully everyone will be able to find their way there in the 2 hours gap there. And that does have a full sit-down dinner. Semi sit-down, but full dinner. Some useful information. Hopefully you've already started finding the Wi-Fi. It is a little bit of a registration step, but if you have an email address or a US cell phone number or a cell phone number that's working here, we've seen it's pretty straightforward. If you have any issues, let us know, and we do have some ways of assisting with the registration process. I looked up the weather and I was planning on including something, and the only thing that the weather report showed was excessive heat. It does seem to be pretty warm. In here it's quite nice and cool, so a lot of this hopefully won't be a problem, but if you're out during the day, please do drink water, sunscreen. It is no joke. You will burn, and that's no way to enjoy the conference. Food and beverages. Again, we have AM and PM breaks. Lunch, it's all included. That'll all be served just down the hall in Arizona, the main ballroom, which has all of the exhibitor booths. So grab some food, look at some demos and chat. Those will be happening basically every single break. We also will have food and some beverage carts set up in here if you just need a bit of water. So that's the main housekeeping done. Hopefully you have a little bit of a grounding of what's going on. So now the question comes down to, what is GNU Radio? This is a fun one because I get lots of different answers when I ask people, what does GNU Radio mean to you? For a lot of people, it's just GNU Radio Companion. You download it, you pop open this toolkit, you can drag blocks around, and you can assemble a signal processing flow graph where your computation occurs through these graphical elements. You can configure the parameters and connections, and magically something happens when you hit the play button. And that is an amazing answer. That's something that's fairly accessible to people, and we're doing a lot of work to make it even more accessible. But it turns out that if you look underneath the hood, you find people who are doing it in embedded environments, pure C++, looking just at high throughput acceleration. So it is an entire software toolkit. So what happens when we say the GNU Radio project? Is it just this piece of software? If it was, I'd like to say that my job would be a lot easier. But no, it's this conference. It is the extensions to that main code base. Volk, which is the vector optimized library of kernels, which handles, it's a bespoke written high-speed SIMD instructions to do DSP operations. It's dozens of supporting projects and infrastructure. GNU Radio is used in so many places and also has continuous integration set up. It has various other deployments set up. All of this kind of gets administered by a group of volunteers that, whether they formally identify with being project members or just doing something in the community, I like to kind of wrap all of that within the phrase GNU Radio project. We have active contributors. I didn't look up the latest numbers, but on a usual year, we have about 100 to 130 people contributing code directly into one of these projects. We also end up with a couple dozen people who are contributing documentation or website fixes or CI improvements. We have continuously packages not only GNU Radio, but many SDR applications for Debian. And thus, if you're using it on Ubuntu, you're benefiting from his work. I'll take that as a moment also to shout out that if you have any interest in seeing GNU Radio run really well on Ubuntu, we could use a dedicated Ubuntu maintainer. This is not a particularly hard job because 90% of the work's already done, but it would be really nice if somebody would check for compatibility rather than just having Canonical vacuum up a semi-random set of packages into Ubuntu. We have an entire ecosystems of modules, applications, and interfaces. One of the fun things is always finding GNU Radio embedded in some application. So we have our entire ecosystem of out-of-tree modules, which in many cases is what pulls people to the toolkit initially. They see something that says, so I can get 802.11 as a software modem just running. And it uses this crazy dependency called GNU Radio. Or I've really always wondered how LoRa works. Oh, it was reverse engineered. Cool. Okay, the explanation is this video talk at some strange conference, and they start digging downwards. And then finally, as I said, it's this conference. It's European GNU Radio Days. some other online events. I don't know of any other in-person meetups, but if there are those out there, please do let us know so that we can feature you and support you. And then finally, we do manage to sneak this in underneath the subtitles. It's yourselves. In the end, I started here as an attendee, and it's the attendees and contributors and everyone using GNU Radio who ends up keeping this project alive. There is no formal organization. There is not a business behind this, and there is, this evolving structure over the last 20 years that has kept this project alive and thriving. So, thank you very much for being here. And if you see a bug, if you see something you'd like to improve, if you have input, you think something's not being done the way it should be, that's how everything gets done. So we look forward to your contributions and you being here. Here's some examples of that I pulled off from offline. Apologies if you were here last year. These do look somewhat familiar, but I thought that they were great examples, so I kept them. There's an entire book published in Brazil, I believe, using GNU Radio as an introduction to SDR. Last year I had some other examples. There's a Japanese book as well. There's books in a variety of languages and certainly blogs in a whole series. We would love to see the main toolkit translated a little bit better. It's a bit of a lofty goal. We could certainly do the user interface. Doing all of the DSP explanations would take a lot of work, but so did building the toolkit. Victor Kai presented in San Diego, I believe, which at this point is about 5 years ago, and went on as a high school student to win several science fairs using GNU Radio to do his work. And then repeatedly, we see examples of GNU Radio deployed and posted up on Twitter of either I'm trying this out, here's my project, etc. Here we have an integration with Microsoft Azure, and so we've seen Amazon AWS as well put up an example. It's amazing to see these things come up, and it really helps if you tell us if you're doing these things and you're publicizing them. We would love to help publicize them on the main GNU Radio channels. It's always interesting to dig them up and find out that entire huge projects such as the thesis are written around GNU Radio and the scheduler, which we're overhauling and would love your input on. And we only find out 6 months later after this person has finished their thesis. So yes. Governance. This is a quick one, but introducing the people behind this. So we're an unincorporated association, which is basically saying we wrote up some guidelines that say it takes a whole bunch of people to do this. We should have a few rules around voting and who gets to control the GitHub access. And so we wanted something that was really flexible. We wanted something that was lightweight, and we think we've mostly achieved that. So we won't talk all that much about it, but you can find our governance docs up on the website. We've just tagged them as 1.0. We've had them for 3 years. We didn't modify them. They seem to be working quite well. So who's in it? So as I've said, GNU Radio really is the community. This group of people are here as stewards and facilitators. In the end, you can't take a room of people like this and sign a contract for a conference venue. So there had to be somebody to actually hit pen to paper. And this group has ended up being the people who hold the pen. But very much we're doing it on your behalf. So I believe there's 17 people on this list. This composes the General Assembly. This is you can think of it as the general steering committee or steering group. It's certainly open to more people. If you have expertise that you don't see the project taking advantage of, that probably means that we could really use you as a volunteer. We have 3 people who are on the board. We have just run elections. So last year I was here presenting as the GNU Radio president, a role I'd held for 3 years. And as of 2 weeks ago, I am free. We've run the elections, and Mark Lichtman and Martin Braun are staying on as board members. I'm stepping down away from that role, and Josh Morman, who is probably a familiar face to many, has stepped up onto the board and as president. So thank you very much, Josh, for stepping up into that. It is immensely appreciated. He's back in the corner there. He will be up on stage giving a full discussion of what's been happening in terms of future plans and future efforts with GNU Radio tomorrow, I believe. And so, or was it Thursday? But we'll get to that shortly. So these are the teams. So the General Assembly acts as holding the pen and handling the paperwork and keeping the lights on. Here's where really the fun work gets done. These are open to all. Send an email and you're in. There's very, very much no barrier to entry here. And that is both because we can't find a reason for a barrier to entry, and because everyone who's ever asked has been, thoroughly qualified to be expressing an opinion and participating in the conversation. So we have our main architecture group. This discusses, the fundamentals of how GNU Radio should be put together as a technical software project. Where should we be going in terms of APIs? How do we handle heterogeneous compute better in the future? How can we get better acceleration on general purpose processors and take advantage of modern C++ developments, etc. GNU Radio Conference, those are the folks who organized this event. Special thanks to Samantha for organizing, heading up the organization of this event. So thank you, Sam, in the back. Infrastructure is literally the lights. It's the website, the CI, the strange servers that we've half forgotten in the corner that do, specific builds. So Andre Rhoda heads up that. GNU Radio Companion, developing the future direction of our graphical interface. We'll definitely see a little bit of that in the future slides. The signal metadata format. Who here in the room, out of curiosity, has seen SIGMF? It's a fairly good group. Who's using it? Oh, good. Lots of hands still. So there's going to be a workshop on SIGMF. This is our not only proposed, but standardized file format for storing IQ data as well as non-IQ sample data. Basically anything that's time series, including geolocation, in a nice human-readable and easily digestible format along with libraries. Trying to solve the binary file format where somebody just passes you a bin file and says, this has a radio recording from our field test last week. And you're like, what's the sample rate? What's the frequency? Where was it? What radio was it attached to? Did you turn it on? All that kind of information can be encoded in this. Volk, again, our SIMD library, documentation. Everyone here loves documentation, not necessarily writing it, but having it. This team, I cannot speak highly enough of. And then the board. If you want to reach the governance group, definitely shoot an email. The last square is open. There's a very loose framework for creating these teams. If you have a specific topic that you think there should be discussions on, that you would like to see, quarterly or monthly or even just a one-off meeting of, we can help coordinate that and we can help make that happen. So there's definitely things that are not covered with this that I personally would love to see us having more regular conversations about. Getting involved. So this is the point where, again, I kind of point out in the crowd and to the camera and say, if you find a bug, please report it. I've had people come up and speak to me in person and say, oh, I'm teaching, this university course with GNU Radio, and we've had this problem. We've worked it around and we've forked the project and we've made it work and stuff, but it's terrible. It's really hard to use. We might migrate off it. I'm like, okay, so what's the problem? They describe it and I'm like, okay, give me half an hour. We go away and we fix the code and it's done. So please don't suffer. Please, please don't suffer in silence, I suppose. We certainly have suffering going on. It is a big project, but please let us know. Same thing with the documentation. We have a page for every block. We have basic documentation for every block, but they could use examples, they could use expansion. Barry Duggan and others have been very busy filling these in, but this is a wiki. You can sign up. You don't even need to sign up. You can just edit a page and then somebody else will approve your changes. So if you spot some weird behavior and you're like, okay, this has changed, or this is an interesting way of expressing this polynomial, or I didn't know what format this should be in. Please edit the page, drop a link in, and we'll format it, but pass information up. Join the chat. This is another funny one. We have a very active chat server, hundreds of people actively there. We have several rooms on it. It's freely available, and I run into people who have never heard of it. So now none of you have the excuse. You've heard that we have a chat server. Same thing with our mailing list. There's a couple thousand people on that. Not always actively replying, but the body of expertise here is genuinely astonishing. And if you want to know about the implementation details of, a particular aspect of White Rabbit combined with a hydrogen maser over fiber, I know of at least 2 people who can probably give you some kind of an explanation of that. Filing issues, I've just covered. Reviewing them and adding details and recreating them. I'm very pleased to say we're going to be handling our backlog of these, but new issues come in all of the time, particularly if you follow my request. So jumping in there, anybody can comment on these, and adding detail and saying, this is still an issue, here's how I replicate it, and I think it might be related to this. Invaluable, absolutely invaluable, helping other people to make the code changes. Improving the tutorials. We had a grant that did some work on this, but there's always room for more. Give a talk about GNU Radio, at this conference, at other events, within your business, within your organization, at your local amateur radio club, whatever the venue or hack space, share the word. You're here, so you think it's a good project. Please let others know. It is free. So here's some of the things that we've been doing that are perhaps a bit more concrete and fresh. So we did participate in the Google Summer of Code again this year. This is an annual event run and funded by Google, where they provide stipends for people who are new to contributing to open source. For a long time, this was students only, and either this year or the previous year, they opened it up much more broadly, and it's anyone who has not contributed to open source before in a significant way. So we pair up students with projects and with mentors and work with them for about 11 weeks through the summer to do some improvement or some development with GNU Radio. So the 2 projects that we had running this summer, which are both coming to a conclusion, I think most basically this week, are GRC, a standalone application and pluggable workflows. So there's been an argument for some time, increasingly loudly voiced, that GNU Radio Companion as a graphical interface does not necessarily have to be tied in the code base directly to the GNU Radio toolkit. If you're running this on an embedded system, that directory is just irrelevant. Or you might want to supply your own interface for creating flow graphs, or you might want to take GNU Radio Companion and use it with something other than GNU Radio. And so this project takes the first steps towards pulling that out of the main code base, putting it in its own repository. We'll still be packaging it and building it and shipping it together and testing it all, but it's going to just give us a little bit more isolation between the two. And this particularly becomes interesting as we look at changing the graphical toolkit itself from GTK to Qt, which is a work in progress, a funded work in progress. And the student who was doing that was Rahul Balaji. And so they did some great work, and you can find their blog posts up on the website. The second project was Qt widget improvements. I don't think there's anybody here who will loudly voice that GNU Radio has the best spectrum displays or the best waterfalls. This project sadly doesn't quite replace that, although there's somebody here at the conference this week who I'm hoping will actually do that. But it does introduce a series of other improvements that both aid in the development of the existing widgets, keeping them living for more years, as well as adding things like matrix displays, a first-tier video display. So if you're running, for instance, the DVB examples, there's now going to be an in-tree video display that can show that. Small, but nice quality of life pieces. And that was Rohit Bisht who is doing the work there. Both these students were great to have on as the project. And both of them and the project and the Google Summer of Code application and management of that in its entirety was done by Håkon Vagstede, who was actually a GSOC student himself, or perhaps it was European Summer of Code. I should check that. But it was perhaps 5-6 years ago that he participated in that. So it was great to have that. And thanks to Sebastian, Josh, and Andre for being mentors on those projects as well. One of the community events that's run in Europe. Not everyone can fly over to the US, sadly, for GNU Radio Conference. And so there's European GNU Radio Days. This was a 2-day event held in Paris earlier this year. This must be the 4th or 5th time that it's been run. And so this was tremendously successful again. I believe they booked out the room, 60 plus people. And it was so large, actually, they had to move from their original venue of being inside of the Paris Observatory and the CIRT Research Institute within Paris to an off-site location just a couple blocks away. And the theme was synchronization. All these videos are available on YouTube, and some of them go phenomenally deeply into the topics of time and frequency transfer across satellites, how to handle fiber links, modern atomic clock development, which included GNU Radio as one of the tools being used, and in other aspects of DSP. This was my first time attending this event, and absolutely fabulous, and I'm definitely hoping to go again. I did not ask if they have a venue for next year, but a request that was made there was that they actively wanted to move to other locations around Europe. It's been held in France for the past few years, and in Germany for a few years as well. So if anybody here happens to be from Europe and have facilities and space for hosting an event, it's about 100 people max, it would be great to reach out to them. You can reach out to us and we can pass you along, or you can find their contact information on the site. The Facility for Antiproton and Ion Research. This is a GSI Helmholtz organization, and we have 2 people here, Ralph and Alexander, and you will see them throughout the week. Ralph is presenting 2 talks, one on Wednesday and one on Thursday, and they have been phenomenal. I want to say new members to the community, but they've been using GNU Radio for a very long time, which by my definition means they've been part of the GNU Radio project for a long time. But they reached out and said, we've been using GNU Radio, we're upgrading our particle accelerators processing systems, and GNU Radio is nice, it could be better. Do you want us to fork it and do our own thing, or would you like us to help improve GNU Radio for the future? And you can guess what our answer was. Please come and tell us how we can do this better. And they've not only told us, they've been doing a tremendous amount of work to actually make that happen. So catch these talks. If I had to say catch anything throughout this week, these are the ones that are going to be instrumental to where GNU Radio is going in the future. This is immensely compelling work, and they're both here, which is an immense boon to the project. If there's any other organizations which are doing work with GNU Radio and say, we have this piece which we think is an improvement, or there's this area here that we're looking at, we need to have be better, whatever that is. We need to stream 100 gigabit Ethernet, and your TCP blocks won't do it. That's probably not a core piece of your business. That's probably not a particularly core piece of IP that is your distinguishing piece between yourselves and other organizations. We would love to onboard those sorts of improvements, make them available to all, and make sure that they keep working with future versions of GNU Radio. There has to be an agreement of how they're going to be maintained in the future, but that's a conversation we'd love to have. And we have means and ways of supporting these sorts of efforts. The SETI Institute. So it would have been 3-4 years ago, we partnered up with the SETI Institute because GNU Radio had grown to a point where our financial transactions and our efforts and our logistics around this conference and elsewhere had simply outgrown our previous host organizations. And rather than being a parasite and wearing them down, we really wanted to find a better home that we could be better partners with. And the SETI Institute came up as a really perhaps slightly surprising but really clear choice. Their work with radio astronomy means that they're working with tremendously wide bandwidths, with flexible systems, different demands on how they do data processing. And so radio telescopes these days, as we'll hear, I imagine, are largely software-defined radios. And so, while they may not all be running on GNU Radio, the problem space has a very high overlap. And they're working on it in public with many scientists, with many very capable people, as well as doing science outreach, education, and a lot of the same goals that GNU Radio has. So this was a discussion piloted by the previous president, Ben Hilburn. We partnered up with the SETI Institute, and it's been a great last couple of years. And we're looking forward to expanding what we do with them over time. So definitely come along on to Wednesday to hear more about that from themselves. One of the key things that is enabled through the SETI Institute that wasn't with our previous hosts is the ability to apply for funding in government grants or scientific grants from different organizations. GNU Radio has done this. I'll be talking about that shortly. But if you have a project that you would be interested in applying for government funding with, or science, NSF, other funding organizations with, but you don't yourselves have the structure to do that, whether you're an individual or a small project or something, or just a group that wants to partner up, a larger organization that looking for a co-host, speak with us. The role that I've moved into primarily is as SETI Institute Principal Investigator for the GNU Radio project. So it's my responsibility to bridge us as a community to the resources at the SETI Institute. Please let us know, and we can do really cool things together. This was a Hackfest run at the Allen Telescope Array. This is an installation held by the SETI Institute and by SETI. And so we ran this in 2019. It was certainly not meant to be the last event, and we hope it won't be. Things got derailed, and we're getting them back on the tracks. So we hope to do this. It's an opportunity to actually get to use some of these dishes directly, to work with the data processing resources that they have. And one of the fun things is, really, they've let us point it at pretty much anything we want, with safety considerations and with some approval and scientific outcomes in mind. But for instance, Daniel Estevez, who's probably a familiar name to many people here, has been extensively using the Allen Telescope Array over the last several years to investigate various satellites, various different phenomena that you wouldn't be able to access from something you would have in your backyard, for instance, or readily in your car parking lot. So this was a phenomenally fun event, and we'll definitely do more of this in the future. There are 3 people here today from SETI, Rebecca McDonald, Simon Steele, and Wael, who stood up earlier. Please do catch them. They have a booth in the expo hall, as well as the social event they'll be running. Wael is speaking today at 1:15. And then Simon will be speaking tomorrow at 4:20. So I look forward to their talks and have really enjoyed working with them. Funding. So we'll jump into that grant. The GNU Radio project for many, many, many years was essentially run on the funding from this conference. And so we had basically whatever revenue we managed to generate from GRCon to literally keep the website online. And that had not mixed success, but mixed levels of success. We've now reached a point over the last couple of years where we do make enough from this conference to kind of comfortably keep things running, but not enough to ever hire somebody or to engage in large scale development. That remains out of reach based off of that funding pool. We have grants, which I'll talk about kind of 2 different levels of. We also have donations. Thank you for being at this conference. That's a tremendous help already. I'm not shilling for donations there. To anyone who's attending as a virtual attendee, if you put a few dollars into that virtual ticket, it's highly appreciated. Thank you for the donation. There's some gap there. There's definitely room for GNU Radio as an organization, as a project, to do a lot more. We could be doing training. We could be doing contracting work. We could be directly doing development contracts. There's a chicken and egg problem of being able to hire people onto that, but we're aware of it. And if you have advice on this, or if you have a route towards this, or are interested in in taking a jump and trying to make that work for yourself as a job, we'd love to hear about it. It's something we're interested in, but haven't figured out the solution on. And the end goal is sustainability. We're absolutely in great shape to continue running as we have been. The really interesting question is where will GNU Radio be in 5, 10, 15 years? So in terms of small pieces, we've become a member of NumFocus in 2021. This is an organization a nonprofit that supports scientific computing, largely in the Python space, though not exclusively. So we became a member, and a couple times a year we have the ability to apply for a small grant, kind of the $3,000 to $5,000 range. And we have received one of these to improve the tutorials. So if you've gone to the tutorials page and it's looked like this, it is thanks to NumFocus. A small amount of money can go a long ways. This was great work that was done a couple years ago. We did try applying for one grant this year and didn't make it through the review process, but certainly intend to do more in the future. And this is another space where, if you would like to get a little bit of funding to do something GNU Radio related, we are happy to help facilitate that through NumFocus. We do have a pot of money ourselves, a few tens of thousands of dollars that have been saved up over the last conferences, burning a hole in our pocket. We do have some ways to spend it, but we'd love to hear your ideas as well. So we have a grant ideas page up on our wiki. And again, this is a small pot of funding that can be pulled on to do small instrumental tasks to improve the ecosystem. So it doesn't have to be an idea that's here. And the path to applying for this is extremely straightforward. Send an email and we'll chat with you. Until that becomes very popular, that'll probably remain our process, and the General Assembly will be the body kind of reviewing and approving the sending of funds. On a much larger scale, and I don't know if our friends from ARDC have arrived today. Nobody's waving at me, so perhaps not quite yet. But the Amateur Radio Digital Communications Group is a nonprofit that was funded several years ago with a large set of money from early tech IP addresses being sold, as well as donations. And so their mission is to support, promote, and enhance digital communications and broader communication science and technology. Very much the space that GNU Radio loves to be in. And so we applied for a grant a couple of years ago, and I actually received $263,000 from them. And this is a grant entitled Usability Enhancements. And we're going through this. I'll quickly flash through some of the main goals. We are looking for 2 contractors to carry out some work. But the main theme of this was, what are the pain points that we haven't addressed through GNU Radio in the past? What have volunteers not been reaching? So the first bit is ease of installation of GNU Radio and the out-of-tree modules. We're now at a really decent point with Radio Condo where GNU Radio is actually installable on Windows, it's installable on Mac, and a subset of out-of-tree modules are fairly straightforwardly installable. But there's room for improvement. We have quite a significant chunk of that 260K is actually devoted to this or earmarked for this. So if you have an interest or know of people who are really good with building Windows installers or Mac installers, native binaries that just work like you'd really hope an application would, and sometimes GNU Radio doesn't, we'd love to talk with you and make this easier for everybody. Documentation, some portions of this have already been worked on, but making documentation more easily available offline, etc. Just going through flow graphs and making sure all the examples work, etc. Software maintenance and support. This is currently being worked on. What I said, all of our open issues are being triaged, so we'll have a better perspective of where the project's at. Continuous integration improvements and improving coverage of the continuous integration. GNU Radio Companion, making a preferences window, so you don't have to open up, /.GNURadio/grc.conf. There will be a native UI by the start of next year, basically, early next year. as well as a list of the out-of-tree modules that are installed and available within your particular GRC installation. Opening up example flow graphs, we actually have a lot of them. People don't find them, and making documentation a little bit more visible within GRC. If you think you can help or help connect us with anybody who can help with those tasks or are interested in finding out more, email us at jobs@gnuradio.org. I am conscious that our time is rolling over, so I am nearly done. This is the last main bit for me, is to thank the organizations and groups which are here today as more than just attendees, who are contributing directly to our exhibit hall, which is a key part of our experience, and to directly supporting the conference and as a carry-on the project itself. So Edis Research and Analog Devices have come in respectively as our diamond and platinum sponsors. Both of them have been extremely regular in this, and we just tremendously appreciate it. Without them, GNU Radio certainly wouldn't be the project that it is today. The same holds true for our gold level sponsors, between Rampart, Vesperix, ARDC, DeepSig, Epic Solutions, and Peraton Labs. Many of these names are very familiar, and there's some very welcome new ones here. So thank you to them, and be sure to, if you see and speak to them, we're very grateful for them. Last sets. So within the silver level, we have Redwire, RF, NM. RF's not magic. John Hopkins Applied Physics Lab, Andro, AnySignal, and B-Cubed Engineering. I believe all of the above, except for AnySignal, unfortunately, have a booth in the exhibit hall. And then our Patreon level sponsors. This is $250. We thank them for just standing up and saying, we use GNU Radio, and basically buying the project a cup of coffee. It is tremendously appreciated. And no matter the scope of contribution here, GNU Radio has to be used, has to be useful, or it's pointless. Reiterating a couple of the last points, get involved, please. Contribute with organizing anything. Advertise that you use GNU Radio on your website. If you would want to be featured, we would love to help feature you, whether that's a white paper, whether that's sharing some announcement that you have. If you are publishing a paper using GNU Radio, we would love to feature that. Write a letter of support. As we go to grant agencies, the question we get is, what is the impact of this project? And we say, oh, it's very large, we promise. Letters are very helpful for this. And so if your organization uses GNU Radio commercially or in a research setting, we'd love to build up a body of evidence that we can supply. And join a team, any of those ones that I listed earlier. All these slides, all this information is available on the main website. And then this is myself. I'll be around all week. I'm easy to find. Anybody who is wearing a white lanyard is part of the organizing and leadership team. So if you have questions, anything, find anyone with a white lanyard. That is the end of my talk. We have 15 minutes before our keynote. There is an introduction for that, so I'll invite Dan Bliss up to give that introduction. I think the new, largely standing and then newly elected president are coming up for a few words. But thank you very much, and have a great week at the conference.
Yeah. So let's give another round of applause for Derek. 3 years of really hard work, extremely dedicated leadership, and we're very grateful he's sticking around as SETI PI, so he's going to be an interface on the business end of all of this. So another round of applause for Derek. So yeah, Dr. Bliss, don't mind coming up and introducing our keynote speaker.
While we're doing that, did we have any questions from the audience? We can probably take one or two.
Catch me in a hallway.
All right.
Well, hello, everyone. Thank you for, excellent. Got a coin. Thanks for coming to ASU. I'm going to say a few things about ASU before I introduce Lindy. First of all, it's hot here. Everyone has told you to drink water. Seriously, drink water. Actually, I do not see a lot of water on the tables here. That's a mistake. It's really dry here, so you actually sweat more than you realize, so you're gonna get dehydrated by the end of the day. So if you're around here, you know this, but drink water, maybe some electrolytes, all those sorts of things. I'll say a couple comments about ASU. So ASU is a big school. You probably have figured that out already. Every time I try to figure out how many students we have, it's changed on me. I think the last number I saw was 140,000. Our engineering department, for example, has over 30,000 students in the engineering department. There are lots of games people play about how they define the largest school, so I won't try to get into that. But we definitely, by many definitions, are the largest university and certainly the largest engineering program as well. I think my executive vice president for research wants me to say something like this. If you take a look at ASU 15, 20 years ago, we were a large but relatively sleepy research university. And over the course of this last couple decades, we have gone from that towards heading towards $1 billion a year in research expenditures, which, given that we were a few decades ago doing a handful of tens of millions of dollars in research expenditures, is an amazing transition. So depending on how you count these sorts of things, for universities without a medical school, we were up to like, I think, number 6 in terms of research expenditures, and now we are actually trying to start a medical school, so I'm not sure how that's all going to work out. All right, so, oops, I lost my notes. So I'm really thankful that Lindy offered to speak to us. There aren't many speakers who are nice enough to write you an entire book about their background. So Lindy wrote A Portrait of a Scientist as a Young Woman, a memoir. It's an excellent book. It's really interesting. It talks about a lot of the issues just sort of lots of people deal with growing up, and then many which are specific to her. Certainly worth reading, getting and reading that book. So Lindy is Dr. Lindy Elkins Tanton is a professor here at ASU. She's been lots of places and has an interesting background. When she started here, 2014, I believe, she started as the director of the School of Earth and Space Science. School of Earth and Space Exploration. Somehow I got that wrong. CC, which is basically our astronomy program, and it's both focused on the sorts of things we worry about looking at Earth and looking outside, looking offside as well. She has a really interesting background as well, which I think probably leads to her success, in that she hasn't just had academic experiences. I mean, she's been a researcher, a professor, but she's also done business consulting as well. And I think that sort of understanding about how to make systems of people work is one of the reasons why she has been so successful. She earned her BS in geology, MS in geochemistry, and PhD in geology, all from MIT. Has worked at Brown University, St. Mary's College, Maryland, and of course at MIT, in addition to Carnegie Institute for Sciences. Maybe most interestingly at the moment, she is the vice president for the Interplanetary Initiative, but technically she runs the thing. So that's a really interesting group of people who are thinking about what is it like. You know, what are we going to do as we try to start exploring other planets? And in fact, there are people involved thinking about entirely different star systems as well. How does that look? And probably the thing that which she spends most of her time on now, though she can tell you if that's true, it's a huge amount of effort. She runs the Psyche mission, which is basically we're going to go send a spacecraft to explore a metal asteroid and try to figure out what's going on there. So that's a huge NASA program, and she's the one who runs it, which is a huge amount of effort. So with that, I will introduce Lindy, if she's ready.
All right. How's that? Good location for the mic, thanks. It is really, really fun to be here. And today is a special day for 3 reasons. First of all, because it was nice that Dan mentioned my book, the paperback edition, was released today. Today is L-30, launch minus 30 days for the mission that I'm going to talk about. Yes, I know. And the other great thing about today is that I get to come and talk with you all, which is just a super pleasure. I feel like kind of you're my people, even though I'm just a radio dilettante. You're going to see something about all the radio needs we have for Psyche mission. So this is the NASA Psyche mission, an electric journey to a metallic world. And so Dan said we think that it's made of metal. The reason that it's electric journey is because we're using Hall effect ion thrusters. And so I'm going to take you on a quick tour through how we came to this point with this NASA mission, and then I'm going to show you hardware pictures, because isn't that everybody's favorite thing? We all want hardware pictures, that's it. And I think that's it, and then I'm really happy to answer questions. So just a reminder that we humans have sent a lot of robotic probes out into the solar system, and in some cases also crewed ones, to rocky planets. So here's our moon, and I'm sure that a bunch of you know that this is, actually I should ask, does anybody know what basin that is on the moon? You can just raise your hand if you happen to know what it is. I know we're not primarily a planetary crowd, but there's a lot of radio in planetary. That's Orientale Basin, caused by a giant meteoroid impact about 4 billion years ago, and it's on the limb of the moon. So it's one of the many, many, many ways that we know that we've sent spacecraft to the moon, because you can't see it from the Earth. So if you need a favorite lunar basin, I recommend that one. It's so beautiful. It's filled with frozen lava, which makes it extra beautiful. And we've also gone to Mars. This is Burns Cliff on Mars, and Mercury, and Venus. So all these rocky bodies we've visited and we've learned a lot about. We've also been to gas giant and ice giant bodies like Jupiter here. And the one kind of body that we have not yet explored in our solar system is a body with a surface of metal. And that's what we think that this asteroid Psyche is. It was named Psyche after the goddess when it was discovered in 1852. At that time, they did not know that it was mostly made of metal. This is an artist's interpretation, obviously, not an image, but I worry these are so ubiquitous on the web. If you Google the mission, there are all these beautiful artist interpretations done by this guy, Peter Rubin, who's actually a Hollywood illustrator. He worked on Ghostbusters, and he did one of the S's for Superman. He told me proudly it's one of the few S's that is actually copyrighted. So he's a super talented illustrator. It's one of the pleasures of working on a really gigantic project, that you get to work with people like this. So he and I Zoomed with each other on the weekends for over a year while I downloaded into his brain all of our hypotheses about the science of this asteroid, how it came to be, and he translated it into art. And so everything that you see here is a scientifically motivated hypothesis. But two really important things for you to remember. Probably everything I tell you today about the asteroid will be wrong when we get there, because space always surprises us. And the other thing is that this is actually what Psyche looks like from Earth. Can you spot it? It's that one. That's Psyche. So asteroid, of course, means star-like. And there is a great story about the people who first discovered the asteroids, which I'm not going to tell you right now, but if there's time at the end, I can tell you if you want to know. We have no images of Psyche aside from a very, very blurry kind of shape model, basically. And so that's an important reminder. We're all going to see what a metal surface looks like for the first time together. And in fact, we have already written the data pipeline here at ASU, because we're running the imagers on the spacecraft and we're running the data center here at ASU. We've already written the pipeline such that the images that come from the spacecraft, we're going to load them onto the internet within a half hour of our receipt for everyone in the world to look at once, because we believe that space exploration is for everyone. And we don't think that curating and editing our images is going to stop people from finding dinosaur bones and smiles and cities and canals and things like that. And so anyone who wants to find those things will definitely find them, and all the rest of us can be scratching our head at the same time, sharing a big human experience. What is this place? So this is one of the best shape models that we have for Psyche. It comes from the paper at the bottom, Shepard et al. 2021. And Mike Shepard was comparing his shape models to the ones above it, his own previous one, and another one by Ferret et al. And you can see there's similarities in them. This is a really amazing, beautiful computational technique They take observations from a wide range of wavelengths. This one they used rest in peace Arecibo S-band, and the Atacama Large Millimeter Array, and also images from Keck using adaptive optics and the Very Large Telescope. And they take these images of Psyche from these different sources as it rotates, and then they derive from that a shape model for the asteroid. And so I would like to say that we kind of know what Psyche's shape is, except that there are other very talented groups that also did shape models, and they're not that similar to this. And so you might imagine right away that one of our challenges is getting into orbit around a body whose shape and composition we don't know. So there's so many really great things about this. The way that you win a competed NASA mission is you compete for years. And so 12 years ago, I started working on this mission with about 4 people. Then we selected Psyche as our target. In 2014, we responded to the NASA invitation for the Discovery program, and we submitted a 240-page initial proposal competing with 27 other missions. And then we were down selected after a year to be one of 5 to compete in step 2 and submit a 1,000-page concept study report and have a full week in-person review panel. It is a very, very intensive process. It feels like the Super Bowl. And by the end of that, we had 150 people working on the team. And then we were told that we won. We and the Lucy mission were selected for flight in 2017. And so 6 years after we started working on it, we're selected for flight. And now, 7 years later, we're about to launch. And each one of these things is just a marathon that leads to another marathon. Because if we can get our spacecraft off the ground successfully, it's going to be on its cruise for 5.8 years before it even reaches the asteroid. So overall, it's a 20-year project. The budget is $1 billion. And so it's a sort of a different scale than what, we academics are usually used to dealing with. So the thing I say about Psyche's shape is that we don't really know what it is. We will know what it is. And I always say it's shaped like a potato because potatoes come in many shapes, so I'm not wrong, whatever it is. And so the team, the Assembly Test and Launch Ops team, I just saw this 2 weeks ago. I was down in Florida at the Cape where our spacecraft is waiting for us and where the Assembly Test and Launch Operations team is working. And they made this as their screensaver. And when I came in and saw it and I took its picture and they said, "See, we listen to you when you say it's shaped like a potato." There's also such a thing as potato testing, which is another reason for potato. So it's a fairly large asteroid as asteroids go. It's about the size of Switzerland. I have many maps like this that I show depending on where I am, and I just didn't feel like putting in the Arizona one. It would more or less reach between here and Flagstaff. It's the width of Massachusetts without the Cape. Its surface area is about the same as the surface area of the state of California. So in the end, we're going to be orbiting. We're not a lander. We're not a sample return. We're just an orbiter. But we're skipping the flyby step. NASA always says we fly by first, then we learn something, then we orbit, and then we land, and then we rove. Well, we skip flyby, we're going to orbit. So imagine orbiting over California for 26 months trying to figure out what California is. That's basically what we're going to do. So, oh yeah, also there it is another time, in case you need 2 perspectives. I can't remember what talk that was for. Somebody, obviously, in that part of the world. All right, so where is Psyche? So this is a picture of our solar system from the sun out to Jupiter only, and you can see the purple are the main belt asteroids, and they are sort of a more or less accurate representation of the number of main belt asteroids. We know, I think, between 1 and 2 million of them. We think there's probably 2 million main belt asteroids. And then there are those really cool ones in yellow that are called the Jupiter Trojans. They orbit in the Lagrange points of relative stability at 60 degrees ahead and behind of Jupiter, and they are going to be visited by our sister mission, Lucy. So she's also going off to visit a new kind of object, probably icy and rocky. So Psyche is in the outer main belt out here. When Psyche is at its closest, that is to say, it's on the same side of the sun as the Earth is, and the ellipticity of the orbits are aligned, the closest it comes to us is about 250 million kilometers. That is 3 times farther away than Mars at its closest approach. And at its farthest, it's 650 million kilometers away. And of course, there are times when we have a solar conjunction between us and we can't communicate at all. And I know that you all know that all of the communications I'm talking about occur via radio waves. And so this is an X-band radio machine that we built. Why do we care about how far away it is? Because I don't know how many of you have seen these headlines. Has anybody seen these headlines? How Psyche is going to make all of us a billionaire? I bet a few of you have seen them. If you Google it, there are literally hundreds of times this has been written in the last 6 years, how Psyche's going to make us a billionaire. Look at these outlets, Forbes and Smithsonian. This metal-rich, potato-shaped asteroid could be worth $10 quintillion. Okay, so where's the truth in this? So if it were possible to bring Psyche to Earth, and if it were possible to do that without swamping the market so that you would still get your value, it actually would be worth $10 quintillion. But there are about 1,000 things that are completely fallacious about this. We have literally no technology to bring this back, absolutely none. And if we did, we would probably destroy the Earth by accident, and that would be really sad because there would have been a lot of investment, you know? And then even if we could bring it back to the Earth and park it in some stable orbit, the markets would be swamped and it would be worth nothing. We are never, ever, ever going to get a financial return from Psyche, but these organizations can't resist. I've talked to the guy who writes about space for Forbes, Jamie Carter, and he does get it right in the text. He explains that it's not going to make us rich. But he said, I can't stop running these headlines because I write about science for Forbes. These are the biggest readerships I've ever had. Like, he's never been able to talk about a giant market from space before. So I think that's kind of hilarious and funny. And so the Miami Herald, this person really got it right. She worked really hard on this. Psyche is not going to make us rich. It is not going to hit the Earth. But we have another reason to visit it, which is the science. So let's talk about what we think Psyche is. How do you get a big blob of metal? It's probably a blob of metal and rock. Actually, it's probably a blob of metal, rock, and pore space, like void space. So what I'm showing you here is a cartoon of what we call a planetesimal. So, all right, here's the number that I always tell my students if they don't memorize it, they fail. 4,568 million years ago. That's the first solids in our solar system in the dust and gas disk that was spinning around our proto-star, 4,568 million years ago. In the first 2 million years of that gigantic number of millions, these bodies clumped up into things that look like miniature planets, the size of cities or continents, and they're called planetesimals. They became the feeding material to build the rocky planets and the cores of the ice and gas giants. And in many cases, they melted from the short-lived radioisotope aluminum-26. And the whole story of how do we know there was a short-lived radioisotope aluminum-26, which is absolutely not existing, it's completely extinct now. We know that there was, and it was certainly heated enough to melt these bodies. And so that what I'm showing here is the metal. So the original material is metal and rock intimately mixed on a centimeter or a millimeter scale. But the metal that's involved here is mostly iron, and it's twice as dense as the rock. So it's about 7,000 kilograms per cubic meter, and the rock is only about 3,500. So when you melt it, the metal sinks to the middle and forms a metal core. The same process and the same structure that all the rocky planets have, because all the rocky planets have a metal core, including the moon has a little metal core. And on the Earth, it's where our magnetic dynamo is formed, of course, and all kinds of space weather results from all this. And I know that affects what you guys do. And so it's all connected, right? It's all connected. So what we think happened was the only way we can think of so far that we would find big amounts of metal with no rock involved. And there are a lot of metal meteorites that have fallen to Earth. And by the way, virtually all the meteorites on Earth transited in the recent past from the asteroid belt, except for the few that came from the moon or Mars, or maybe an unidentified, we don't know what else. But let's say 98% of them came from the asteroid belt in recent times. So we think they're parts of the metal core of planetesimals like this. So this is what we think happened. We think that in that early high energy beginning, the rock was knocked off by impacts, that it froze from the outside in and created a magnetic field and erupted sulfur onto its surface and was knocked over on its side to get to where we are today. And so in fact, you know, the Earth's spin axis is, 23 degrees off of perpendicular to the ecliptic plane of our orbit. Psyche's spin axis is lying more or less in the plane of the ecliptic. So it spins like a rotisserie chicken, which you could imagine makes lighting conditions interesting because it has a 5 Earth year orbit. And for a quarter of that time, its North Pole is only lit and its South Pole is super freezing cold. Then it's sideways, so it's fully lit. And then in the next quarter, its South Pole is lit and its North Pole is freezing cold. So you need to arrive at the right time to get the pictures that we want to share with everybody. It's an interesting problem. So that's our fiducial hypothesis. And again, could very, very likely be wrong. There are about 9 asteroids that people have found that we think are made mostly of metal. Psyche is by far the biggest one, and the only one that's roundish, triaxial ellipsoid. And so there's only one of it in the solar system. You can't really apply a normal distribution of hypotheses to a singular object. So that makes it interesting to try to plan your mission. So this is the cover of our step 1 proposal, and now you know what that is. That's the moment of impact between 2 planetesimals. Imagine the challenge of trying to sell to NASA and a bunch of review panelists a mission to an object they probably have never heard of and we have no pictures of. You got to tell the human narrative to get people involved. And so that's where Peter Rubin came in, and we're trying to tell the story over and over again of what we think Psyche is. And then here's the cover of our concept study report, that 1,000-page thing. It's about 30 seconds later, maybe, and the impactor's screaming off to the bottom left, and that red hot metal core is starting to be revealed. That's what we think we're going to see. But again, probably wrong. And I always ask everywhere I speak, what else would create a gigantic concentration of metal? Our second favorite hypothesis is that it might be material that formed very near to the sun and was therefore reduced by the heat and radiation of the young star, so that the iron atoms were reduced to metal and pulled out of the oxide phase. There's no evidence for iron oxide on Psyche from reflected light spectra, which is very sensitive to iron oxide. So if you're a chemist at all, that's a bizarre creature. And so I've had knowledgeable humans tell me that it is not the Death Star because it's too small, and it's not the Death Star prototype because it's too big. So those are my only options, planetesimal or reduced material. That's probably it. I want to mention that we've got a really big student collaboration and public engagement program. We have 4 major programs, and one of the big ones is undergraduate senior capstone program. And then we also have this art program where every year we pick 16 student artists from people who apply to us, and we fund them to make 4 original works of art during the year. And then we do a virtual gallery, and also we have art that travels. There's some in the Phoenix Sky Harbor Airport right now in Terminal 3, if you happen to go through Terminal 3. And I thought that you all might particularly appreciate this platter on the bottom left. It's a pretty big platter, if you can see kind of what my arms are showing you. It's very, very heavy, made by this amazing ceramicist. And he wanted the glaze in the middle, which is very bumpy, to have a texture that he emotionally associated with what a metal surface might be like. So he made a glaze out of thermite, which is a super exothermic iron-bearing thing that can be used. For example, at MIT, famously, they used it to weld the trolley wheel to the track back in the day by just putting thermite on it, waiting. Isn't that funny? Like, it's really funny for the trolley people. But no one was hurt in the making of this bladder. Amazingly, it did trigger the thermal alarm on the kiln, but even the kiln survived. So this is the kind of stuff we get, really great stuff. I wanted to just say, before I go on, we've had over 50 colleges and universities and over 1,500 students from everywhere across the country participate in this. And if you are at a university with a capstone program that would like to have offered real mission problems from the Psyche mission to your students, get in touch, because that's what we do. So our first science objective of 5, the only one I'm going to talk about, is whether Psyche is a core or if it's unmelted material. And so, as I was referring to a moment ago, those are our best 2 guesses. Who knows? And this is another of Peter Rubin's artworks, because it turns out that impacts into metal do not look the same as impacts into stone or ice. With metal, if it's a small impact, the spall from around the liquidized material actually freezes before it falls down. So you get these little spiky, we've all seen those stop action camera photographs of droplets into milk, and it makes that crown of splash. And with the very tiny impacts, or impacts sort of centimeter size, you actually get a frozen rim around it, which could be pretty cool to see. Could be, we'll find out. And so we've been looking at meteorite analogs. So we've been looking at the reflected spectra and the density comparison with Psyche to see what we could find in our collection on Earth of 70,000 meteorites, to see if anything matches Psyche. And regular metal meteorites and sulfur-bearing ones do match, but the very best match of all, bizarrely, and I'm not expecting there to be meteorite like jargon experts here, are these bizarre meteorites called CB chondrites. There are very few of them. If you look on the one on the top left, you can infer that the gray is the metal, and the darker gray is the rock. And the metal, the shiny pale gray, see how those are really shaped as circles in most cases. You can see that this is a polished section through a series of things that used to be spheres. So it's thought that those were actually splashed droplets of liquid metal from a giant impact. It's sort of a froth after an impact. And so the question we're left with is, can you make a froth the size of Massachusetts? That would require a very different scale of impact than the little planetesimals I was talking about. Don't know, we'll find out together. So let's get to the hardware. So I lead the mission here out of ASU. Jet Propulsion Laboratory is our mission manager. Maxar is our partner. They built the spacecraft bus and the power system. Danish Technical University and Johns Hopkins and Malin Space Science Systems built our science instruments. So that's what the spacecraft is going to look like after it spreads its wings. And in about 2 weeks, I'll be down in Florida for the remainder, and I'll get to go watch encapsulation as they put the folded up spacecraft into the fairing, and that'll be the last time any of us see it, which is kind of a crazy idea. Something. I will tell you all about the launch vehicle. It's so exciting. Okay. Yeah. So here's a picture of the spacecraft bus with a human for scale. This is Maxar's smallest off-the-line spacecraft bus. And now we get to like the good radio science stuff. See that beautiful high gain antenna up on the top? And then there is, I think down at the bottom, it's probably behind that really excellent caption, the low gain antennas. We have 3 low gain antennas, because if we turn on our high gain antenna before we're 1 or 2 tenths of an AU away from the Earth, I forget exactly what the number is, we will blow out the deep space network, and they will blow us out too. So that would be bad. So we use a low gain antenna until we're far enough away that we can communicate via the high gain. And you can see how we've taken our science instruments and put them up on booms as far from the main bulk of the spacecraft as we can. And the magnetometers, we really want to see if there's a magnetic field, are in a gradiometer configuration midway up the beam and at the top, so that we can subtract the spacecraft field from what we're measuring. And so that's a really great calculation you might want to give to your students. What's the optimal spacing on a 3-meter boom of 2 magnetometers to subtract a spacecraft field? It's kind of a cool calculation to do. So when we unfold the solar arrays, they're almost 25 meters across. And at Earth, they're 20 kilowatt solar arrays, and it's about the size of a singles tennis court. So that's the spacecraft we built, a real big one, a beauty. Okay, here we go. We are going to launch, hopefully on October 5th at 10:38 a.m. Eastern Time on a SpaceX Falcon Heavy. And they're going to re-land the side boosters. So it's going to be epic. And I witnessed this last November, and I will tell you, it's the biggest sonic boom. And so if you have any inclination to just go to Florida, there are plenty of public places to watch from where you will be knocked over by that sonic boom. It's super exciting. And so that's the plan. And for many various reasons, we do not, so terminology. We have a launch period, which has to be at least 20 days long, and there has to be at least some time on each of those days, according to NASA law, that we can launch. And so our launch period is October 5th through the 25th. So we have 21 days. And every day we have at least one, but we only picked one, instantaneous launch second. So we don't have a launch window on a day, we have a launch second. And so our launch second is 10:38 and I think like 36 seconds. And so that makes it interesting. I've been learning so much about rockets, which is quite amazing and fascinating. And so I really recommend this. So we're going to launch 60 minutes later, about an hour, well, 62 minutes later, the spacecraft is going to separate from the final stage of the rocket. And then it goes through a whole series of autonomous behaviors all by itself. The first thing it does is detumble, which is the proper phrase, but we try not to use it with the press because it sounds scary. So we asked for a tip off from the rocket with no angular momentum. We'll probably get a little bit. So we have to get ourselves stabilized. We'll start warming up the comms equipment, and then we'll unfold first one solar array and then the other. That's totally autonomous. And then we will get into a sun search, and we will go and we'll face the spacecraft toward the sun, and then we will go into safe mode. And so that whole thing could take a couple of hours. During that time, radio science. So during that time, we're not going to be consciously, like purposefully trying to get the spacecraft to communicate with Earth, not till it gets into its safe mode. But the low gain antennas are very broad in their beam, and so they'll be sweeping across the Earth occasionally as it rotates. And so what we hope to get is at least a carrier wave, if not some of the telemetry, which is on the polarized wave that gets superimposed on the carrier wave, so that we'll at least find out that the spacecraft is alive. So the Deep Space Network will be totally dedicated to Psyche for a little while. We'll have Canberra, we'll have Goldstone, we'll have Madrid. And then after that, when we're purposefully facing toward the Earth, that's when we'll really get a lock on and we'll get all the telemetry and health data. That could be as late as 3 hours after separation, depending on where the Earth is with respect to the spacecraft when the spacecraft starts its sweeping search. So if its sweeping search starts just after it passes the Earth, it could be 40 minutes before it comes back around and hits the Earth. And so in case you all watch with nerves like we're gonna be, don't worry if it's still 2 hours and we haven't heard, it's probably fine. But we are expecting to get at least some carrier wave a bit earlier because as our mission ops lead, it says the spacecraft's going to be very close to the Earth. It's going to be shouting. The Deep Space Network is very sensitive. We'll probably know that the spacecraft is up and alert. But nobody really jumps up and down with joy until the spacecraft is power positive and in communications and thermally stable. Those are the 3 things. So as soon as we get those 3 things, feel free to be super excited wherever you are in the world. So that's what we're hoping for. But wait, I just want to say very briefly, we were supposed to launch last year. Turns out, super hard to build a giant spacecraft during COVID. Almost all of our major build happened during COVID, and JPL was fully closed for a number of months, which we did not have in our margin. And then we went through a really interesting thing that I just want to mention in case this is of interest to any of you and you want to have further conversations about it. It was really a team culture thing that caused us to be surprised a year ago, April, that we were not going to make it to launch in August. The guidance, navigation, and control part of the team. Now, we wrote new core flight software from scratch from this mission. We are not using JPL heritage flight software, long story. The GNC part, and of course, even if you don't know what guidance, navigation, and control software is, it's obvious that you wouldn't launch without it, right? You need that. And that team was not able to get their testing done in time for us to launch. The reason that this surprised us is because of a team culture issue. That team had effectively been silenced. Their management did not, with high fidelity, bring their concerns upward through the several other layers of management. At that time, we had about 850 people on the team across dozens of organizations, and we didn't hear from them. And so one key lesson for me was silence is not a good sign. Silence is a bad sign. And another thing is, in your efforts to spread a team culture where every voice can be heard, because that is a huge risk reducer, it's hard to make sure that everybody buys in and knows how to implement that. And so, it's humans who create all the tragedies and all the miracles. It's not, the hardware is not the hardest part. And so even the software is not the hardest part. And so that's a really important lesson and something that I'm always eager to talk about. All right, so here's a little part of our team. And again, we are 850 at peak. We're about 250 now. In total overall time, we've had over 2,000 people work on this project. So our launch is October of this year. And then initial checkout is 100 days in that red crossed, what would it be like, red highlighted part of our trajectory. And then we go around the sun, and then we get a Mars gravity assist in 2026. All the parts of the trajectory that have the gray highlight, that's when we're thrusting. So solar electric propulsion is super different than chemical propulsion. You thrust more or less all the time, rather than just the occasional, burst. And then the blue dots are when we're testing the deep space optical comm, which is the threat to radio. They're going to use lasers. I'll show you pictures in a minute. And so then in 2029, we will arrive at Psyche, we'll enter into orbit, and we'll orbit for 26 months, which will take us a little more than halfway around the sun with the asteroid. So deep space optical comms. So this is a tech demo that we're flying on behalf of NASA. And beware ye the tech demo, which is supposed to just plug in and bolt on, ha ha. This is a fantastic demo, and I'm making snide comments, but I love this demo, and we are super excited to be flying it. But it was not easy to accommodate. It weighs more than all our science instruments put together. It costs more than all our science instruments put together. It uses more energy than all of our science instruments put together. It was a big deal. We're very excited about it, and Bill Klipstein, who leads this project, is just a wizard. And so they have had to build not just the flight laser transceiver that you see on the right that is on the spacecraft, but also a receiver on Earth and a transmitter on Earth, which you see there. So the transmitter is at Table Mountain and the receiver is at Palomar, and they've got all those blue dot chances to test this over 2 years. And so the idea is you can just encode a lot more information in a laser than you can in radio out to certain distances. So it doesn't actually help us at Psyche, and we will not be using it at Psyche because this baby is so magnetic it would screw up everything else we're trying to measure. And just for those of you who like this kind of thing, the spacecraft has got good pointing ability. It's got to be able to point back very precisely to the Deep Space Network from 3+ astronomical units away. But that pointing ability was not good enough for the Deep Space Optical Comm. And so I thought it was a joke the day they told me they were going to solve that by releasing entirely from the spacecraft and auto-pointing themselves using electromagnets as the Deep Space Optical Comm transceiver floated in space, free. I'm like, ha ha ha, that's a stupid idea because it's so dangerous for the spacecraft. But no, that's exactly what they had to do. So we built a cage around it so that it can't float very far because you don't want like a bowling ball in your trunk while you're trying to later maneuver. And then it has, NASA is very good at unlocking stuff in space. Just look at James Webb, right? Not so great at locking stuff back up. And so they had to invent locking procedures for this. Really, really interesting. And I will just add, the receiver, this was one of my favorite tech geek things that I learned about in the last few years. It's an array of superconducting nanowires that are so sensitive that the energy from a single photon from this laser will actually bring them out of superconduction and allow the detection of that photon, and then they cool it again. Isn't that awesome? Superconducting nanowires. We need to make like t-shirts, I think. It's kind of great. All right. So Psyche, we'll get there. We'll do a high orbit, a closer orbit, as we learn the gravity field better and better from Doppler. That's how we learn the gravity field with the X-band radio, same when we use for comms. And then we'll do a plane change maneuver and go down really low. So all of this is enabled by radio, and all of our information goes back and forth. So here's some hardware. This is a spacecraft shipping container. It's basically a mobile clean room. The spacecraft is built under extremely clean conditions. And so this is a fully sealed clean room with double generators. So it's dual string generators. So if we lose one, it's still safe, and it's super instrumented, every shock and every acceleration and now the temperature all the time. And on the side of it is a stencil that says space flight hardware do not drop. And I had exactly that reaction. I'm like, oh, that is ridiculous. Who put that on there? And then later I discovered it is possible to drop it. We didn't drop it, but I'll show you where. This is me and Henry Stone, our project manager at JPL, when the beautiful spacecraft bus came down from the Bay Area to Jet Propulsion Laboratory in Pasadena to begin to be integrated with the software and all the science instruments. Very great day. This is the Deep Space Optical Comm team the day they installed, and it's that silver thing over their heads that hangs out the side of the spacecraft. And this is just a hero shot. And you can see how big it is with the people next to it, especially when they're at the same distance from the camera like it is here. Everything in red is removed before flight. Those are covers, I believe, on the nitrogen gas tanks for the cold gas thrusters. And one thing they've set up down at the Cape is a pegboard with the outlines and the names of everything that has to come off the spacecraft, so you can see at a glance, is the pegboard now filled? Have we forgotten anything? And a lot of us have those removed before flight tags sort of as souvenirs, but then we worry about it in real life. This is me in Denmark holding the flight spare magnetometer. So this is a beautiful instrument they make at Danish Technical University to detect the magnetic field. It gives you a sense of scale. Oh yeah, there it is. Forgot to put that on. Here they are installed in that gradiometer configuration. And then this is the gamma ray spectrometer at the end, and the neutron spectrometer is partway down the beam. This is from Johns Hopkins University Applied Physics Laboratory. And that gamma ray spectrometer at the end, again, this is a moment where I get very excited from a tech point of view. How do you know the atomic composition of an asteroid from orbit? No sample, no laser. It's because our galaxy gives us intergalactic cosmic rays. These high energy things, which I'm sure you all are aware of because they do interfere with radio, don't they? Yes, no, maybe. And we're shaded from them mostly by our atmosphere, but Psyche is naked, so it gets struck by these cosmic rays, and the individual atoms that get struck are energized, and then when they lose that and release that energy, they give off a gamma ray. And the frequency of the gamma ray is indicative of the type of atom it was. And so we're going to collect those gamma rays in a scintillator crystal in that gamma ray neutron spectrometer. What is this scintillator crystal, you might ask? It's about the size of a football. It's bright green like krypton, and it's pure germanium. I'm told it's the purest material made by humans, and it's pretty awe-inspiring. So that is a crazy, fabulous instrument we're very excited about. All right, these are the Hall effect thrusters. Ion thrusters have been used outside of Earth-Moon orbit before, but never Hall effect, which is the next step up from ion thrusters using a more complex magnetic field for accelerating. So for those of you who do not know how this works, we're going to fly over 1,000 kilograms of xenon, the noble gas xenon, and every xenon atom will get ionized in an electric field from the power from the solar panels, and then accelerated through this electromagnetic spin of the Hall effect thrusters and released out the back of the thruster. And it's that momentum transfer that moves the spacecraft. Extremely efficient, way more than 90% efficient, much more efficient than any other way, but very, very low thrust. So you thrust all the time. You start out really, really slow and you end up really, really fast. So the highest speed we're going to reach relative to the Earth is when the spacecraft and the Earth are on opposite sides of the sun just before the Mars gravity assist. So that kind of helps with the relative speed. And it's 125,000 miles per hour, I believe. So it's very speedy. That's speedier than Voyager's ever gone. So there they are with their remove before flight caps on them. And they're on these articulated arms, and here they are installed. And this is what they look like when they're turned on in a thermal vacuum chamber. It turns out that ionized xenon is blue, and so it's going to be this beautiful blue ion trail. Being a sort of a chemistry person, I also calculated how many moles per kilometer we were going to use, which I forget at the moment, but it's a tiny fraction of a mole per kilometer to move this giant thing. Now, one of the things we have to test is we have to test for electromagnetic compatibility and interference of all the systems on the spacecraft. Hard to do. This is JPL's clean, they're very high bay, high ceilinged, high bay clean rooms. The whole thing is a clean room. And of course it's filled with electromagnetism of its own. And so you have to put it into a Faraday cage. So that is a Faraday cage for a spacecraft. It's made of conductive carbon fabric. And so we passed our environmental testing. Then you have to put it under space conditions, test as you fly. See the people for scale, the guy in green up on the balcony and the guy in the white lab coat at the bottom. And that's the bottom of our spacecraft going in. The yellow is the adapter ring that will connect to the rocket. And then that big door closes. That's JPL's big thermal vac chamber. It's 25 feet in diameter, and it gets evacuated to space vacuum and cooled to space temperatures using an endless parade of liquid nitrogen trucks coming up through the JPL gate for whatever it was, 10 days or something of our thermal testing. So we did well with our thermal testing. By the way, thermal testing is one of the things that in general deep space missions need more help with. It's very hard to make an accurate thermal model of a whole spacecraft. And so doing that thermal testing, getting some empirical knowledge is very important, but anyone who is very interested in finite element thermal models, that's a place where we need help. The spacecraft got flown to Kennedy on a C-17 transport plane. This is the moment where I thought you could drop it, couldn't you? Like, could you not make an entire ramp that filled the whole space? But we were fine. We did have another shipping container problem when the spacecraft was not in it. We ran our shipping, the trucking company ran our shipping container into a bridge. That was exciting. I'm happy to tell you that story too. So there it is. It fits just perfectly in a C-17. And in fact, we had to build our own shipping container because the one that Maxar would have lent us only fits in an Antonov, and the U.S. government does not give free Antonov flights. So, and we didn't want to ship it across Route 10 on a truck, which is the other option. When, okay, now I don't remember, it was Cassini or Galileo. When one of those two was shipped across Route 10 to Florida from JPL, when it arrived, there were bullet holes in the shipping container. So the spacecraft was fine, but I couldn't get that out of my head. I'm like, get it on a plane. I want it on a plane. So now the last couple of pictures, here it is at Astrotech down in Titusville, just outside of Kennedy Space Center across the river. It's all blanketed now and taped up. And one of the last things we did was reinstall the solar panels after they were fully tested up at Maxar. That's one panel. There are 5 panels that size on each side of the spacecraft, so that kind of helps with scale. And here it is, we are practicing the extension of one side. That's just the horizontal line of the plus that is our solar panels. But because they're only designed to deploy in zero gravity, they have to have special equipment to offload gravity in order to practice here on Earth. So you can offload it with that scaffolding above it for the plus, for the horizontal part of the plus, but for the 2 that go up and down, you need super special gravity unloading equipment that only Maxar has. But that also gives you a sense of the size of the spacecraft. And so there it is, hero picture from 2.5 weeks ago during Media Day, which was very, very fun. That's another of the fun things about these NASA things. And in fact, tomorrow we've got a big Media Day for L-30, which is going to be live streamed on everything that NASA uses in case you want to listen in. Me and 3 other really expert people on the engineering side are going to be on. And one of the things we do is we take selfies. This is Paige Arthur from our Assembly Test and Launch Ops team in Florida, looking through the window into the clean room there. The spacecraft has now moved to the hazardous processing facility because normally to fuel load a spacecraft, you need to be in a hazardous site, but xenon is not very hazardous and neither is nitrogen, but that's where the fuel loading occurs. There's no picture window there. And that is Luis in the middle, who's our ATLO deputy manager, and Henry Stone, the project manager. And we just take 1 million of these pictures. And so finally, that's me and Brian Bone, the ATLO manager, under the spacecraft, looking up at it. We've been degaussed and we've got all our degaussing wires on, looking at the comms panel. And so there we are on social media, and we also have got this great website. And I want to thank you again very much for listening and for the opportunity to come speak to you. And if there's time, I'm very happy to answer questions. Thanks a lot. There is time, I'm told. Yeah, go ahead. Can Webb see a better view of Psyche, he asks. So you guys are going to be running microphones, but in case we don't reach somebody, I will repeat. In fact, a wonderful young astronomer named Stephanie Jarmack, with me as a kind of a sub-advisor, because I'm not an observational astronomer, applied for Webb time, and we got it in cycle 1. And back in March, Webb looked at Psyche. But to the disappointment of many people, we did not look with cameras. We looked with the mid-infrared spectrometer. We were trying to understand more about the chemistry of the surface. And so I think we could see better pictures of Psyche potentially, but probably still not good enough to really help us, because if you think about the challenge of the gravity field to calculate a stable orbit, first of all, imagine that we have this sort of potato-shaped thing. And imagine, this is an extreme case, all one end is metal at 7,000 kilograms per cubic meter, and all the other end is void space and rock, which could be less than 3,000 kilograms per cubic meter. That's going to be a pretty confusing gravity field, and that's not something Webb could tell. So it's not a super high priority for us. We'll get great pictures in time. Other questions? Oh, do we have the microphones out already, or here comes a microphone for you?
We have a question right here.
Right, wave your hand. Where are you?
Right here.
Thank you so much.
Pardon if I missed this, but how many newtons of thrust does that ion thruster produce?
I know. I should have looked up the number, of course. There's so many numbers to memorize for a crowd like this. I've been told it's like holding a coin in your hand. So it's very small. It's a little fraction. I don't remember what it is, though. Sorry. Yeah.
No problem. Thank you.
Right here.
At the beginning of your talk, you mentioned how inconspicuous Psyche was. So what attracted your attention to it? What made it stick out?
So what made it stick out? We had written, I and my colleagues at MIT, when I was on faculty there before I left for a directorship elsewhere, Ben Weiss and Maria Zuber and I wrote a paper about the formation of planetesimals and core differentiation in planetesimals. And then I got an email from a couple scientists at JPL saying, we loved your paper, would you like to propose a mission to test your hypothesis? Which is, do you guys all remember in Ghostbusters where the one guy says, if someone asks you if you're a god, you say yes? And so I felt like when someone from JPL asks you if you want to propose a space mission, you say yes. And so we started investigating, and the best place we could find in the whole solar system to go look at a metal core was this asteroid Psyche. So that's why we chose Psyche, and we have this little tagline that going to Psyche is going to outer space to investigate inner space, because we are never ever going to look at our own core. So that's why Psyche.
What's your power budget as you're at Psyche?
Yeah, well, what's our power budget? So we're 20,000 kilowatts at Earth, and say Psyche's at 3.2, so you've got a 1/r² relationship, so it's about 2 kilowatts at Psyche, and that does everything. That does comms and the science instruments and the thermal and everything, and propulsion. Yep.
Over here. I don't know if you heard Derek talk about the efforts at the Allen Telescope Array. I was wondering if you have efforts so he was talking about how citizens and students can get involved in radio astronomy.
Yeah, I love it.
And I was wondering if you have any, special activities to involve like undergraduate or graduate students in the Psyche mission. So, we can have young people get involved in space missions at an early age.
Yeah, well, we have that huge student collaboration, those 4 different things that I only talked about, capstones and the art project, and there are 2 others. So in 7 years, we've had 1,500 students get involved. For students to actually do observations, they really need to be working directly with a co-I or a different PI who is doing the observations themselves. And so that's not part of our Psyche student collaborations program, but I know students are involved in that. And one of the things we're trying to do encourage that kind of thing is we're actually developing new NASA policies for the mission to bring on junior scientists faster, and also to make the rule that they don't have to be at the same institution as an existing co-investigator, which is a rule that has really limited the ability for junior scientists to get involved. We also don't believe that we have a science team and an engineering team. We have only one team. Because the truth is that you need the budgeters and the schedulers, and you need the artists, and you need the media people, and you need all the engineers and all the scientists to make it work. So the more we work together and talk together, the better. So we try to make lots of opportunities for students to be involved as much as we can.
I understand this is not the most exciting part to you for the mission, but could you give an estimate of the bit rate that you would get out of the optical link at which distance?
Oh my gosh. So I think that under the absolute worst conditions that we're anticipating, it would be 10 bits per second. And we're still kind of we're working through to make sure that we can get that would be like safe mode and everything's kind of broken. So we hope we never find that out, but trying to make sure that we can actually get enough information about the spacecraft under those conditions that we could actually diagnose. And I don't have in mind, and this is obvious one I should have looked up, what our standard bit rate would be. But that's not secret information. I just didn't memorize it. Sorry.
Okay, thank you.
You talked about the communication issues that you had with the GNC team and bringing that up kind of the chain. Do you feel like that was addressed? And can you talk more about how you were able to address that?
Yeah, so one of the things that happens when the leadership, has suddenly become convinced that you're not going to make a launch date, a planetary launch date, where there is not the option to launch to that planet necessarily even every year because of its relationship to the Earth around the sun, what happens is a gigantic series of enraged and crisis-ridden meetings. And NASA immediately convened an internal review board, by which they mean an external review board. So they brought in like the heavyweights of NASA review, including Tom Young, who was on the James Webb Review Board, which is only 20 times larger mission than us. $1 billion is considered kind of a small mission, but they brought in all the heavyweights, and we started to go through a super intensive review process, the end of which is a meeting called the Continuation Termination Review, where you go and present at NASA headquarters for 4 hours. And at the end, they go around the 90 people who were there in NASA leadership, and they say, continue or terminate, continue or terminate. And so I'm telling you this background because everyone voted continue, which was great. And the board really helped us understand better all the reasons why we got to that situation. And they wrote a report, which is freely available on the web. It's on a press release on the NASA website, and you can download it and read it. It's not redacted. It's the full thing. And I think they got it exactly right. And it talks about many, many of the things we did to try to fix that right away. One of the things was we were already having all team meetings twice a week to keep everybody on the same page and try to stop people from panicking, because you have to pull people back from where they were. Oh my gosh. I mean, we all know how we felt during the height of COVID. We're in existential fear all the time. We or people we love are sick. And these are people who are just determined to get to the launch date for us because of all the things that rest upon it. And they're missing their kids' soccer games or whatever it is. And then you have to tell them, okay, we have to scale back, but not stop. We're supposed to keep working on the spacecraft, and we have to kind of cheer you up, but in a few months, we'll find out if we're canceled or continued, and then we have to do this incredibly hard thing for another year. Like, that's a real morale issue. So we did a tremendous amount of work on morale, and then a lot of one-on-one talking with people. We did so many things, but I'll just say specifically, one thing is people who've been through an enraging circumstance where they felt impotent in the face of the machine, which is what happened to these people who are trying to say we're not going to make it. They need to unload those emotions in a space where it doesn't contaminate the rest of the team. And they probably need to be heard more than once. And you need to have all team meetings where people talk together. And so there are all kinds of these sort of social things that we were doing to help people be heard. And then everyone was involved in trying to do a better process. And of course, nobody wasn't trying their best. Everyone was trying their best. It's kind of a human, natural thing to, when you play telephone with bad news, to kind of downplay the adjectives. You know, your tone isn't as intense. So by the time the words got up to us, it just doesn't sound as serious. And everyone said they're going to catch up. I mean, it's harder. We just spent like 10 hours talking about 2 number 8 screws that fell out of a waveguide, because it's so much easier to talk about number 8 screws than it is guidance, navigation, and control software. And so we had all those problems of how do you articulate it. It's a tiny bit of the story. Yeah.
Well, thank you very much. We are at the beginning of the break, and so I do want to thank you very much. So yes, we have a 15-minute break. And I hope that there will be an opportunity to continue the conversations. I certainly have a question that I didn't get to. So food, a little bit of food, a little bit of drink is down the hallway and around the corner in alumni, the exhibit hall. There'll be a whole procession of people, so please do follow that. 15 minutes, we'll be back here at 11 o'clock to start on the first of our regularly programmed talks. Thank you very much.
Oh, sorry, I haven't plugged in yet.
talks now, and we've got 2 talks and then lunchtime and lots more good stuff to come. Our first speaker is going to be Mark Lichtman, who's a member of the board and the GA for GNU Radio. And the project he's going to be talking about is IQ Engine. I'll just read the first line of this here to avoid giving his whole talk. The IQ Engine is a free and open source web-based toolkit for analyzing, processing, and sharing RF recordings, which is really useful. And it's also built on SIGMF. So here is Mark Lichtman.
Hey everyone. I'm Mark, and I'll be talking about IQ Engine. I wanted to first thank all contributors of the open source project, as well as anyone who's contributed recordings, as well as the Coherent folks. So IQ Engine is an open source project that aligns really nicely with GNU Radio and SIGMF, as you'll see. It started about a year ago. I actually presented a prototype of it at last GRCon as part of a lightning talk. And quite a lot of work has been done over the last year. So I'll be showing a bunch of features, demoing the current state of the tool, and then talking about the next steps. So to jump right in here, what is it? Well, it's a web-based tool designed around RF recordings. So that includes management, analyzing, light processing, as well as sharing RF recordings, all in your browser. Now I'm going to try to do a live demo, even though I recorded one just for fun. So IQ Engine is available, like it's public at iqengine.org. The landing page has a little bit of information about the tool, but the main, first page is here. So these first 3 tiles represent repositories of RF recordings available online. GNU Radio hosts a bunch of example SIGMF recordings. There's also some from Daniel Estevez and Northeastern. But you can also open your own local recordings using this tool or a local directory of recordings. And currently they have to be in the SIGMF format, which is not a tough format to adopt. If you want to learn more about SIGMF, there's kind of an introduction here. And we're also hosting a SIGMF workshop. I believe it's tomorrow, if you want to learn more. And if you have your own cloud storage, you can connect to it directly. But I'm going to dive into the GNU Radio examples. So within each repository, you have the list of recordings available, with any folders used to categorize. Spectrogram thumbnails, I'll zoom in here so it's easier to read. And the core SIGMF information like data type, center frequency, sample rate, the number of annotations. You can actually click on that to show the list of annotations and a breakdown of each one. So this is pretty useful if you're doing RFML work. Going into one of these recordings, we view the spectrogram page. So this shows, as you can imagine, kind of a zoomed in spectrogram at the beginning of the recording. But then on the right, we have the minimap inspired by VS Code, which represents the entire recording. So you can jump to a different part. And what it does is download the IQ samples you're looking at only to the client. And then all the FFTs and such are done client side. That's how we can also open local recordings, all client side. Now, you can see the SIGMF annotations show up as bounding boxes, which are editable. And you can enable time cursors, frequency cursors. The frequency cursors let you do baseband and RF units based on the center frequency the recording was taken at. Time, frequency, and IQ plots. Close Discord so it keeps... Currently, the time, frequency, and IQ plots show whatever portion of the recording you have displayed on the spectrogram tab. On the spectrogram tab, we have adjustable color maps, and you can adjust the dynamic range of how the magnitudes are mapped to the color map if you have like low SNR signals. There's an FIR filter that runs before the FFTs are taken. So we have some example filter taps, like being able to filter out everything but the center half. And once again, this is all client-side processing. Or you could just type in your filter taps, either real or complex. Let me go back to no filter. Adjustable window, FFT size. And then one experimental feature over here is this Python snippet. This is a portion of Python code that runs in the browser using an open source project called Pyodide. And the idea is whatever X is at the end of this snippet is what the what will be displayed. So right now it might be hard to read, but it says X equals X times 1. So it's not doing anything. But if I square it, and then actually it takes a few seconds for Pyodide to initialize at first. But once it's initialized, it's like maybe 5 times slower than native Python, which isn't bad, honestly, for the browser. I've been pretty happy with it. So let me do X times 10. And you can see the magnitudes are higher. I'll try X squared. So if it was a single carrier signal, you could use that to find the offset frequency, for example. Just a quick way to dabble around in Python. You have NumPy, SciPy, and basic Python available to you. At the bottom, we have the global SIGMF information as well as a list of the annotations. You can jump to a specific annotation by clicking this button, and it'll jump to whatever portion of the recording had that annotation and fetch the samples. Zooming in, or zooming out rather, is currently done by doing batch decimation. So it obviously needs to download way more when you zoom out, but we have a system where it only downloads, a fraction of the FFTs. Of course, the Wi-Fi here is pretty slow. So far, it's been able to keep up surprisingly well. Yeah, that's why I saved it for last. Okay, so now that you saw kind of the basics of the tool, I'll run through a little bit more about the tool. So for the sake of context, what I showed you was the public instance of the tool at iqengine.org. You can open local files with it, so there's really no reason to clone and run it yourself in most cases. Unless you were, for example, wanting to run it privately within your organization and share recordings, within the org. Or if you have really sensitive data and you can't just take my word for it that the data is kept client side, you could run your own instance through the Docker images that we build. If you're a developer of the tool, you'll want to actually run it from source. And that's really the only instance, I'd say, where it's worth running from source. I think a lot of us are used to finding a new SDR-oriented project and cloning it and figuring out how to install it. Well, in this case, there's no need. So iQengine's built on top of SIGMF, like I mentioned. SIGMF, we'll go over it more at the workshop, but it's an open standard for saving RF recordings to disk. And that's in contrast to sending RF, digitized RF over the wire, like with Vita 49. So iQengine involves having a binary IQ file and a JSON file. And at a minimum, you're going to want to store the sample rate, center frequency, data type. That way you can avoid bit rot and you can have compatibility with tooling like GNU Radio and iQengine that supports SIGMF. Like I mentioned, there's that link on iQengine, and then we have the workshop. So the target users of iQengine are pretty similar to that of GNU Radio, where both individuals and organizations could get value from it. And we're trying to keep it very education oriented, as you saw with some of the features. It could be used for research-oriented work or alongside production systems. So if you're a spectrum sensing group, you're making a lot of recordings, you could use iQengine to manage those recordings, query them, display them, even run processing on them. Now, one of the newer features of iQengine is the plugins. So everything I showed you so far represented client-side processing done in your browser on your computer. But plugins allow a way to run back-end signal processing triggered from the browser. So the back-end server running plugins is separate from the rest of the iQengine, back-end and front-end. And you can actually have multiple backend servers connected to one instance of IQ Engine. In fact, a third party could run a backend server, like a company could show off their RF capabilities. It doesn't even have to be open source. And we could connect the main IQengine.org to that server so that anyone can try out the functionality. Now our API interface is defined with an open API spec that sort of represents a way to send IQ samples and parameters and then get various returns like more IQ or detection bounding boxes, that kind of thing. But this means that plugins can be written in any language, although the project only has examples and templates for Python and GNU Radio right now. So here's a quick demo of running a plugin. So I'm going to go to this synthetic signal here that has a few different signals within it. I enable time cursors, which lets me choose the portion of the recording I want to send to the plugin. And then at the bottom left here, it might be hard to see, represents the plugin's interface. I guess I can just show this live. So if this refreshes here. Yeah. Anyway, so right now we only have one plugin server attached. It's kind of like the canonical server. But I'm going to show a detection plugin running. So you can see there the results are shown as SIGMF annotations or these black bounding boxes immediately. So you can immediately see how well like a detector worked. But there's other forms of plugins. So switching over to a recording that includes analog signals, select the portion you want to send to the plugin since it's running at the back end. And then I'm going to run an FM signal detector. It's not hard to detect FM. We know where it is. And then I'm going to run an FM demodulator on the middle signal. So what gets returned is actually a WAV file that the browser then downloads. Although I don't have audio, it's a very small snippet of IQ, so it's like a few milliseconds of audio. Now, the last type of return from the plugins is more IQ samples. So I'm going to run a low-pass filter plugin now, where you specify the cutoff and the width and the number of taps. And currently what IQ Engine does is it displays the returned IQ samples in this pop-up, where we can see the spectrogram, time, frequency, IQ. But in the future, we plan a way for you to say whether or not you want to make the returned IQ samples what you're now viewing in the main tool here. So that's the gist of the plugins. Writing a Python plugin is extremely simple because we already wrote the server part that deals with the open API interface. So here's an example of a Python plugin that runs a low-pass filter. Now, every plugin gets the sample rate and the center frequency automatically, but you have to specify the custom parameters you want. And we're using a Pydantic's data class decorator to automatically grab a schema of these custom parameters. That way the front end knows the parameters and the types and everything. So these three are custom to this plugin. And we use NumPy's Furwin and Convolve to actually perform the filtering. Lastly, the return is using this object here. We're currently base64 encoding the return samples, which is a little inefficient, but it gets the job done for now. So yeah, I mean, if you wanted to make a Python, turn Python DSP into a plugin that you could run from the browser, it's extremely simple. And there's going to be a workshop on Thursday where we're going to do a hands-on tutorial. We'll show how to run a development server locally and how to make your own plugin. Now on the GNU Radio side, it's a little hacky, the current way we do things, but it works with existing GNU Radio blocks, which was the important part. So we're using ZMQ's pub and sub to get samples from Python land into GNU Radio land. Some of you may have guessed that's what we would do. So as a quick example, here's a Python GNU Radio flow graph. It's a low-pass filter, and it includes a ZMQ sub source for getting samples into GNU Radio, and then a pub sync for getting them back out. Now, as far as the plugin side of code, we create a corresponding pub and sub socket in Python. So we make the pub, we start the flow graph, set up the sub, and then we send the samples to the flow graph. This is a really common scheme. In fact, we have a tutorial, GNU Radio has a tutorial doing the same exact thing, essentially, where you get the samples back into Python, and then we return them to the client just like we did before. So you can imagine that plugins can be chained, right? If a lot of plugins return IQ and take an IQ, then you could certainly chain them together. And that's where this idea of pipelines comes in. So the browser interface that I showed you, it currently lets you evaluate a plugin, tweak the parameters. You can play around with other people's work, but you can't create a plugin in the browser. You have to have it already created, whether that's in GRC or in Python. And then you would wrap it into a plugin to allow others to evaluate it. Well, so what we're planning to do, it's not done yet, is to find an existing format for designing pipelines. It's kind of like GRC, where you connect blocks together, except it's a little more like combining flow graphs together. And ideally, we would want this design software to be web-based, so that you could actually design the pipeline in the browser and then run it. Now, as far as actually executing the pipeline, it would be on a Kubernetes cluster, which would either be set up to listen for more recordings to show up in a storage account, or to be provided over the same REST interface I showed earlier. So this pipeline thing is obviously more tailored towards organizations than individuals, but I figured I would mention it. And if anyone, either org or individual, is interested in sort of working with the project to make this happen, definitely let us know. So for you RFML folks out there, I figured I'd point out where IQ Engine fits into the workflow. It might be kind of obvious, but at the beginning of the workflow, if your data set is based on a bunch of SIGMF recordings, you can use IQ Engine to manage those recordings. Look at, if you're performing detection, you might have labels using SIGMF annotations. So you could sort of review your data, add annotations. And then the other place it comes in is at the end. Once you've done training, once you have a successful model and you run the model via inference so that it can be used, you could wrap it into a plugin so that you can share your work with the world if you want to, using IQ Engine. So it's a way to share, but inversely, it's a way to sort of bring the SDR community together so that it's easier to find other people's work, right? Speaking of communities, so we have a Discord server. A big thanks to Jumbotron for moderating the server and helping configure it. And then if you're not into Discord, you can always use the GitHub system, like making an issue for either a feature request or just an idea. And then here's a quick snapshot of our Google Analytics. So we have Google Analytics running on iqengine.org, but it's configured to only grab the minimal information. We wanted to make sure there was no way it could get information like, for example, a file name of a local recording that someone was analyzing, right? That must be kept private. But we're currently at 8,000 unique visitors over the last few months across the globe. By the way, there's a link to the Discord in the top right if you're on iqengine.org. The code is organized with a big mono repo. Even the plugins are part of the same repo. Now, the front end and back end are kind of shipped together in the same Docker image, so we can control versions a little more easily. But the plugins are packaged up separately. And the plugins container includes GNU Radio, as you can imagine. And in the future, we're going to be including other open source software that we can wrap as a plugin. But someone could also sort of fork our Docker recipe and add their own dependencies if they wanted to wrap something else. Documentation lives as MDX files. And these are a pretty convenient way to do documentation. The actual source code looks like Markdown, but it can be rendered as React components. So that way we can render the documentation in the website itself without it looking ugly in the source code. So our front end uses React. The back end is all in Python and Fast API. And then we use Tailwind for CSS. And there's a few more details about the code organization in this diagram. The CI/CD I'll briefly mention. So even though it's a very young project, we spent a lot of time early on trying to get as mature CI/CD as possible. So we have staging.iqengine.org, which is a deployment that always represents the latest main code, which is really nice. If you're a contributor and you get your feature merged in, you can immediately see it. And then every few weeks, we release a tag. We release a major revision to prod. We got a bunch of unit and integration tests. We're using Playwright for the integration tests. It's been working out pretty well. Sort of the GitHub actions that you would expect to see. Now, some upcoming features that I'll point out a few of these. So right now, you can either open local recordings in the client, or you can view recordings stored in the cloud with these under these storage accounts that I showed. But what we want to do is add a way for someone to have like a local storage server or a NAS and be able to run the backend and have it serve those recordings. So this would be useful for an organization who wants to keep everything private. The next thing that we're planning to wrap into a plugin is SatDump. So if you're interested in satellite signals at all, I would highly recommend this awesome open source software by Aang on GitHub. And he has a whole community on Matrix around it. So he has several different satellite receivers implemented. And the plan is to have each of these receivers show up as a plugin in the IQ Engine interface. Longer term, the time, frequency, and IQ plots are very simple right now. They're really just using Plotly. So sort of beefing them up and adding features there is a big one. Ways you can contribute if you're interested. So there's obviously the code contribution part, being involved in the development of the project. But if you're not able to do that, you could contribute RF recordings that have been approved for public release or that you've individually created. Or you can contribute plugins, which is really just any open source signal processing. And then I didn't show the SIGGEN tool, but if you have any Python-based transmitter code, in fact, I could show it off real quickly here. This is more education-oriented. This SignalGen tool is kind of like a little playground for folks. We have example signals here. There's OFDM, DSS, BPSK. And then the idea is you run this Python all in the browser. And it kind of acts as a starting point for someone getting into signal processing. So we have the time, frequency, spectrogram plots, and then the code to generate them here. And everything's editable. Once again, we're using the PyODide project to do this and the CodeMirror project for the actual editor. So yeah, so I'm hoping that in like a year from now, there'll be several examples of Python transmitters listed here. I think this will be a nice kind of central place to share, mainly for education, and to sort of act as a starting point for research. Now, so we're also looking for universities and organizations to engage with to try to figure out if the features we have on the top of our mind, align with what folks want. Because in the end, this is an open source community-driven project. It's not under any specific organization. So if you want to chat, reach out on Discord, or you can email iqengine@vt.edu, or reach out to me. One last quick thing I wanted to show off if we've got it working here. So I didn't show off querying. We have a basic query system which lets you search over frequency, date, etc., what you'd expect. But more recently, Gabriel, who's done a lot of work, added OpenAI integration. So you can type like recordings that contain LTE. And you can see here, it really just contained LTE in the description or the title. In fact, you can look at the query parameters, but you can do some other fun stuff like recordings in X-band taken within Central Park on Labor Day of 2020. So this uses the GPT models, which don't go past 2021. Now, there are no recordings that fit that, that query, obviously, but we can look at the query parameters that were generated from it. And you can see the frequency range, X-band, date, time, I assume that's Labor Day, and then the GeoJSON polygon that I would imagine represents Central Park if the GPT models are working. So, you know, if you're a big, like a spectrum sensing group or whatnot, you can imagine the value of having that kind of query at your disposal. And yeah, that's it. So if you want to, you know, support the project, the simplest thing you can do is star us on GitHub. That's one way. But with that, I'll go ahead and take any questions. I think we have a few minutes before Martin's talk.
Thanks, Mark. That seems really interesting. Any questions from the audience? Over here. Anybody knows where a second microphone is? We can do this fast.
So is this the second one?
So this is super cool. I would have wished to have had this many years ago. I was learning all this stuff. When you are selecting things, can you select for frequency and time? I don't know if, I think your examples were, I was looking at a spectrogram, but it sounded like you were saying time domain samples. Like, could you also just isolate like chunks of the spectrum and send it off?
So right now, the time cursor is kind of used doubly for deciding which samples are sent to the plugins. And that's really just deciding which like portion of the recording. So there's no like tune, filter, decimate, but that is part of in the roadmap to have a way to specify a bounding box. It could be an annotation or it could be the selection cursors, and then say, hey, I want to download this. Can you do a filter, a tune, filter, decimate to zoom in frequency, crop in time, and give me the resulting SIGMF recording? That's one of the near.
That'd be awesome.
Yeah, I'll make sure that happens.
Thank you.
Here's the other one.
More questions? Okay, I don't see any more questions. Thank you to Mark. And by the way, Mark's also the author of PySDR.org. And so that's another
Thanks for
really
the plug. Yeah, if you want to learn more about DSP using Python, check out PySDR.org. Free online textbook.
All right, now a very familiar speaker. Everybody always waits for the latest Edis hardware to be announced. This is a sponsored talk from Martin Brown, and he's promised me if I introduce him really quickly, he'll give me a free X440. Is that still on? Okay, here's Martin Brown from Edis National Instruments.
All right. I don't have a laptop or anything. There we go. How do I, oh, this is the clicker, there we go. Is this, how do I advance? Is this how it works? Perfect. Cool. All right, so yeah, I was introduced earlier as part of the board of GNU Radio, but I actually also work for a company called NI, and we've been sponsoring this conference for a long time, which I'm very, very happy about. So they pay me to fly here and of course talk about our products, which I'm also, also proud of. And this is the USRP X440, our latest, and I don't want to say, yeah, I can say the latest and greatest in the USRP product line. Not that the others aren't so great, but I'll be talking about this for a few minutes. So yeah, just to be clear, this is not me speaking in a GNU Radio capacity. This is me speaking in an NI capacity, and this is our sponsor talk. So I will use this time to brag about our product line. Okay, the X440, let's look at some stats. What can it do? What's so special about it? Sort of the general tagline for the USRP X440 is like just more and better. And what do we have more of, and what is it better than? And if you look at the number of channels, you can see it has 8 channels, TX, RX. Or you can do full duplex, or you can do half duplex over a single port, the same as you were able to do with any other USRP in the past. So we have a lot more channels, that's number one. And of course, very interestingly, so each of these channels can handle up to 500 megasamples or like a 400 megahertz of analog instantaneous bandwidth. If you are okay with not using all 8 channels at a time, you can go up to 2000 megasamples or 1.6 gigahertz of instantaneous bandwidth per channel. which makes this very useful. And this sort of unlocks new capabilities that you couldn't do with an X410, for example, or even an X310. The one thing that might stand out a little bit is the frequency ranges actually drop compared to other devices. So 30 to 4 gigahertz, what's that about? And the answer is we've simplified the RF section in this device intentionally to make this a device that is primarily to be used as an IF device. So, all the other USERPs you could effectively put an antenna directly on and they would be useful. Like they would have like reasonable output power and, filtering and whatnot. If you wanted to go fancy, you could connect a RF conditioning device like the SE2430 to the X410, but the X410 by itself is a useful device for transmitting and receiving directly. But there are many use cases where you need some kind of specialized RF hardware, and then this comes in handy because this sort of offloads the RF conditioning problem outside of the box, which is how we were able to fit all those channels in. I'll talk about that a bit more in a sec. Quickly mention some other stats. In almost all other respects, this is the same hardware than that the USRP X410 already had. So it even uses kind of the same, like the box looks very similar. It has an RF SoC, the same one as the X410. The only difference is that we are using a speed grade 2 device here. Other than that, you have the same interfaces and the same interfaces that you can sort of use for sort of the digital connections. If we look at the front, you can see, well, a bunch of connectors. Unsurprisingly, we have 8 channels to handle. So that means a lot of connectors. We couldn't actually fit 8 SMAs per daughter board. So these are MMPX connectors. So if you might need some adapter cables for your existing RF. But other than that, you just have a whole bunch of RF coming in and out of this device. And if we flip it around and look at the back side, it looks exactly like an X410. So I don't need to talk about this in all great depth. Just to reiterate that we do have the same 2 times 100 gigabit Ethernet connections. You can also do 10 gigabit, of course. Synchronization, PPS, 10 megahertz, etc. And the same digital interfaces, USB. And of course, you have 1 gigabit Ethernet, which can come in very handy for management. You can also stream over that 1 gigabit Ethernet interface, but not very quickly. Remember, this is a 2 gigahertz, a 2 gigasample device per channel, so you're not going to do that over that 1 gigabit Ethernet connection. If we put it side by side with the X410, you'll see all the things I just mentioned. We have more channels, we have more bandwidth. We have a different frequency range because this is supposed to be used for sort of IF applications. And if you look at the other interfaces, it's pretty much the same. It supports UHD, RF-NOC, and through that, it of course supports GNU Radio. We're hoping to see some more software support by other software vendors in the future. But we think that this device will actually be used in different applications than the USRP X410. So we didn't just want to upgrade the X410, we actually wanted to build a different device for different reasons, and that's what we did. So one thing, sort of just to sort of wrap up the stats section of this device, if you look at the block diagram of this device, on the motherboard side, unsurprisingly, it looks like the X410 because it is using the same motherboard as I mentioned before. On the daughterboard side, it's much simpler though than the USRP X410 because we are now removing that that RF circuitry to fit all those channels, which means basically all we have are some balance there to actually connect the front panel connectors to the high-speed converters. There we go. And the main and sort of key feature that we're providing with this device is access to hundreds of sampling rates. So this comes in, very handy. Now the RF SoC is a good IC that we've been using, but it is complicated to program. So there's a lot of stuff that you need to know. And here's a screenshot from our manual that sort of grew in complexity as we were adding to it. You can see up to 5 PLLs on here, and that's hiding the fact that some of these are dual PLLs and others are 1 PLL per channel. So there's lots and lots of stuff that you have to program on this device if you want to actually sample at like variable sampling rates. And we sort of try and take all of that away and sort of fold that neatly into UHD. So you can just request a sampling rate like you could with any other device in the past. And you would get that. So we go all the way down to 125 megasamples on the low end. Of course, you can do further processing and get it further down if that's what you need. But what we can actually natively produce from the converter goes down to 125 megasamples and up to 2048 megasamples. And then there's like all sorts of rates in between. Multiples of 100 megahertz. We have the various 5G rates available. And for the most part, you can just ask for a rate, and UHD will figure out what to do and give you that rate. Now, what do you actually do with an X440? Of course, we'll see next year what people have been doing with X440s, because it's not like this is still very new. We were actually glad to have something to show for this GRCon, so it's not a lot of people been using it so far. But we have a couple of ideas, and the fact that you have 8 channels that can phase coherently produce and consume data makes it an option for doing direction finding. Now, if you have to move out of the 30 to 4 gigahertz frequency range, then you would connect your external up and down converter. You definitely want to have some filtering, but there you go. You have 8 channels in one device, like 1/2 RU space that you can use. And of course, you can combine 2 of them, then you would have 16 channels and so on for building, setting up a uniform linear array or something like that for direction finding purposes. So that's an obvious application. If you're running a satellite ground station, then we can't tell you anything about RF conditioning and filtering. You probably know more about that than we do, and you probably already have it set up in your satellite ground station. So the fact that the device itself doesn't have all this, like 5G compliant filtering is not really a downside for you. And then, this is a natural fit because, again, you have a lot of channels in a small rack space. If you're working on radar, you want the high bandwidth, and that's where we've actually unlocked something new, going from like previously 500 megasamples per channel to 2000 or 2 gigasamples per channel. So that does unlock new applications. Of course, you need some powerful signal processing on the side, and you probably, or in almost all cases, want to have some external RF up and down conversion, filtering, etc., like I mentioned before. But this is definitely something that that unlocks new applications. Now, you could also do some. There's supposed to be an animation in there. I don't know if this is the PDF or the PowerPoint. Okay, I'm just going to have to assume that the animations aren't working. They are hiding like some of the boxes though. What it says on the left-hand side under the green pentagon is wireless comm software stack. So this is the idea that you might be running some kind of 5G, 6G software stack. And on the right-hand side, you could be using an FR2 up and down converter for millimeter wave. Now, why would you do that with an X440, not with an X410? Where the X410 is the device that we typically advertise as useful for, these kinds of applications like wireless comms research, is because these external up and down converters make it a perfect match for this IF-based receiver. So there's a company called TMY Tech which sells up and down converters. They also have like beamforming antennas that you can connect. And we actually have some at our booth, so you can come and take a look at them. But there's also other companies that sell these devices that you can match nicely with an X440. And now pretend that these green pentagons are magically moving onto the slide. What I wanted to point out here is that in all the example applications that I mentioned earlier, you always have 2 problems that you need to solve. You have plenty of problems, but there are 2 problems in particular that are common to all these applications, which is A, you want to stream data up and down from the device at a high rate, and you might want to facilitate accessing the external RF front end into your software. And we have solutions to both of those problems. So first of all, one thing that we've introduced a while back is the extension framework that we originally introduced for this device at the bottom, sort of right, the SC2430 signal conditioning device, which is built by a separate company than NI that we've partnered with called Signalcraft. And this extension framework allows you to connect an RF extension box to the device. It could be, well, it could have its own, Ethernet connection, but in this case, it actually uses the digital controls on the front end of an X410. And the idea is that you tell UHD what you're trying to do, as in, I'm trying to run an USRP in combination with this RF extension box, And then UHD will abstract away the RF extension and try and make both devices appear as a single device. So I don't know if you can actually read this from behind, but like in this GNU Radio dialog here, we add a device argument that says extension equals SC2430, and that'll prompt UHD to go find a binary plugin that'll then load. And if the RF front end changes the available frequency range or gain range or whatever, then the device will report like whatever that frequency or gain range is. And you can, so if you had a front end that went to millimeter wave and you say, okay, I need, I don't know, like 28 gigahertz or whatever center frequency, then it'll simply choose that center frequency for you, assuming that you have an appropriate plugin for this. And the other thing is the whole streaming problem. Now in the past, whenever you was streaming data from a USRP, like all the streaming data went through the same UHD session that also set up your frequency, your gains, and I don't know, antenna ports, whatever else you need to configure. And we've sort of changed UHD in the past, so you don't have to do that if you don't want to. If you think that you can handle the streaming better elsewhere and within your own software, and that's not unlikely because you know better what your application is, then you can have a UHD session, set up the USRPs, again, set the frequencies and everything else that you need, the sampling rate, whatever else, and then tell the device to stream its data to a remote processing node. And because this is all like built into RF-NOC and RF-NOC compatible, you can also build blocks into the FPGA that do some kind of pre-formatting of the sample data. And last year we had a guest slide from Microsoft where they actually showed how they built an RF-NOC block to generate Diffie-compliant VIDA49 packets that then came off the device and could be consumed by a VIDA49 compatible receiver. All right, I just mentioned RF-NOC. Who's familiar with who's heard of RF-NOC here in this room? Oh, that's a lot of hands. Wow, I think that might even be more than SIGMF. I'm gonna give myself a pat on the back for that. RF-NOC is our framework that lets you integrate custom IP into the FPGA of a USRP without having to modify UHD or anything else. Of course, you need to build a custom bit file, but the way that you integrate the custom IP is standardized. So, UHD will query the device for its capabilities, and it might say, oh, I have this custom RF-NOC block in there that's running some kind of custom IP, or it's an FFT or an FIR filter or whatever. And in the past, you could use RF-NOC with GNU Radio in a graphical fashion, but you would have to install an external separate out-of-tree module called GRCon23. And we've been slowly upstreaming all of that into GNU Radio now that we think that the API is appropriately stabilized. And the current GIUHD support for RF-NOC actually supports more blocks and options than the original GRCon23 did. So I highly recommend people to move over. Of course, you need the latest GNU Radio release to get all the features. But that's where we're sort of putting our attention these days. And one thing I want to point out is like Jeff, our MC, who just introduced me, was actually very helpful, giving us appropriate feedback on the whole upstreaming thing, because now we are moving our code into the common GNU Radio code base. And if RF-NOC and our blocks and our demos, there's one thing that stands out a little, which is phosphor, so you might have seen the GPU accelerated phosphor, which is really cool looking waterfall histogram display. And we have an RF-NOC version of that where the pre-processing is done in an FPGA, and it simply sends all the data over to the the host computer that is required to do the visualization. And that included a Qt based sync, which we have also put into GRCon23, and that was something that Jeff gave us more feedback on. And I'm going to give a little bit of a sort of a business secret away here. If you're a company in the SDR space, it helps to work closely with the GNU Radio maintainers. It'll make your life a lot easier. So I can highly recommend that. And thanks again to Jeff for helping us upstreaming that. So in the current version of GRCon23, you actually have sort of a standalone demo that shows how you can just put raw samples into that sync and then display them the way we do on the left. Still doesn't look as cool as the original GR Phosphor, but it is definitely nice to have. couple of other things that we've been working on, and this is just sort of I'm going to rattle off a short list of things that we've been working on in the last year. We've been working on FPGA usage for those people who are actually modifying FPGAs, for example, to integrate their own RF knock blocks. This was necessitated, there was public demand for that, but also like for the USRP X440, we really had to do this. In the past, if you built a custom design, you had the option to choose a bit width, which sort of gave you like a maximum available bandwidth. The maximum bit width that we support on our devices is 512 bits per bus. And if you want to do 100 gigabit Ethernet streaming, that's what you need, because otherwise you can't shift enough data over the available buses. Now, that's a lot of bits to route. And if you had a design like this with a crossbar, that automatically generated a whole bunch of routes that needed to be somehow placed and routed and put on the FPGA. It was very difficult to accommodate. So we've changed that so that you could, first of all, you can mix and match bus widths to a degree. So you can have like a 512-bit bus on your 100 gigabit Ethernet connection, but then use a lower bus rate elsewhere where you won't need the high bandwidths. And you can also leave out routes on the crossbar because that might be what your application actually needs. And that way you can save a whole bunch of resources and make building FPGA images easier. And we have like a bunch of other things on the FPGA side. This is not, most of this is like really sort of like in the details, so I'm not going to go through it in all that much detail. Maybe if you have questions, you can approach me about that. Like one fun little thing that we notice is if we produce data at line rate on a 10 gigabit Ethernet link, like so we send data from a USRP into a computer at line rate without any interruptions, back-to-back packets. NICs won't often be able, NICs as in network interface cards, won't always be able to keep up. So even if you have a reasonably powerful computer, the network interface might say, oh, I've been dropping packets left and right because I can't quite keep up with the data rate that's coming out. And this is nothing that we can catch with our flow control. So we put a little feature in that you can actually slow down USRPs. It seems a bit silly, but like for some applications, this is just really useful if you want to download a bunch of data from the DRAM. It's one of those little things that you run into and you're like, I guess I have to fix this now. And yeah, we did. And UHD 4.5 is not quite ready. It's not released yet, but like the release candidate is out, which means I have high faith that the team that is going to finalize that release will have that out in the near future. It has a bunch of features, but mostly the X440 support. Of course, we've been putting in a lot of bug fixes and, even just small things that I personally find are very important. Like you can compile UHD on many platforms, many compilers without any warnings, for example. I find those things to be important just as a metric of quality. And I'm very glad that we are able to sort of maintain that. All right, that wraps it up. Again, I'm very, very happy to be here, not just as a GNU Radio person, but also as representing NI, because this is an important conference for us. We are very happy to be here and very proud to be sponsoring, for so many years in a row. We have a booth in the coffee break area, which you've probably seen. You can talk to any one of us wearing like these green NI/Edis Research shirts. There's Hayden is at the booth. Neil is doing a workshop, I think today, on RF knock that you can visit. Talk to us about USRPs, and we hope we can help you with your various applications. All right, that's it from us. That's it from us. Thank you very much. I think I might have time for a question or two, but I also realize that it's time for lunch soon, so I will not be upset if you want to get some food. Well, again, thank you very much, and I hope to talk to you about USRPs.
All right, we do have time for a couple of questions, and we also have an announcement from Josh before we get going. We do appreciate all of the ongoing support from Edis Research and all the work Martin's done. We're not sure which Martin we like best, so we'll take both of them.
Thank you.
Anybody have a question other than can I have one? That's really easy. They just all want one.
That's excellent.
Okay.
Okay.
All right, Josh, you want to come on up? Where'd he go? Oh,
Okay.
there he is.
you want to announce the? Do you? No, you go ahead.
All right. Thanks again to Martin.
Thanks, Martin. So quick announcement, we do throughout the week have lightning talks. So there's a block in the morning and a block in the afternoon each day. So Wednesday, Thursday, and Friday. So if you have a project that you've been working on that maybe didn't become a full talk, but something you've been working on you want to share, sign up. We will send out a link with signups. We'll have a QR code out at the front desk later on. So keep that in mind. So if there's anything you'd like to share, 5-minute slots, just let us know. And I think Sam wants to add to this.
Yeah, so just to give you guys a feel, we will actually have a couple lightning talks very quickly this afternoon, and that's on the schedule to give you ideas. It's really informal. Did you have an idea? Did you want to say, hey, we want to get together and talk about this, and you can find me here at this time? That's kind of what they're for. They're 5 minutes. If you want slides, you'll have to do a little bit more coordination with us, and we can absolutely make that happen, but anything else people want to do. So just want to make sure you're aware, and we'll have the sign-up sheets out for you tomorrow to sign up for the rest of the week. Thank you. Are we going to lunch? Oh, and I will go ahead and say I think lunch is set up. I would take your times because it is a smaller room if you haven't been over there yet. But yeah, we will have enough food for everyone if you want to wait a little bit as the first rush goes through. So thank you all.
Could you do me a favor and close that door? That would be fantastic. Thank you. All right, and with that, are you guys ready? The AV guys, you give me a thumbs up. Okay, perfect. Well, then I'm very happy to introduce Christopher from University of Massachusetts in Boston, and he'll be talking about. It's a very long title. I'm just going to read it. Actually, I'm just going to say it's about optical wireless communications. And he's an undergraduate student, so I'll give him a quick round of applause, and then I'll hand you the mic. Thanks.
Okay. So hello everyone, my name is Christopher Onchekwa. I'm an undergraduate GRCon student at UMass Boston, and I'm here to present the design and implementation of a multi-node OWC testbed for centralized configuration and adaptation of system parameters using GNU Radio's XML RPC and ZenQ modules. So the work I'm presenting today is a combination of our past work we performed from the Air Force Research Lab for the Beyond 5G competition. And specifically, my role in the team was for the control and feedback research. Other members of the team performed the hardware characterization and the signal processing. And we're happy to announce that we were the first place team for the 2022 to 2023 Beyond 5G Student Challenge competition. And if anyone here is interested in participating in this competition, feel free to reach out to Tony Liza at the BBI. So I would highly recommend it, as it provides very good hands-on SRI tooling and very good extensive work on GNU Radio. So motivation and background, optical wireless communications. So we know that researchers are interested in OWC for the next SG. And we know that specifically researchers are looking for systems level research focus. And we know that experimental tools for system level research in OWC are needed. So why SDR for OWC? We know that SDR gives us the flexibility, the rapid prototyping, and the cost effectiveness. So you don't need to buy your traditional fixed function hardware black box. You can still simply configure your SDR tools and get ready and utilize them to your need. So why a multi-cell, multi-user testbed? So some of the key things we wanted to highlight was that it provides the scalability, it provides the programmability, it provides the ability for centralized control, it allows for automated testing, and specifically want to pay attention to the modularity, the realism, so transferring work done in the simulation domain into real-world application, and the reproducibility of findings during research. And we hope that in the future we can enable dynamic and adaptive technologies for real-world scenarios. So this is the project overview and architecture. So as part of working in the lab, we've established OWC, point-to-point OWC system. So we have, in this scenario, what you can see in the figure, we have a TXA and RX1. So in the lab before, we had a point-to-point connection. And over time, we expanded it to accommodate more endpoints. So we added a second RX2 with another X series USRP running GNU Radio as well. And we accommodated for another LED array, which is our TXP, which we use for modulating the data stream from GNU Radio. And what we want to enable with this testbed is that we want to be able to send modulated OFDM data streams over OWC, our OWC testbed. And we want to extend Pi work to enable for multi-cell, multi-user resource allocation. And another thing we've done to improve our testbed is that we've added a control network. So in this control network, we use the testbed controller, and we use Ethernet cabling to interlink all of the computers running GNU Radio to the network switch. And then we've added the ability for centralized control for automated data collection and research in dynamic and adaptive OWC networks. So background. So we know GNU Radio is a free and open source toolkit for OWC and RF communications. Specifically in our testbed, we use GROWC, which is a specialized extension within the GNU Radio framework for optical wireless communications. So it allows for out-of-tree blocks and allows for control and modulation of OWC systems. In addition, we employ Python scripting, and we know that Python is a compiler coding language that allows for powerful functionalities in conjunction in GNU Radio. In terms of the hardware we're using in our testbed, for our OWC front end, we're using the ETSIS X series USRP with LFTX and LFRX daughter boards. We have a photosensor we employ as part of our testbed, and we use a consumer off-the-shelf LED array. And one thing to point out is that LED array is modulated by the signals sent out by GNU Radio. And one of the benefits of the testbed is that the modularity allows for swapping between different auto-receive front ends. So now I'm going to go over the testbed architecture. So one thing to pay attention in this testbed architecture picture, that we employ a DC bias because we need to shift the AC signal from the USRP into the LED's linear range as we use the LEDs for the intensity modulation. And another thing we need to pay attention is that we perform optical conversion as we send the signals into the LED array, as you can see for the TX LED arrays in the photo. And from the receiving end, we use electrical conversion from the photosensor to USRPs into the RS flow graphs in GNU Radio. And then one thing we want to highlight is that remote control and feedback for a multi-node ODBC system is very useful. So one thing we need to pay attention to is that XML RPC is very useful for parameter control. We know that XML RPC enables remote parameter control via server-client interaction within GNU Radio flow graphs. So this is just the XML server block. I'm sure many of you are familiar with it. So all you have to do is simply configure the address you want to connect to. And within the Python script, you can call upon this XML server to update any relevant flow graph parameters you want. And then we use ZMQ for data retrieval. So we know that ZMQ facilitates real-time data retrieval and feedback loops for adaptive control in OWC and RS systems. So we know ZMQ follows a publisher-subscriber communication protocol. And as you can see in the bottom, we have a little photo of the ZMQ pub sync, which we employ in our testbed. So now I'm going to go over the demonstrations we have. We have a couple of videos for you guys to look. And okay, I'm going to play the first video. I hope it's not too loud, okay? So over here, you can see that we have unique tones at each transmitter. So when I cover the RX1 and RX2, in the waterfall plot, we can see the signal drop off. When we cover the TX1 and TX2, we can still see the interference from the other LED as both the RX2 pick up, both the RX pick up the light from both of the LEDs. So, okay, so this is the same thing, however, we're adding modulated data at the transmitter. So I'm going to play the video. So over here, we block RX1. We see the drop off in the waterfall plot. We block RX2. Again, we see the drop off in the waterfall plot. Once we cover TX1, we see the drop off, but we still observe the interference at RX1. And we see the same for RX2, the same interference pattern coming up. And once again, this is just like a more zoomed in photo of what's going on in the waterfall plot. So we see RX1 blockage, we see the drop off, we see RX2 blockage, we see the drop off, we see the TX1 blockage, we can still see the interference pattern in between, we can still see the interference pattern over here too. And we see the TX2 blockage again, once again, we see the interference pattern. So another thing to point out is the reduced noise floors, because once the TX1 drops, we still have a little bit of interference from the DC power of the LED. So that's just another thing to observe. And as you can see, in both TX1 and TX2 blockage, the interference signal is still present. Next, we want to highlight how we use XML and ZMQ in GNU Radio. So I'm going to play this video. So it might be quite hard to see on the waterfall plots. However, we're using XML RPC to remotely, from a central computer, adjust the flow graph variables. So we're basically disabling both the TX1 and TX2, and we're also enabling both the RX1 and RX2. And as you can see, the relevant drop-off in the waterfall plot. And once again, in this scenario, ZMQ is used to retrieve the power. So we have a ZMQ pub sync that basically logs the power readings from the flow graphs, and all of that is available in our Python script. And once again, this is a multi-cell data transmission. So we're doing resource allocation across OWC cells. Yeah, I'm gonna play it back for you guys one more time. I don't think the audio came out properly. So as you can see, we rotate the photo sensor. And as we rotate, we observe the change in the audio file. There we go, perfect. And once again, we're going to show this demo, and this is basically when we use XML RPC to, from a central computer, configure the OWC subcarrier assignment. So this is all done remotely from a third control computer. And we're using XML RPC to configure everything. So we didn't use any of the Qt GUI or anything. So we just simply hit play in our control script in Python, and you should observe the changes. You can also observe in the waterfall plot how the different subcarriers are changing. And perfect. Okay. So outcomes. So we enabled a dynamic DC bias or optical wireless OFDM multi-node testbed with a remote control and feedback. We demonstrated a 2-channel DCO-FDMA link with dynamic subcarrier assignment. We demonstrated remote subcarrier assignment via XML RPC from a centralized computer. We demonstrated power retrieval and photograph feedback via ZMQ from a centralized computer. We hope that this open source contribution will help aid researchers for OWC research, and the repositories for all the relevant flow graphs and scripts can be found at this link. And another complementary repository which contains SDR tutorials for GNU Radio, and also performing packet error rates with XML RPC and ZMQ, again within GNU Radio, can be found at this link. And yeah, thank you for listening to my talk. Yeah.
Well, thank you very much. One sec, was Boyel here as the next speaker? Can I? Oh, there you are. Perfect. Okay. I just wanted to make sure you're around. We do have time for a question. Any questions for our speaker? Okay, Marcus has a question.
Hey, thanks for the great talk. OFDM is kind of, you mentioned that you have a DC bias to get your diode into the linear range, and OFDM is very sensitive to non-linearities. Like, is this a problem on the receiver side?
Sorry. So as part of the work we did for the Air Force Research Competition, so another team member performed the linear range and reception patterns of the photosensors. So we had to make sure the photosensors were within the linear range before we configured all of the flow graphs. So a lot of this stuff was done by another team member, and we made sure the whole testbed architecture aligned with each other. So the photosensor was in the. I'm stumbling upon myself. I lost my train of thought, my bad. But basically, we had another team member who was responsible for the hardware characterization, and he did emission and reception patterns and made sure all of the testbed architecture was configured properly. We actually have a repository where you can find like the emission and reception patterns and all the data and the spreadsheets for everything. I can refer you back to.
Thank you very much, and another round of applause. Okay, we have our next speaker, Whale, Dr. Whale Farrar. Whale is with SETI of Berkeley. I don't know. It's a mix, and he will be talking about GNU Radio and the Allen Telescope Array, which we heard about earlier this morning in Derek's talk. So actually, we're not quite sure. Are you gonna plug in your own computer? Do we have Whale slides? Are you guys?
Yeah.
We do. Okay, so we can just use those, and we have a clicker somewhere there that you can use. The green button advances.
This one?
No.
There it is. Oh, there it is. Oops, sorry. Perfect. That's a big green button. All right, awesome. Well, thanks everyone for tuning in to this talk. My name is Wa'el Farah. I'm a radio astronomer. That's what I do for a living. And my title is the project scientist for the Allen Telescope Array. And I'm here to talk about the Allen Telescope Array and how that interacts with the GNU Radio, which I'm sure all of you here are wanting to listen to. And also I want to talk about the other activities at the Hat Creek Radio Observatory, which is the facility that hosts the Allen Telescope Array. First things first, I have to give credit to the small but really vibrant team that stands behind the effort that's been going into the Allen Telescope Array in general. I'd like to highlight 4 members here on the screen. I don't think I've seen Nathan. Luigi is here for sure. Derek, who we all know and love. Nathan West, I don't think I've seen him here, and Danny Estevez, who might be actually online if there's a stream out there. But really, we are a really small team, and the Allen Telescope Array, as I will show later on, was only refurbished in 2019. This telescope was constructed in 2001, finished construction in around 2007, but it was put in hibernation mode until very recently. We do have a list of collaborators and consultants that I cannot really go through. Some friends as well, I would say, like people like Phil Karn and Roy Davis are really, friends of the Allen Telescope Array, the SETI Institute, and the Hat Creek Radio Observatory. All right, so where is the Allen Telescope Array? You can actually see it from Google Earth, which is kind of nice. If you fly into San Francisco, if you're in San Francisco and you drive 5 hours north and around the area where Redding is, and you drive east, you get to the Lassen National Park. It's a really awesome place to be. If you're ever in the area, please drop me a line, and you can have a private tour of the Allen Telescope Array and the Hat Creek Radio Observatory. But this is what it is. If you look at it from a satellite image, you'll see the signal processing room here to the green there, and you see those small speckles, so small pixels. These are the telescopes. So about the ATA, so Allen Telescope Array is the ATA. It was originally constructed, in 2004, I said 2001, and then refurbishment started in 2019. There are currently 42 telescopes as part of the interferometer. So it's a collection of dishes that act together as an interferometer. We have currently 28 of those have working feeds, and 4 others that have old generation feeds. So part of the refurbishment program was to upgrade the feeds that are on the system, on the focus of the telescope, upgrade the feeds, and upgrade the digital signal processing chain down the line, which I will talk about in a second. We're also really nimble in terms of how we develop and how we deploy equipment. We do have a quad-rich feed that we are prototyping as we speak right now. It's a 20-to-1 feed. You can ask me about it later on. I don't have slides on it, but it's super interesting component on its own. And the telescope has a really flexible configuration. It can track in azimuth and elevation. It has a fairly high speed in terms of its elevation and azimuth drives, so we can actually track satellites with it. So what are the current capabilities of the ATA? So again, I said we have 42 elements. We have 24 plus 4 old feeds, so 28 only operational feeds, but 42 elements that are mechanically usable. Each feed is sensitive between 1 and 12 gigahertz. Now there are some, or 1 and 11 gigahertz, there are some limitations when you go higher in frequency, so I always like to say it's between 1 and 10 gigahertz. That's the shape of the feed up there, so the top left, I guess, image that you see there. This is a log periodic in design, so it's basically 4 Yagis that are kind of coupled with each other for X polarization and the Y polarization, and they are placed in the cryostat, which cools them down to a temperature of around 70 Kelvin. And the reason why we do that is that electrons they whiz really slowly when they're cold, and so we have higher sensitivity. Now, the way the ATA is structured in terms of signal path, there's an RF over fiber module that takes the RF signal, the 1 to 10 gigahertz RF signal, sends it down through optical fiber all the way into the signal processing room that I showed in my previous slide. And there are a bunch of analog, really cool stuff that will take the RF signal back to SMA, back to copper. And then there are a bunch of local oscillators that would allow us, tunable local oscillators that would allow us to select up to 4 independent channels from each antenna, from each polarization, 4 independent channels of 700 megahertz each. So what makes the telescope really flexible is that it's sensitive between 1 and 10 gigahertz, and you can tap into 4 times 700 megahertz of bandwidth anywhere in that 1 to 10 gigahertz. So you can observe at X band and observe at L band at the same time. And the digital signal processing setup, anything that has to do with analog to digital converters come towards, at the end, as you can see in the bottom right hand side there. We currently have 3 DSPs setups. We have snap boards. Those are Berkeley, Casper, I guess, if that term coins, if people know that term. These are Casper boards. They are currently not being utilized because we have replaced them with RF sock boards, which we'll talk about in a second. But we do also have GNU Radio USRPs that are directly connected to the signal chain. Okay, so what are the RF sock boards? So those are RF system on chip digitizer boards. We currently have 5 of them. We're hoping to get 4 more in the next couple of months. So we're using 16 RF input boards. So that would takes us, 5 times 16 inputs equals 80, which gives us the ability to digitize 20 antennas with 2 polarizations and 2 intermediate frequencies, or 2 tunings out of the 4 that I mentioned. The role of the digitizer boards, and this is the main backend that we're currently using. The GNU Radio comes, parallel, I guess, to this. So the boards are, ultra scale plus FPGA on board. They digitize the signal at 14-bit ADCs at around 2 megasamples, 2000 or 2 gigasamples a second. We have a polyphase filter bank for coarse channelization, and that's what we need for radio astronomy in general. We also have a delay engine and what we call a fringe rotator. So as an interferometer, you have to make sure that all your antennas are delayed correctly with respect to each other before doing any operations, right? If you need to beamform, if you need to correlate, that's basically something you have to deal with at some point in the the signal path. And so that's the role of the delay engine here. And then we packetize the data and we stream it out into the network. And then a compute cluster would receive the data, would ingest the data. We have 8 of those, what we call SETI nodes. They are super micro, sort of off-the-shelf commodity hardware. We have NVMe drives for very fast I/O. 2 GPUs, either for every machine there are 2 GPUs in there, either RTX 3090s before they went extinct, and A6000s. And we also use 100 gigabit Ethernet network interface cards with a huge bulk of RAM. In total, we receive around 110 gigabytes a second from the current setup, which gets divided into those 8 compute nodes. So every NIC is receiving something on the order of 62 gigabits a second, or 7.5 gigabytes a second. Now, the observing mode, we can voltage capture, what we call a voltage capture mode, which is basically take all the data and shove it to the disk. This is only needed for certain science goals. We don't use it often because it's a really I/O intensive operation. We can either run the correlator, what we call the correlator. It happens that if you take an interferometer, the data from every single dish from an interferometer and multiply everything together, you obtain the cross correlation matrix. And then if you two-dimensional inverse FFT of that, you get a sky image. That's a really nice mathematical operation that you can do with an interferometer to form images of the sky. If you want to do studies of galaxies or studies of you name it. So you can use the correlator to do that. The correlator can also be used to calibrate the beamformer. So the beamformer is basically when you sum all the antennas with respect to each other, or sum the antennas together. Often you might want to delay them later on to produce multiple beams on the sky within the primary beam of the telescope. But these are the 3 observing modes that we currently have with the main backend. Okay, so what are the science programs? So again, here I won't focus on any specific science program. I just want to give you a brief sort of description of what we're doing, and also hopefully that would kind of trigger some ideas that some of you might have. So please, if you have any ideas of what you can possibly do with an instrument like that, please come talk to me. So the Allen Telescope Array is the first radio telescope that was built from the ground up to perform SETI. So SETI stands for the Search for Extraterrestrial Intelligence. What we do is basically we scan the skies with sort of our certain sensitivity. We scan the skies looking for signs for technosignatures, or what we call technosignature, which is basically anything that cannot be produced by nature. Any radio emission that cannot be produced by nature, right? So we're trying to tune in to an exoplanet that is orbiting its own star that might harbor technologically capable life that might be leaking radiation, for example. We also do search for deliberate beacons. The assumption there is that an advanced civilization might want to communicate for one reason or another. And the way we search for these signals is search for a narrowband CW, basically, that cannot be produced by nature. We search for a signal that is compressed in frequency. So this is a list, not a really extensive list of the projects that are going currently right now as we speak. We search nearby stars. We search what we call the anti-solar point. The anti-solar point is a shelling point. Basically, it's a way that universally multiple sort of civilizations might think that this is a way we need to communicate with each other. It's basically trying to search for a signal that is directly away from the sun. So basically, when it turns midnight, we point towards the stars that are directly away from the sun. And the reason why we do that is that if there are planets at that light cone, if there are planets that see Earth and see that we are actually transiting our own star, that's kind of a shelling point. And so this is one way they might emit a deliberate beacon to us. We also study what we call a SETI ellipsoid. I won't have time to actually go through this. It's also a cool concept. Basically, if a supernova goes boom somewhere in the sky, there might be a coordinated sort of effort of also ET trying to emit beacons over what we call an ellipsoid. As the radiation from the supernova kind of strikes planets as it goes by. Those planets, if they harbor technologically capable life, might send a beacon out saying, "Hey, we saw something." And so, if we detect that coordinated, that coordinated beacon, we can say that, hey, we might, find aliens that way. And we also do planet-planet occultation, which is basically, same thing as us, right? We send probes to Mars, we send probes to other solar system objects, as we heard earlier today in our in the talk. And basically, there's a communication line between us on Earth and the probe. And so, if that communication line might actually be leaking on other ends, right? The beam that the DSN has, or the beam that the probe might has, is pretty large compared to the size of the Earth, and pretty large compared to the size of the transmitter. And so there's leakage on either ends. And so one thing we can do is we can time planets. We can know exactly when planets are transiting, and we can try to search for leakage from communication, basically. Okay, so some things we try to do is we really try to do some, searching for technosignatures. One thing we do is we point at Mars. So we'll see what we can pick up. And this is an observation that we took early, I think last year, of Mars. We can actually see the carrier wave of Mars Express, as you can see on the left-hand side. This is basically a screaming technosignature, but it comes from a human-made object. And on the right-hand side, we can see actually the spectrum of Mars. We can see the detection of Mars Odyssey. Mars Express was not detected in that particular observation, but it was detected. It was probably occultating Mars. Tianwen-1 was there, and Maven. We've also seen Voyager. It's probably not too. Yeah, you can if you squint your eyes, you can probably see it. Doppler drifting signal in there. And yeah, we did so much tests to figure out that this is actually what we are looking at, Voyager, and it was it. It matches the frequency that we expected, and it was amazing. It it boomed in at the correct carrier to noise ratio that we expected, and you can also read about it if you're interested. It's on my blog. We also study what we call fast radio bursts, so FRBs in short. Fast radio bursts are millisecond-wide blips in the radio spectrum that we detect to be coming from outside of our galaxy. So something really, really strong, something really, really bright or luminous is emitting them. We still don't understand what they are, but we detect so many of them. On average, there are 5,000 of these FRBs a day, and we still don't understand what they are. But the ATA is also engaged in the study of fast radio bursts. And yeah, we've detected a repeating fast radio burst. Some of them repeat, some of them don't. This repeating FRB, it has a phone number of 2022 0912A, whatever. We observed that for around 500 hours. We detected 35 bursts, which is pretty cool in this field. We also track what we call slow transients. So if a star goes kaboom in the sky, it emits radio waves for many reasons, due to the sort of the emission processes that go off with the supernova sort of shell expanding and interacting with the nearby material. And if you're fast enough and you detect it in time, you can actually do some really cool science with it. And this is one of our first ATA results, which was pretty amazing because it was published in Nature Astronomy. That was really a nice piece of result. We worked a lot with people from Oxford to get this done, and yeah, it's just means the telescope works as intended. That's also sort of our fast follow-up. Again, if a supernova goes, if a supernova goes somewhere in the sky, we can actually directly, because we operate the telescope, the SETI Institute, owns and operates the telescope. We have absolute control over what we can do with it. So we can go and if there's a trigger from other observatories, saying that, hey, we detected something, the ATA can directly, get on source as quickly as possible. And this is one example. And this was published in last month. We also had another detection actually yesterday. There was another what we call astronomer telegram about this literally yesterday. So it's a really active field, and the ATA is really helping out in this kind of things. Again, I don't want to go through too much details here, but there's also other projects going on, like sort of measuring the magnetic field strength in the interstellar medium. And this is one way we can do it. Combining with other sort of facilities, the ATA can complement other kinds of observations that are being done. Chenoa Tremblay, who's a well-known radio astronomer, has been working on the ATA to do some of her projects. Also, the ATA has attracted a lot of undergraduate students as part of our REU program. So here in the US, there's and the National Science Foundation funds a program called the Research Experience for Undergraduates, REU. And the SETI Institute has a role to play in this. So we get around 10 to 15 students every year. A couple of them do projects on the ATA. And here I have a list of them there. So Ella Hort did some SETI signal searching. Miro Said, who was a SETI Institute intern, who actually now is applying or got his PhD in University of Manchester, so he's finalizing the paperwork. Felix Weber did some analysis of pulsars. Pulsars are neutron stars that are, basically when a massive star explodes, it leaves behind a neutron star, and if that neutron star spins around itself, it can turn into what we call a pulsar, so it pulsates in the sky. And so Felix did some of his REU studies on pulsars. Again, Alex did some, Alex is also an REU student who left us last week. Also did some search of fast radio bursts, and Grace Brown is also a postdoc from Penn State doing some work on long-term analysis of pulsars, of scintillating pulsars. You can actually see them on the bottom right. I know this plot is kind of too busy, but the bottom right, the set of red red plots, those show basically. I know the the font is really small, but on the if you believe me, on the y-axis there's frequency, on the x-axis is time, and what you can actually see, you can see the speckles of scintillation. Basically, there's a screen of ionized material between us and the pulsar, and that moves, and that basically means that there's a scintillating band or scintillating sort of effect on us. It's basically like sitting at the bottom of the pool and looking up at the sun. You can actually see how wavy, how scintillation works inside the pool. This is actually we're in a galactic pool in a way. It's kind of interesting. Okay, so let's move into some SDR related stuff, some amateur radio and SDR related projects. Derek mentioned in the beginning talk that the SETI Institute and the GNU Radio have joined forces, and this brought a community, you guys, a community of amateur astronomers or amateur radio astronomers. I hope you like this description, but we brought on board people who have knowledge in the field to join us at the Allen Telescope Array, and this is one of the hackathon that happened in 2019, which I took a promise from Derek a couple of days ago that we will have one next year. So please be tuned, stay tuned. If you're interested in sort of plugging your hardware into the Allen Telescope Array, you have the ability to do that next year. And yeah, that was a great event. You might also know Danny Estevez. Danny's been really active and he's really thanked for the stuff he's been doing with the ATA. All of this work has only been using N320s and N321 USRPs. Those tap into 4 antenna polarizations, and there's a GNU Radio Companion server somewhere on a dedicated sort of physical server that receives the data. But Danny has been able to do a real-time reception of the galactic hydrogen line using that. So basically, hydrogen. If you leave hydrogen atoms alone, there's the electron spin would emit basically if electrons sort of spin gets flipped, they emit light, and so this light is the 21 centimeter line. It's a really well-known line to study in radio astronomy, and we managed to detect that with a couple of USRPs, and you can see it here on the left. Also, Danny managed to figure out how to correlate the antennas with only 2 USRPs, and what he did basically is to, for every 2 antennas, record for 5 minutes, cross-correlate, and then produce this matrix, and then stuff everything together, using the RF matrix, basically just select as many antennas as you can, cross-correlate, and then at the end, merge everything together and produce an image of the sky. And what you see here is Cygnus A, which is basically a supermassive black hole in the middle of the blobs. So you see 2 blobs. In the center of the blobs there sits a supermassive black hole in a radio galaxy, somewhere in the universe, and then the material gets spun up around the supermassive black hole, and then 2 jets would arise. And this is exactly what we're seeing here. We're seeing the 2 jets from the supermassive black hole, and it's an active field of research. But it's also amazing that we can actually manage to do that with just USRPs. Other stuff that Danny has been busy doing is reception also of Artemis 1 that happened a few months ago. We also managed to detect Voyager 1 with a single antenna, and you can also see the plots there. On the left-hand side, I guess that's the quadrature plot, I guess, of Artemis 1. On the right-hand side, you can see Voyager in the right-hand and left-hand circularly polarized. Danny has a really nice list of projects that he's done on his blog, among many other interesting things that Danny does. But one of the sort of the thing that I like a lot about this project is that Danny managed to calibrate for polarization, right? So the ATA is a linear feed. He managed to do calibration so that he can convert linear polarization to circular polarization. So that's also interesting if anyone's interested in that. Okay, some training and outreach stuff that we've been doing. So earlier this year, we invited some PhD students and researchers from all over the world to do a hands-on radio astronomy and interferometry session at the ATA. So we held a 3-day workshop. We discussed how the ATA works and how radio interferometers in general work. And then we had a live observer training with around 20, we had 20 participants. 11 of those are graduate students, 7 are career researchers, and some of them are still using the ATA now. This is some of their results. We detected the crab pulsar. I know also this is a busy plot. You can ask me about it later, but that small blip there is on the bottom left in the time series. That's the crab pulsar. In imaging, we detected Cassiopeia A, which is a supernova remnant. So what you're seeing here is this expansion of this supernova shell that interacts with the interstellar medium, and it heats up the medium and it emits radio waves. We also detected some rovers, orbiters of Mars. I'm not sure which one that is, but it's one. We've also been granted an ARDC fund very recently. So ARDC, I'm assuming some people here are from ARDC, and there's a booth for ARDC that I saw earlier in the exhibit. But we applied for a grant to develop a GNU Radio-based SETI curriculum. So if people are interested in GNU Radio and interested in SETI, this is the place where you want to be. We are trying to work in collaboration with NASA community colleges, and we're trying to reach out to around 100 colleges. And we're also doing some training workshops for the ATA and so on and so forth. So this was just awarded. So we'll see the results of that in the next few months. Okay, let's see how am I doing on time? 2 minutes. Wow. Okay. All right. Other activities at the Hat Creek Radio Observatory. We've also been working with collaborators at CU Boulder, in particular, and many others from Google, WinForum, DeepSig, and National Radio Astronomy Observatory, to work on what we call the National Radio Dynamic Zone. In the past, if we want to protect radio astronomy in general and radio passive receivers in general, we place what we call a radio quiet zone, right? This is what's above the Greenbank Observatory and in Greenbank. But we cannot do this anymore, right? Population have expanded a lot. There are no regions in geographical regions where we can just make everyone stop using Wi-Fi and Bluetooth. This is not feasible anymore. So one way forward is to apply what we call the dynamic radio dynamic zone, which is basically a zone where active transmitters and passive receivers can communicate, how we can use the spectrum effectively, right? So if I'm a radio telescope, I can say, hey, I'm trying to observe this particular point in space and time. Can all the active emitters around me that are emitting at my particular frequency, can they please tune away from me or just tune it down for a second so that I can conduct my observation? And that's the whole sort of idea behind the National Radio Dynamic Zone. And we've been active in this field, so you can also ask me about this. Here are some cool photos and pictures about it, but that's basically what I wanted to say. We're also targeting some external and international collaborators. We're also hosting an outrigger telescope. Basically, CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. It's a telescope that was built to detect the early hydrogen signature from the universe. But it turns out to be a really well suited instrument to detect fast radio bursts. And now they're trying not to only detect them, but to use very long baseline interferometry to actually know exactly where they're coming from, because there's a lot of science you can do with that. And so the Hat Creek Radio Observatory was chosen to be a site for a radio telescope coming from Canada. And you can see the shape of the telescope is right there in the bottom left. Okay, I'm almost done. Just a quick announcement. Tomorrow, please join us at the Hilton Tempe downtown at the Varsity Ballroom. That's the address. There's wine and beer if you're interested in talking about, Breakthrough Listen and SETI. We have members from the SETI Institute, Rebecca and Simon right there. There's also Luigi. Are you here? Luigi, yep. And then Derek, if you're interested to talk about any of this, please, walk around the room, find them and ask them questions, and I'm sure they're happy to answer them. And with that, thank you a lot, and I'm happy to take any questions.
All right, thank you very much. I'm going to ask you to take the questions offline in the hall, just because we're like slightly over time. But it was always great to see you guys. I'm not quite sure which organization you're for. One of your organizations is also a sponsor of the conference. So yeah, Allen Telescope Array is always very exciting to see what we get out of it, and it's one of those fascinating places where GNU Radio and really cool science meet. So actually, do we have the next speaker around? Are you Michael? All right, Michael Aldred, that's right. From Sydney, is that right? I was reading that. I was like, wow, we have people coming from all over the world to this conference. Michael will be talking to us about ad hoc sense networks in rail shipping containers, like very interesting abstract. Yeah. All right, I'm gonna let you set up and take it. So you're using your own laptop, okay? Yeah. So you just plug in and then go. At least I think it's worked so far.
Yeah, we tested it before. So.
Excellent.
Yeah, okay. I'll just put it down. Testing. Okay, hi. I'll just get the screen up. Yeah, hi, look, this is a presentation on ad hoc sensor nets and software-defined radio used in a rail environment. So yeah, my name is Michael Aldred, and I'm a PhD candidate at UTS and also a senior project engineer at Laing O'Rourke. So my work career is included communications utilities across the world, Ireland, Australia. I've worked for Hitachi and MTS, and I'm currently working for Laing O'Rourke. So my research at University Technology Sydney started in 2019 and extended from an idea using audio to transmit data using ultrasound. So the ad hoc shipping network project was initiated by my supervisor, Professor Robin Braun. My objective was to create a working prototype using GNU Radio to modulate and demodulate data at 40 kilohertz in air, water, and steel. And the original concept was theoretical in nature, to create nets using modulated ultrasound. The software solution was novel and innovative with many benefits. So communications devices could connect to each other to form networks. Nodes could be created when a certain number of connections had been made. And the application was considered revolved around shipping containers with sensitive and precious cargo. So these freight normally had high monetary value. The environment inside a container could be continuously monitored. And so that it was not damaged, sensors would capture temperature, humidity, air quality, gas, preventing vibration, radiation if required. So as you can see from the diagram there, like shipping containers on ships, they're packed really quite high. And so one of the issues about that is that when you're trying to communicate with the outside world and with this information, if you're using a 4G modem, and if your container happens to be the one on the inside, it won't be able to communicate to the outside world because RF doesn't communicate through these if it's surrounded by other metal containers. So, however, audio waves will travel very well through metalwork, and you could create two devices, a device that will communicate through the metalwork using audio waves, and then to a node that will actually use a normal EM wave. So the same issue as well for freight trains, where you have like a number of containers all on a very long train. There's no network in a lot of the rural and remote areas. So you need to have a way to communicate, especially if you've got sensitive or precious freight. So each metal car would basically have so all the containers are in metal cars. They're all connected to each other by coupling. And if each one of these containers had a device that could, like a shipping container radio, that could modulate and demodulate, the sound waves would propagate through the steel for the short distance, and every freight metal enclosure on each railway car, they all would communicate. And the concept behind how ad hoc networks could be created using GNU Radio is a way to exchange data between these devices. And if a container generates an alarm because the sensors detect heat, then the driver, for example, of the train could actually do something about it. So basically, how you're actually propagating data, you're using an ultrasonic transducer, and the sound wave, the energy causes the piece of ceramic plate to vibrate if it's on the receive side, and if it's on the transmit side, you're actually converting the electrical signal into an audio signal. So the electrical signal is amplified and resampled to create a complex data stream, and the software block in GNU Radio filters out the unwanted components of the signal. So the part that remains is the data stream, and the stream has to synchronize with the receiver. So you need to have a preamble that will actually, tell the receiver where to actually start when it's correlated and where to actually begin the data read. And if all goes well, the data is captured and can be opened to read the message, to see the image or hear the audio. So one of the things about, like, as opposed to electromagnetic waves, so at 40 kilohertz, an EM wave would have to have a wavelength of about 7,500 meters, which is quite long. But for audio, that wave would be in air, it would be 8.5 mil or 37.5 mil or 148 mil if in steel. Now the speeds that audio waves travel, like in air, it's 340 meters per second. In water, it's about 1,500. And in steel, it's about 6,000 meters. And the wave itself elongates when it actually changes from one medium to another medium. So there's some issues with that can cause data loss. So this is just a short video. It just shows you how you can see how fast the audio wave will propagate through steel. And when I play that, it's really, really fast. And then when it goes through air and water, like in air, it's like just pretty slow, right? But it just shows the actual the difference in speed. Like I think sound propagates through steel nearly 20 times faster. So next up, so when you're using audio waves, in normal EM waves, it's a transverse wave, but in audio, you can have both a transverse and longitude waves. It can be both. So some of the modulation techniques, on-off keying, right? Which is a very basic way of doing things, which is quite good. So our amplitude shift keying, but BSAK is the same as off-off keying. Frequency shift keying is another very good, using a mark and space for the 0 and 1. You can actually have a QFSK, but that requires a bit more bandwidth, and the same with phase shift keying. If you want to have like 4 frequencies, you need QPSK, which takes up a little bit more bandwidth, and we have very limited bandwidth. It's only really from 39 kilohertz up to 41. So I did a signal noise ratio test, and you can see on this that I'm getting nearly 30 dB above background, which is great when it's close together. This is again in air, but the signal to noise ratio is fantastic. So some tests that I actually performed. So first of all, some rail track that I actually did some testing on to begin with, using 2 Raspberry two Raspberry Pis, and Ubuntu GNU Radio, using a bit of Rail, and I basically put the transducers on both ends, and I sent a data set from one side to the other, and I got very, very good results from that. Now, again, it was a data set, so it wasn't actually real data in a real, like a file that you're transmitting. But it was still okay. It showed that everything, the data was actually being received properly, and it was being sampled correctly. And I demodulated and displayed it on the monitor. It did a comparison. It was exactly the same. Did use the 3 different modulation techniques. However, ASK or double on-off keying was pretty much the best result. So, excuse me. So this is another test I did. This is showing using it in air. So this is basically some files that I used for transmitting and receiving, and they're basically modulated files that Barry Dugan created, and they work really well for this application. So the first thing was using software with the preamble. I tried using text, and the preamble allowed the receiver to synchronize, and it correlated straight away. The transmit receive rate, was 120 baud. And the file source was about 2 kilobits. So it took about 2 or 3 minutes for this to transmit. I used the Gettysburg address, and it worked really well. So, all right, the next bit was basically just actually, I decided to do an image, and this was at 1200 baud, so I transmitted the image again, and it was in air, so I'll just play this.
Okay, so what I've done is I've set up again, like to have another go. I've created 2 new leads because I wasn't having much success with the transmitting it through rail. So I've got 2 40 kilohertz transducers. They're actually going through this particular sound card. I've got an empty output.temp, and I've got an output2.jpg, and what's in that file is basically, this is my target, and it's actually just the blue screen of, So now what I'm going to do is I'm going to move this file, which is giraffe2.jpg, and I'm going to transmit it from the left to the right, okay? So the first thing I'm going to do is I'm going to just make sure that I've got both of my things ready to go. So I've got to actually open up the receive first. So I'm going to go receive. Okay, now this is actually set to transmit at 1.2 kilobits. One thing I noticed before, the correlation did it straight away. I could not get it to collate earlier, right? And no matter how hard I tried, I could not get it to work. So we have good data flow, which is fantastic. This takes about 3 or 4 minutes.
So rather than waiting to see data transfer, I'll actually just advance it a little bit.
34.
So to get towards the end where you can actually see the actual file convert. So I'll just move it up to about here. So this is pretty much getting towards the end of the actual data flow, and you can see that it's actually, the preamble has actually finished.
Last bit of data is done. So that's completed in just under 8 minutes. So I'm going to, now that that's done, I'm going to close the transmit. I'm going to close the receive. My data that's been transmitted is 52.7. So there's quite a bit, there's a bit of the preamble in there as well. That's all the preamble. So now what I'm going to do is I'm going to come back to, and this is receive. And then I'm going to go to convert it. And watch, as soon as I actually press the return, what will happen is the output2.jpg will change. All right, and there it is. So what that means is I have transmitted the giraffe from one to the other.
Yeah, so that was, but that's in air, so it doesn't really count, does it? I mean, you know, you can just actually use RF for that. However, like, so this is basically the transmission. So I've got the actual target with blue screen, nothing like it to actually overwrite, and then the actual image of the giraffe. So then I thought the next step of that is to actually do this in water. So I set up a little water bath, and I actually set it again, same sort of thing. And I transmit it. So this is the second one. Again, it was a 1200 board.
What I'm going to do at the moment is I've got this in water.
I did it a number of times. They're not actually, they're not
minutes ago,
touching,
so I'm
even though it
going
might
to
look that way.
Give it a go. So we've got set up. We've got our sand card, 2 ultrasonic transducers sitting in water, right, and they are not touching, as you can see, but they are sitting in water.
I had to mention
So
that.
this is what I have at the moment, and I'm going to send a picture of a chimp, right, which is in my receive file. It looks a bit like this, right? So I'm going to send it from one side to the other, and it'll replace that output too. So I'll get my files open again. Okay, so over on this side, I'm going to run the receive. Okay, so that starts that side up. On this side, I'm going to run the transmit. Which is that one. And as you can see, it correlated pretty much straight away, right? Which is surprising because it is sitting in water, right? Now, in the end, I found it was just best just to dump it straight in the water, and then it worked.
Yeah, sometimes it's better not to try and line it up. It just put it straight in.
Set it up in any way. So correlations worked. That's very good. And it takes maybe a couple of minutes.
So I did this with a number of different file sizes and
as you can
with
see,
various successes.
Right, and it seems to be transmitting okay. So we just got to give it a few minutes. So this is really the first successful transmission in water, right, that I've had. And so we'll see how it goes. As I said, it'll take a couple of minutes, and we've just started maybe a minute ago, so it'll probably take about 4 minutes.
Yes. So one of the issues I had with this was basically if you move the transducers around, it actually caused the signal to actually deteriorate. So that they had to be not interfered with during the transmission.
It seems to be,
but
transmitting.
I did it a number of times with a number of different file sizes, and it was successful most of the time, except when I moved the transducer.
And on this side, we have, our TX all going through very well. And this side is good. It took such a long time to get it to correlate, but it did eventually.
So what I'll do is I'll just advance it to get it up to probably where it's getting towards the end.
Again, still correlating, still sending, still going through. And I think we're
probably, yes. Oh, there it is. Now it's finished. It's gone through the actual
and then I'm going to come on this side and close the
preamble at the end. And you have to actually remove the preamble from the file to get the original file back again. It did make the file about 20% bigger.
And now I'm going to go over here and I'm going to run the preamble stripping. So that's stripped the preamble. That seems to have said that that's gone through okay. And then if we have a look over here and we open up this file, and there you go, right? Transmit it from one side to the other. So I've now got.
Oh yeah. So anyway, that one worked. So that was successful in water. Now, I really wanted to get it work in steel, but unfortunately I had some issues with that. But I'll just show you the results for water first. So most of the time it did actually come up. I did get image, as you can see with this image, where the top part of the image is okay, but the rest of it's distorted. So there was a couple of attempts where the transducer did get moved and it ended up failing. And also the type of transducer that I was using, some transducers were better. I had to actually figure out which ones were actually best suited for this type of application. I found one that worked really well. It was still an off-the-shelf device, but I found one that worked better than the one I tried in the first instance. The first image was 80 kilobits, but I've done a couple of other images as well along the way, and I've tried different ways of actually immersing it to actually get it to work. So it all worked out okay. And again, the actual file size was about 20% bigger at the end of it. Once you strip the preamble off, it came back to the original size. So it works for text, works for images. So the last thing was basically to do it in steel. Now, unfortunately, I had an issue with the transducers. Like these transducers, I actually tested at 40 and 48 kilohertz. Because the idea is you'd have two channels, so you could have duplex, which is always a great thing. So both channels, they work in air, but unfortunately, they won't work in this particular thing. And again, it's to do with the fact that you're generating the or acoustic signal in air, and then you've got an interface between the transducer and the rail, and the wavelength is extended, and then when you get to the receive, it has to be compacted down to go from 150 back to 8.5 mil. So I think these areas are definitely causing issues with the signal. With basic data, with just a normal data set, it was okay, it was perfect, but basic data set isn't really going to be of use, but I will get this sorted when I actually try some different transducers. I think that will make a big difference. So pretty much that's the end of the presentation. I'd like to thank Barry for his help in getting this to work, especially with the preamble, and GNU Radio for inviting me, and my friends at UTS and colleagues at LOR and family and friends. So that's pretty much it. Thank you, and I can take any questions.
All right, all right, we have a question over there. We actually have some time now. We caught up again, so that's great.
When you switched from air to water,
yeah,
the baud rate stayed the same. I would have expected, since everything's
no, but don't forget, in the transducer itself, right? It's actually like a speaker. So it's in an enclosed container, right? So you're actually generating the acoustic wave in air. And then, it's actually, when it's going into water, the length of the wave is changing from what it's been generated at to a longer wavelength. Because the speed of sound in water is like nearly 1,500 meters per second, as opposed to air, it's 340. So to be able to generate, if I was to use a transducer that had liquid in it, it might actually, I'd be generating it in liquid, and then I wouldn't have that issue with the interface where it's actually elongating and then it's compacting again. So I think that will actually make a big difference. But I think it's got some great applications, and I think it can actually do, it's just using sound cards with very high sampling rates. And, as the audio technology improves and becomes available, you will be able to do a whole lot more with sampling at that particular frequency.
Are there any more questions? I actually have a question of my own. So sure. I wasn't quite sure I fully understood the intended application. So you showed this picture of the long train, And the idea is that you can like have communication across the train, even when you're in the middle of Australia where there's no.
Well, that was to do between each one of the actual containers on the train and the driver's cab, right? So when like, if you're having, say, a shipping container radio where you're going to be communicating from container to container, so if every container or every second container had an actual a shipping container radio, right, where you're actually communicating using ultrasound, using acoustics rather than EM, you would be able to communicate between every container, and you would also be able to communicate up to the driver's cab. And that would be useful for even such things as train integrity, for understanding that, you know, if there's any issues with the car right at the very end, that it's gone on fire, that the driver would have an indication that there's some issue. There was another application as well that we had for high rail vehicles, road rail vehicles, when they were going on and off. And the pads, when they go from a normal road vehicle to a rail vehicle, they put their rail wheels down. And a lot of the time you want to log that vehicle when it's going on, and being able to capture data from it, like when it's in tunnels and when it's actually another information about logging it from accessing the corridor and leaving the corridor. And it would be very useful. If you're using RF, that road rail vehicle wouldn't have to be in the actual corridor. It could be just outside the fence and you'd still be logging. Another application was if you had a train on platform hold and waiting at a level crossing, you could basically you could transmit directly to the interlocking for the level crossing to get it to activate. And again, because it would be through the rail, you wouldn't be actually activating the level crossing if you were anywhere else except within 30 to 50 meters of the actual level crossing. And the problem with the solution at the moment for where trains that are on platform hold in front of a level crossing is they're using an RF radio to connect to the interlocking to activate the crossing, but that could be used from maybe half a kilometer away, when you wouldn't be near the level crossing. So it's just another way of actually communicating through using acoustics rather than using electromagnetic waves.
I'll take it. Actually, is our next speaker right here? I just want to make sure that we have. Oh, there we are. Perfect. Okay.
Thanks for the talk. Can you actually have multiple channels?
Yeah, well, it depending on your sampling, right? So if you can, and the transducers that are available. So I'm using 192 kilobits per second for sampling. So that's 4 times the actual transmission rate. So even at 48, I can sample, so 40 to 48. But if I was using a higher sampling rate, I could sample at 96, or I could sample at a higher rate, but it has to be either 2 times or 4 times the actual the transmission speed. So 40 kilohertz, 100, which is 160 kilohertz, that's fine at 192. And again, 48 is the same thing. So you can have a number of different channels, right? You just need to have an audio device that can actually sample at high enough rate. So it's got some great applications, you know. And from using in water, from using through metalwork, and also for places where you simply cannot use electromagnetic waves.
All right, Michael, thank you very much. Another round of applause, please, for our speaker.
Thank you so much. Okay, cheers.
And we have two more radio astronomy talks before the break. Lindsay, you can come up. Our next speaker, Lindsay Burkhardt, is actually from ASU, so that's very nice. And we'll be, oh man, sorry, you were talking about 21, the hydrogen line reception. That's right. We heard about the hydrogen line in Whale Sock, and then we'll hear how everyone else can actually participate in doing that. Yeah, please take the mic. It's all yours.
Cool. Everyone hear me? This better? Excellent. Hi everyone, I'm Libby. I'm a 5th PhD at ASU, and I mostly work on radio astronomy. Today I'm going to be talking to you a little bit about one of our outreach projects called CHART, or the Completely Hackable Amateur Radio Telescope. It relates actually a little bit to some of the stuff that was talked about 2 talks ago with the ATA. So what CHART is a low-cost open source platform for radio astronomy. When I say platform, I mean full platform from learning about the astronomy to taking your data all the way to analyzing the data. So kind of all of the steps involved. We're targeting this project particularly at secondary school and undergraduate educators. And undergraduate students at ASU take ownership of the development and testing of the project. So I'm talking here from a more advisorial role where I'm mostly supervising undergraduate students who are doing the actual work here. And I'm not going to get technical at all here with our GNU radio involvement, because the next talk is going to be from one of our undergraduates who's going to talk to you more about that specifically. So why do radio astronomy in a secondary school? Why not stick to optical astronomy, which is probably a little bit more familiar to most of the public? There's a good science case, and then there's a good accessibility case. So different wavelengths give you different information about astronomical objects. The image I'm showing here is the multi-wavelength Milky Way from NASA. So most of the public is familiar with looking at optical images of the Milky Way, where what you're seeing is stars emitting light that is obscured by dust, and that's most of the structure that you see. But other wavelengths give you other information about the galaxy. You can see in the radio continuum, the dust is completely transparent and you're just seeing the emission. Additionally, radio observations don't suffer some of the logistical difficulties of optical astronomy. Backyard optical telescopes are a little bit limited, both in scientific information and in visibility. So looking at a galaxy through your backyard telescope is really cool and inspiring, but not necessarily particularly scientific. And you have to make those observations at night in places where light pollution is not an issue. Radio telescopes do still have some limitations like RFI that make measurements difficult, but you can still do clear science with them in cities for low cost during school hours. So the science case that we're targeting for CHART as a base platform is this 21 centimeter line that was mentioned a couple talks ago. So neutral hydrogen has 1 proton, 1 electron. The proton and electron have what we call a spin. When the spins are aligned, so they're either up, up, down, down, it is a slightly less stable state than when the spins are anti-aligned or opposite of each other. So any neutral hydrogen atom that is excited into the aligned state will eventually spontaneously decay back to the anti-aligned state and will emit a photon at a characteristic wavelength of 21 centimeter or frequency of 1420 megahertz. And this 21 centimeter line is used for a lot of different applications in astronomy. The one that I'm referencing here, just to kind of pull in what we could do at a secondary school level, is measurements of our own galaxy. So I'm showing you a rotation curve, actually not of the Milky Way, this is of M33 here, where you're measuring the velocity of visible matter at a distance from the center of the galaxy. And when you predict a rotation curve, you sum up all the mass in the visible disk and you predict what the rotation curve should look like. And then you go out and you measure how fast are stars moving on the edge of the galaxy. You find that everything is moving much, much faster than we expect. And this is one of our key pieces of evidence for why dark matter has to exist. We know there has to be something out there that we can't direct detect. And a lot of the evidence for this comes from 21 centimeter measurements. And you actually can reconstruct this rotation curve using amateur measurements. So this is kind of our big picture, like trying to get people interested. You can prove dark matter to yourself. So this is where I'll stop to mention that there are a lot of similar projects out there, as evidenced by the fact that one was just talked about a little bit earlier. These are a small sample of some of the ones that are most similar to us. This is definitely not all of them. There are many projects with many specific focuses. Ones like Pictor, which is the bottom one here, set up an instrument for you to use remotely where you can take these measurements sitting on your laptop somewhere else, and some of them focus on building your own instrument. We're specifically focused on trying to do a complete system. So you build your own telescope, you take your own data, you analyze your own data, and making that all really accessible. Our base system is pretty simple. It's modularized to be easily accessible, and components can be easily swapped out. This is because sometimes things go out of production or are difficult to find, or maybe you just want to use a different SDR. Our base design is really simple. It's a cardboard horn covered in aluminum foil. There's some electronics, LNA filter, and then we use an RTL SDR and Raspberry Pi to do the processing. The cost breakdown I have here is assuming that you have none of these parts available to you already. You don't have your own personal laptop running GNU Radio. You don't have a monitor or cables and connectors, and all of that costs about $250. But you can significantly reduce that cost if you already have some of this stuff available to you. So just to show you some cool results that we have gotten with our cardboard horn, these were taken in Winona, Minnesota, which is a semi-rural location. It is a university town, so it definitely is still populated, but it's a little bit less sparsely populated than somewhere like Phoenix. And what I'm showing you is us pointing our horn out somewhere in the galaxy. Hopefully that image of the Milky Way is big enough for you to see. But you're looking along these lines of sight that cross a number of different structures in our galaxy, and you're collecting all of the gas within the field of view of your horn. And then we take that frequency spectrum, do bandpass correction, transform to what we call the VLSR frame, which puts the Earth and Sun stationary with the mean motion of the local solar neighborhood. So basically, you're just correcting out for the Earth and Sun peculiar motion. And then we calibrate to get real units. And here we're comparing our data in blue to a data from the a simulated spectrum from the LAB survey, which has an online simulator where you can go in and put your galactic coordinates and your field of view and get out an expected spectrum. And so what you're seeing there is a velocity versus brightness temperature spectrum. So you're seeing a couple of different clouds of gas moving at different velocities within your field of view. And you can see we agree pretty well with the LAB survey models. There are a couple of discrepancies. You can see maybe in the lowest one, the width of our data looks to be a little bit wider than theirs. And there are a couple of obvious sources of error for that. When we go out and take this data, we're pointing a cardboard horn at somewhere in the sky and writing down where we think we were pointed, and we're not going to be able to do a perfect job with that, but we can do it pretty well. And then the LAB survey simulator only goes up to a full width half max of 20 degrees, and our field of view is a little bit bigger than that. For the horn, it's maybe 25 to 30 degrees. So we expect a little bit of difference. But we're definitely doing a good enough job at a secondary school level to be able to make really interesting measurements. And this is just to show that we've also taken measurements in some more densely populated areas, such as the middle of Phoenix. Our student who went out and took this data took this photo of where he was observing. We don't know what that antenna is or whether it was transmitting, but it was pretty funny to see him in a parking lot right next to this thing. And we do a pretty good job even in RFI heavy test environments. We definitely still convince ourselves that we do detect the 21 centimeter line. We, in this particular observation, can't necessarily detect substructures like that sort of bump out at negative 60 kilometers per second. We have a ripple on our spectrum at about the level of that substructure, so we're careful not to interpret that as necessarily a detection. But our main lobe fits pretty well, even in a RFI heavy test environment in the middle of Phoenix next to a building with a giant antenna on it. And we've used this system a couple times for a couple of different purposes. So we've taught a couple of things at the undergraduate level Specifically, earlier this year, our lab ran a 1-week-long boot camp for undergraduates where they analyzed data from this instrument. We used it in a spring 2021 course at ASU, and also we have pretty much every summer a cohort of summer interns who come in and work on the project. We also taught a 1-week-long teacher workshop at Winona State University where a couple of local teachers came together and they built their own instrument, and they were all able to get detections, which was really cool. So if you're interested in this kind of work more, or you want to maybe build your own system, you're welcome to contact either me or Professor Jacobs at ASU. We're kind of the local advisors. This is also the part of my talk where I advertise that I'm graduating in the spring and looking for a job. So if you want to contact me about that too, feel free. Also, Professor Beardsley at Winona State was the founder of this project, and he leads the contingent there. We also have a website and a GitHub, which are probably not fully navigable without help from us yet. Some of our tutorials are still in alpha testing and not all the way integrated. But if you are interested in helping us out with some of the testing, we would love that. We also have a paper. You can currently find it on the archive, and it is in peer review for a journal. And if I have any time now, I will take questions.
You do? Yeah, thank you. All right, who wants to start? Marcus? No. No, sorry, you looked like you were. There we go. Can you just repeat the question?
Oh, sorry. Are you asking? You want to know like this location with the big antenna, like how it corresponds to? Okay. So it's not. It's not the same line of sight as any of these. Unfortunately, you can see on the Milky Way photo, I have all of the lines of sight for the Winona data labeled. I think the Phoenix one is the green one, so it's not directly comparable to the ones on this slide.
So for the recording, the question was whether the picture with the antenna corresponds to any of these graphs. We have time for another question. Oh, Eric.
How do you point it, and how do you know where you're pointing? I mean, the pictures of all have like just somebody with a piece of cardboard box in their hand.
Yeah, great question. So one of the things we're hoping to put on our website very soon is an observing guide telling you how to go out and take your own measurements. For the most part, we're using Stellarium to predict where the galaxy will be when we're going out. So we go out and we have a plan of where we want to point. And then basically just using a cell phone kind of laying on top of your horn, you can get a pretty good altitude measurement of like where exactly you're pointed, and we just estimate from there. Fortunately, our beam is so big at like 25 or 30 degrees that getting like exact pointing is not incredibly important.
Right. One more question, and is the next speaker somewhere around? Oh, there you are. Perfect. Okay, perfect. Just so I know that.
Thanks for the talk. Can you, with a beam that size, and you're doing measurements around the 21 centimeter line, which is expected to be a RFI free band, technically due to the FCC regulations. Can you say something about RFI inside of that band, especially in Phoenix?
Yes, definitely. So that is one of the things I glossed over when I said RFI is a problem. As you said, the 21 centimeter line is a protected band. Nobody should be transmitting in it. Unfortunately, out-of-band stuff still does saturate electronics, and so I think that that's our main issue with why data from Phoenix looks so noisy is out-of-band stuff. We do see some actually in-band emission that might just be artifacts from out-of-band stuff aliasing, or it might be our own interference. I think we did some testing, like whether our own like Raspberry Pi was generating stuff in-band. But Yeah, I think the main problem is just everything out of band saturating.
All right. I think that's all the time we have for questions. Keep in mind, Libby is looking for a job next year in spring, and she was able to chart the galaxy with a cardboard box. So that's all the qualifications I need. Yeah, big round of applause. And we have one more speaker, Caitlin, also from ASU. I assume you were working together on this.
Yes, she's now going to tell you on this project specifically how GNU Radio is related, because that's what she worked on.
Okay, perfect. So basically, this is a continuation of your talk, of this talk, and yeah, we'll hear all about it.
Hello, I'm Caitlin Ashcroft. I'm an ASU undergrad, and I will be talking about the visualization of signal processing for radio astronomy, a GNU radio companion-based spectrometer for chart. To reiterate some of the points from the talk before, chart, short for completely hackable amateur radio telescope initiative, targets students and educators interested in radio telescope astronomy and teaches them how to create a telescope and how to analyze the data. At the moment, it is set up and being tested by undergrads. Chart has telescope making tutorials, computer programs, and Jupyter Notebook tutorials set up to teach people how to make a functional program. Previous work set up a robust data capture system, but the code is a black box. This project is for users interested in pursuing signal processing in more detail. GNU Radio Companion Base makes this process transparent. The horn is made from cardboard and tinfoil in the shape of a pyramid, which is shaped to be more easily allow the signal to reach the antenna that is in the horn. And the circuits are made from easily soldered pieces. The antenna part of the telescope is very easy to build. The antenna horn is attached to a low noise amplifier through cables. The cables also attach the low noise amplifier to the SDR that is either connected to a Raspberry Pi or, as shown on the screen, a laptop. Chart is designed to be as simple as possible with easy to swap out components. My focus was on the data collection and file writing process that can be done on a computer. A few different data collection programs are offered depending on the user's interest. The program before mine offered a Linux-based Python data collection script accessed through a terminal, as well as a GUI that is easily navigatable. You put in the range of frequencies that you want to integrate over, the number of times you want to integrate, and the amount of times the integration lasts. The GUI then puts the parameters in code and runs the program. This data collection and mine use GNU Radio package and Python. These methods offer a quick way to understand the parameters involved in data capture, but obscure the signal processing steps being performed by Python code from the user. Users can look at an open source code themselves, but if they lack familiarity with Python or signal processing, it may be difficult to interpret. GNU Radio offers a more visual way of understanding the steps involved in collecting your data. This makes it easier for students like myself to go through the steps of setting up the data collection program. The flow graph performs the FFT, power calculation, integration, and file writing steps without me having to go in depth on the math needed behind every step. It also includes a number of breakout points where the user can inspect their signal live, letting the students understand how these steps affect the signal coming in. When I first started this flow graph, I used tutorials on Chart website and on GNU Radio Companion site to set up the initial graph. The graph has allowed me as a beginner programmer to see where the data was going. The power connection and integration are average power part, and they are signals that change it from the time domain to the frequency domain, and they average it to amplify the signal more. I may have known what an FFT was and how to integrate it from my classes, but I did not know what it meant in radio astronomy. The file writing section of the graph is made up of a file sync and file save. The file sync is a standard GNU radio block that saves all the changes in the spectrum to the file. The file save is a custom Python block that takes metadata down and saves it to a specific file type. Now it's time to go out and test the flow graph. Even though there was a lot of helpful tutorials on how to set up the flow graph, it had still been daunting to make. This is where I finally got to see the fruits of my labor outside the lab. The horn is taken outside and pointed at the galaxy, and the program is started. I was so excited when I finally got confirmation that the signal was coming in. You can see the top graph as the time domain voltage graph showing us how the signal is coming in. Then we have the spectrum FFT showing us the frequencies that are coming in, and finally the waterfall plot showing us the histories of the frequencies coming in. At the same time as these graphs are being shown, the program is saving all spectrums to a file save. Finally, after we have the experiment, we can start further analysis of the saved data. The chart project provides a number of Jupyter notebooks with example Python code for analysis. In these codes, they provide tutorials on how to code. Students can share and learn from chart guided tutorials that allow them to process the data. This graph from the same experiment, but at a different pointing to the one before, is one single pointing at 75 above the horizon near the galactic center. The 21 centimeter line is clearly visible. I would like to thank Lindsay Burkout for answering all my questions, and Professor Adam Beardsley and Danny Jacobs for helping me with this project.
Okay, cool. Thank you very much. Do we have any questions? We have some time. Okay, first of all, I love these kind of projects. You know, it's easily accessible, and then you not just like listen to the local FM radio station like what I said, but you actually look at the entire galaxy. So I think those are very cool. I just wanted to. It's not a question. I just wanted to put that in here. I did have a question. From earlier. When you showed those lines, you said you used some external data to calibrate to real units. I don't know if you said that or if you said that. I don't know who's best equipped to answer that question. But like, how do you actually calibrate back to real units? Did you have like an actual calibration step, or did you have some other data to correlate with? Oh, okay. Excuse me. Do you want to answer?
For that part. So we try not to publish methods to calibrate back to real units that we don't feel like educators would be able to replicate. So we don't want like lab equipment or anything. We actually just used that LAB survey and assumed that we were seeing the exact same thing and used their absolute temperatures to calibrate our own.
Okay, thank you very much. Do we have any other questions? If not, we'll have one more round of applause for our two speakers and the chart project. And we have two more lightning talks before the next break. And the first one will be given by Clayton on the Capture the Flag. So while he's walking up on stage, I just want to plug the Capture the Flag contest. So you can participate in this during the conference. You know, there's like basically signals you have to find or other kinds of puzzles. I actually will be hearing about that from Clayton himself. But I just want to, urge people to participate and don't be intimidated.
All right, here we are. Let's talk about Capture the Flag. But before that, who am I? My name is Clayton Smith. You may know me online where I use the handle Argilo. or you might find me on the air where my amateur call sign is VE3IRR. And I would consider myself an SDR hobbyist. I like to decode all the signals that I find around me, and if there's no software existing for those, I like to build my own. And I like to build transmitters for all kinds of things. So I've fooled around with stuff like HD radio, GoTenna. I'm the maintainer of GQRX, which is able to receive a lot of different types of radio signals. So let's get into capture the flag. Isn't that the game where you try to grab the other team's flag? Well, that's not the type we're talking about here. We're talking about a game that came out of the information security community. And in a traditional hacking CTF, usually what you have to do is break into computer systems and find information that is hidden in those systems. And you'll find little secret messages that are called flags. And when you see a flag, you submit it into the scoreboard and you earn some points. Here at GRCon, we have an RF CTF. And so instead of the flags being hidden in computer systems, they're hidden in radio signals. So what might that look like? Here's an example of a challenge from a few years ago where there are two FM signals and they're moving up and down in frequency, and you had to put together some kind of a receiver that would be able to follow those changes in frequency in order to decode the signal. If you tried to do this with a standard program like GQRX, you'd have trouble because as soon as you receive something, it's already off to another frequency and you're not hearing it anymore. So people who solved this were able to put together a simple flow graph in GNU Radio using something like a phase lock loop to track these things as they move around in frequency. Here's an example of another challenge from last year where a signal was painted onto the spectrum, and you could look at it with something like InSpectrum or GQRX. And as time moved on, there was more and more noise, making it more difficult to make out the text that was painted onto the display. And if you were persistent and used some DSP techniques, you could pull that out of the noise and be able to see what the flag was. If you listen, you might also hear some flags showing up in Morse code. This is one from last year as well. And this year you might find a similar one somewhere around 434 megahertz. If you listen right now, you might hear it and you might be able to get some points. Here's another example of some flags that showed up last year. We had a NTSC analog television signal that had a number of flags in it. And you can see a couple on the screen here. One was hidden in a QR code, and another flag was in the subtitles. So that's just a little flavor of the sorts of signals that you might encounter in this year's Capture the Flag competition and what a flag might look like when you find it. So if you want to have a look at some of these signals, where do you go? Well, we have a channel on Matrix Chat called Capture the Flag. So you can enter the channel and you'll find a link to sign up for the competition. And we also have a room number 210. And I think I have a picture here. It's just outside the room, and turn to the right and you'll find the Plata room 210. When is it? It started just over an hour ago and continues until Friday at 4 p.m. and that's 2300 UTC. And if you're sticking around till Saturday, we're going to have people demonstrating how they found the flags that were hidden in all kinds of weird and wild radio signals. That's planned for 2 p.m. local or 2100 UTC. You definitely don't need to be here in person to participate. Almost all of the signals are available as SIGMF recordings that you can download from the CTF server. So if you're remote, you'll be able to solve almost all the challenges. There are a few where you need to be present here because we have transmitters set up either in the CTF room or distributed around the conference. If you're remote, I would suggest teaming up with somebody here who might be able to provide a recording of the local signals for you if you want to help out. And that's it. So if you want to get started, just go to ctf.gnuradio.org, and I'll leave the QR code up there for a little while in case you want to scan that. And that's it. So I hope you will join. There's challenges for all skill levels. Even if you're a complete beginner, there should be some things there that you'll be able to solve. And we have challenges running all the way up to very high difficulty that some of the experts will be grinding away at for hours. So I hope you'll join us in the CTF and see you there.
Thanks. Finally, one more lightning talk. We've heard about radio astronomy and Psyche mission, but this is the actual important stuff that we're going to hear about now from Seth.
Super important. I know it's getting late today, so yeah, the search for the mythical one ballant flow graph, aka what is a microballant? All right, how does this thing work? All right, so microballant is, it's a representation of your flow graph complexity. I've seen lots of questions where people have, what does this represent? Where does it come from? What does it mean? Well, yeah, it's a joke. Doesn't mean anything at all. This is really a kind of history of the early GRCons. We tended to have somebody named Ballant Sieber. He used to work at Edis, and he would get up every year and he would do what we'd call the Ballant Show. And the really early Ballant shows were fun. It was our yearly dose of all your RF belongs to us. And what he would do is he'd just come up with random crazy applications that he would mess with SDRs. He'd do stuff with receiving signals from airplanes, satellites. I think he messed with Matt Edis once with a restaurant pager, triggering it while he was waiting for his food. And Matt apparently, at least the story was Matt went up and was really confused because the food went anyway. But the trick was, it was how Ballant did it, right? His flow graphs were, complex, so many blocks. So I, scraping the web, managed to find this one from GRCon 2013. Oh, it gets better. Yeah. Let's zoom in there. So yeah, that's a typical Ballant flow graph. Some of the later presentations weren't quite that complex, but the fun thing was every time he would get up after that, people would do mini live demos, and the comment was always, this is a 1/4 of a Ballant flow graph. So I got the brilliant idea of one day during our hack fest, I was like, let's come up with something and figure out flow graph complexity, and how do we calculate what is flow graph complexity, and how does it, there's some code that does a bunch of stuff, and the real trick, you just disable your blocks and add a bunch of connections. It doesn't do anything useful. So, but yeah, that's my fault, and I figured we've seen lots of comments over the years about what the heck is a microballant. So I figured I'd give a quick history lesson on what flow graph complexity means. TLDR, nothing. But on a more serious note, I mean, there are a lot of really interesting graph theory type and ontology type things that would be an interesting thing to research in the future. But this was just a fun little Easter egg to put into the GNU Radio Companion. So, yep.
All right, thanks a lot. That's the perfect kind of lightning talk that ends our speaking session for now. Not for the day, but for now. We have a break now, and oh my God, do you know the time? Okay, you gotta look at the schedule. I don't have it off. I don't know if I had. But you can go get you can go grab a cup of coffee now, and you can you'll just please come back whenever the next session starts. 3:20. So we have half an hour. Okay, perfect. Half an hour. You can go check out the sponsor booth, and we'll see you then. Bye.
I need to reset my clock. Anyways, so it is a pleasure to re-announce Marin, who's been on stage already. The last time he was on stage, he talked about a device that was optimized for IF sampling. I guess this is like an extension of the idea of not doing RF sampling all the time. So give your warm attention to Marin as he talks about, lo and behold.
Okay. I'd like to sincerely apologize for everyone who's seen enough of me today. This is my last presentation, I promise. And I said earlier I wear multiple hats. One of these hats is I'm a nerd. I just like stuff. And the last few GRCons, I've tried to make an effort to give a presentation about some basic thing in SDR. So for example, last year I spoke about GPIO, so before that about spectrum analysis. So this is supposed to be a basic introductory talk to a topic. So if you're an expert, all of this might be completely boring to you, and I apologize. But I find it, useful to do these talks every once in a while, and personally, I enjoy them quite a bit. So I'll be talking about direct sampling techniques in software-defined radios. And this actually brought me back to my first encounter with SDR was in my, 5th or 6th semester, I can't remember, in university. I heard about SDR for the first time, and this was the book that I used. That was, the textbook for the class, so it's all in German, of course. I couldn't actually find that book. I must have lost it, I moved several times since. So yeah, I couldn't actually find the quotes that I was looking for. But I did find something on the German Wikipedia that says something about an ideal SDR, and it says something along the lines of an ideal SDR would just consist of an ADD converter and an antenna, and all further processing would be done in a digital computer. But then there's this footnote, so in practice we do need RF circuitry for selection and tuning. But like me, sort of young little me, was impressionable me, was left with this idea that, well, if we just had an ideal converter, this would be unnecessary. So as I was, this gave me the impression that this RF stuff is more of a crutch than anything else. So I tried various things in university until I figured out what I wanted, and I really enjoyed stuff that was close to the math, like theoretical stuff, but I always wanted to be able to prove that my theories were working. So an SDR was great. And in my mind, an SDR was a device that would give me an arbitrary piece of spectrum as samples, and I wouldn't have to worry about anything else. So, the hardware, etc. And in practice, that didn't turn out, and now I've been building SDRs for almost 10 years. But at the time, this was exactly what I wanted. I said, I need those 20 megahertz, and I need it at 20 megasamples at any frequency that I need at the time. So that was my personal, completely subjective definition of an ideal SDR. And I didn't care if it was if there was RF circuitry in there or not. Now, if we can't build an SDR that just samples everything and does the rest in a digital computer, what do we do? And what we've been doing mostly in SDR was build these zero IF or superhead architectures. So we of course do have an analog to digital converter, but then between that and the antenna, we have a whole bunch of components. We usually have mixers, LOs, like 1 or 2 mixing stages, a lot of filters. And this is a great architecture. First of all, it's well understood. We have people who know how to design these. But all those filters, they remove a lot of the unwanted spurs, and interferences. And of course, we can mix a signal several times until it reaches an optimal point for the ADD converter or D to A converter. So an architecture like this actually is pretty close to this ideal, ideal SDR for me as a user, from my user perspective. So yeah, it's not a bad design at all. If any sort of residual frequency offsets we can fix in digital, that's easy. A lot of filtering. It's a good design and it's well proven. So what's the problem? So I mentioned I'm not going to go into details. I hope you know what a zero IF or a superhead architecture is. If you don't worry about it. But if we have a direct conversion architecture, we have to deal with impairments, that come from the hardware design, such as IQ imbalance. We have LO leakage. The LO leakage would show up as a DC offset in this spectrum here. The tone that I'm looking at is the one at 5 kilohertz. This is a standard GNU Radio flow graph that ships with GNU Radio that I used here. And then at minus 5 kilohertz, that's already one of my spurs that I don't want to see. And then there's harmonics and all of this other stuff. That's one of the problems. And the other problem is the complexity that comes with it. So this isn't even a schematic. This is like the first page of the schematic for the TwinRx daughter board, which is the overview of the schematic. This is basically the table of contents, just to show you what's going on in one of these daughter boards. And that's an RX only board. It does 2 channels, but like that's not even reflected in this part of the schematic. There's a lot of stuff that goes on the hardware, so it's difficult to design. And trust me, the software to run this was just as difficult to, like we had to like come up with a whole new framework to reduce complexity in UHD at the time. So yeah, sure, we can build these things, but it's not easy. So the complexity is a real downside in these architectures. And now it's 2023, and you know, since I visited that class in 2000 and I don't know, like 5 or whatever it was, like you know, the state of silicon has changed quite a bit. And so these are TI, ADI, and Xilinx, like 3 sort of major vendors of converters, all have like super high rate converters these days that you can just buy. Now, by the way, real quick, this is not a sponsor talk, but like I can't really give this talk without pointing to real life chips. That doesn't make any sense. And I don't work for any of these 3 companies. Just quick, but like they are the ones that are selling those chips. So where was I? Okay, so we have these super high rate converters these days. So now, I mean, it feels like we should go back and see if that ideal vision of an SDR can now be accomplished. So that's that. Now, first of all, this idea that you can just remove all RF components is, of course, always a lie. As soon as you have an SMA connector or you know any other RF connector, you have at least something that you have to put on your PCB. But in an ideal case, like here, we have part of the schematic of the X440 motherboard, sorry, daughter board. So the only thing that's between the connector and the converter is actually a balloon for the single-ended to differential conversion and a bunch of switches. So there's really not that much. And compare that to the picture I showed earlier of the TwinRx daughter board. Like the complexity is massively reduced, and that is of course a huge advantage. However, these balance or transformers, they do have a frequency response of their own. So in this case, they dictate how far down we can go and how far up we can go in frequency. So we can't get close to DC, for example. I mean, those transformers do exist, but they can then also go up to 6 gigahertz. So you have to make a choice, and boom, you already have sort of a real life constraint. But still, this is a very wide frequency range, extremely useful for most applications. I want to quickly do a sort of sidestep here a little and talk about the sampling theorem, because the sampling theorem in the GNU Radio community has always been like a source of confusion, because people come out of a class and they know they've been taught something like what we see here on the left, and it says, according to the sampling theorem, to reconstruct a one-dimensional signal from a set of samples, the sampling rate must be equal or greater than the highest frequency in the signal. And then I don't know how often Marcus alone has answered the question of why we are able to capture like a 20 megahertz bandwidth in a 20 megasample signal if, where's the factor of 2 in that? And we have to say, well, it's complex and yada, yada, yada. And Marcus probably has canned answers for that at this point in time. But there's another piece of confusion as well, because this is not actually what Shannon's paper says. Like, if you read what Shannon wrote in his paper, he says, if a function contains no frequency is higher than W, and then it is completely determined by giving its ordinates at 1/2 W seconds apart. So, they basically invented and they say extra stuff that Shannon didn't actually say in his paper, which is most fine, honestly, for most cases. If you're doing like audio sampling, this is effectively a true statement. But the point is that's not actually what the paper says. And if you look at the English Wikipedia on the sampling theorem, it actually has a much better statement. It says, the theorem states that a sample rate must be at least twice the bandwidth of the signal, not like the highest frequency. Now, that's also not what this theorem says, but at least it actually matches, what the entire paper says. So, we double the bandwidth, then we can sample, and we're doing real sampling. Okay, what are the problems of building an SDR that only consists of a converter and has no RF circuitry? First one is that without all this filtering that I showed you on one of the schematic that I drew by hand earlier, anything that reaches the converter is part of your signal. So if your signal of interest is between 1 and 2 gigahertz, like it is on here, but then you also have spurs on the lower end, and you're catching something from the ISM band or the higher end, like you have to deal with that. You have to properly sample that first. You can filter it out in the digital domain, but only if you've not violated the sampling theorem in the first place. So the actual bandwidth is now multiple giga samples. Now, if I have an ADC running at 2 gigahertz, then I would be able to capture the signal of interest, but not all of this. Now, which means I have to add a filter to remove all of this other stuff. And if I do that, my signal of interest is between 1 and 2 gigahertz, which means the bandwidth is less than 1 gigahertz, which means my ADC running at 2 gigahertz is perfectly fine to capture the signal according to Shannon's theorem. But I had to put that filter in myself. And in the past, with the the more complex RF architecture, I could sort of basically request a filtering step from the SDR through my software APIs. And I can't necessarily do that with a direct sampling architecture because I don't necessarily know what I'm looking at, where which filter do I need. So I'm basically putting some of the onus on the end user. I need to talk about Nyquist zones for a sec. What is a Nyquist zone? The definition of a Nyquist zone, it's a frequency area of the width of 1/2 my sampling rates, starting at 0. So from 0 to 1/2 the sampling rate is my first Nyquist zone, and then from 1/2 to 1 times the sampling rate is my second Nyquist zone, and so on. And Nyquist zones show me where there will be an alias of a signal. So I'm just going to start with an example here. Say I'm going to transmit a tone, which is the white arrow in the signal, in this graph, which is in both. I have like two graphs for 2 different sampling rates, and I've put the white arrow at 0.4 times the sampling rate. If I transmit this, then I will see more tones on the output of my digital to analog converter, 1 per Nyquist zone. So this tells me 2 things. First of all, if I have a higher sampling rate, I have fewer spurs that I need to deal with. So that's good to know. So I can just increase the sampling rate. If I could increase my sampling rate, ad infinitum, and then also increase the processing power, that means I could let my problems go away, through sheer processing. But of course, that's not possible. I said there's 2 things, right? What was the other thing? Oh yeah, the other thing is I still need to apply some external analog filtering to remove those spurs because of the practicality. So even in the bottom example, where I only have one, like dark green arrow, that's where I don't want it, I still need to filter that out. Okay, so this is mostly to get the nomenclature right. So this is Nyquist zones. These are the aliases. Where do aliases actually come from? There's different ways to explain that. One way is to look at it like this. So this is an example. The green sine wave is, well, it's just a sine wave, and I'm going to sample it at a rate such that the sampling rate is 10 times the frequency of my sine wave. And then if I do that, I end up with those blue X's. Those are my sample values. However, there's another sine wave with a frequency of 1.1 times the sampling rate, which produces the exact same like samples. So which one, like if I show you the blue dots, like can you tell me which signal I had in the first place? Was it the green one or was it the orange one? The answer is we can't. Like we've sort of lost that information in the sampling process. So like the green and the orange sine wave are both perfectly valid representations of the blue samples. So now this is a bit of a it's a bit of a hand wavy way to explain it. It's more of an intuitive way really, but you could say it like this: if you're sort of receiving these signals, then you've lost the information if it's like the higher or the lower rate, and if you're transmitting these samples and like your D2A converter is trying to reconstruct the analog signal, then it'll just. The other thing to keep in mind of where these aliases come from is that when you're handling real valued signals, there's really no such thing as a negative frequency. It's not really meaningful, and any positive frequency will have a mirror image at a negative frequency. If, cosine of x equals cosine of minus x is, one sort of way you can remember that. So again, if I have my intended signal in the first Nyquist zone, the white arrow, then I'll have all these dark green arrows showing up as well because of those two effects. Okay, but this is useful. I can actually do something with that. A very common technique, even when we were not using direct sampling architectures, is undersampling. So assume I want to receive a signal which could be at one of three frequencies, F1, F2, F3, and they happen to be in the first, second, and third Nyquist zone. Then, assuming I only have one of these at the same time, I can actually sample that just perfectly. I don't have to do anything else. Like, I'm just going to run my ADD converter, and in the digital domain, the signal will look like this. You can see it on the bottom left. So assume my original signal was at F1, then this is what you get. Assume my original signal was at F3, then you actually get the same thing because of this aliasing effect. So we're actually looking at an alias of our signal. That's what we sample, kind of. Like, I'm sort of being intentionally unscientific here, and more illustrative. But we sort of kind of moved the signal down into our first Nyquist zone, and that's what we get. If it's in the second Nyquist zone, we have another effect. It's mirrored around the center of the Nyquist zone, but that's something that I can very, very easily fix with digital processing afterwards. So all of these signals are perfectly captured by an ADD converter. Nothing I have to do, which makes me think, wait a minute, like all those mixes that I put in my superhead or zero IF architecture, they weren't necessary. Like, I could just sample this; it works just fine. Like, there's no problem at all. So what's the big deal here? And the problem is, like, these aliases don't always work out the way we want them to. So what happens if my signal of interest is right on the boundary of two Nyquist zones, for example? And then I'm just going to throw in a spur in a completely different Nyquist zone. What does the end result look like? Now, first of all, my signal of interest, like the part that's in the first Nyquist zone, gets captured at the right spot. Everything that's in the second Nyquist zone gets mirrored and gets folded back onto the signal itself, which means I've already garbled my signal. And then that spur, because of the whole aliasing, also lands on my signal of interest. I completely destroyed it now. So this is not actually a valid capture of a signal. So this is a problem that I have to deal with. And the problem is a bit of an odd one if you're used to, like the typical SDR, where, the one that was my personal ideal SDR, where I say I want a frequency at this rate and at this center frequency. Like, all of a sudden, that's not possible. There are certain frequencies that I cannot capture at if I've already chosen my sampling rate, and vice versa. So if my center frequency happens to be 1/2 the sampling rate, well, I'm in trouble. Like, there's nothing I can do with the direct sampling architecture. So my ideal SDR definition and this direct sampling thing, they don't really work together. Okay, so how do we get around that? And there's we removed all the knobs from our SDR intentionally to reduce complexity, but that also means I have fewer knobs that I can twiddle to change things. But the one thing that I can change is the sampling rate. So in this case, I could run a capture with two different sampling rates at the same time, such that the Nyquist zone boundaries never align. And then it doesn't really matter where I move that signal here, it'll always fall on a valid frequency where my direct sampling architecture can capture without having any of those negative aliasing effects. However, the sampling rate that I choose, unless I'm just building a graphical spectrum analyzer, is usually not arbitrary. I usually chose the sampling rate for a reason, maybe because I'm matching it up with like the baud rate of, like, symbols and whatever, like the OFDM symbol rate or something like that. So in this example, at least one of those sampling rates will not be the one that I want. Like, one of them will be not useful. Luckily, many of these high-speed converters, they have ways to fix that. So they have built-in resamplers. If you are completely flexible, then maybe you can just have one receiver chain where you dynamically change the sampling rate, giving you the same effect. But quick note on that, like a lot of those chips that I showed you earlier, they take a while to reconfigure. Like just setting the sampling rate is actually a difficult process, and it could take like up to a second. All right, 10 minutes left. Wow, that's a lot of time. Okay, fair enough. There's another problem with these direct sampling architectures, which we see on the output, like meaning the TX direction. Most DACs, they have a what's called a zero order hold signal reconstruction. Basically what that means is when they are transmitting a sample, which is, has no duration in time, they hold the corresponding voltage for that sample for the duration of a sample. And then on, the next sample interval, they hold a different voltage. So you get these step functions in the time domain. And the Fourier transform of that step function is a sinc function. So it's the line that I sort of semi-professionally highlighted in blue here. Now, if I look at this line, it's immediately obvious that I can't actually use the output of my DAC except for the first Nyquist zone. So in the second Nyquist zone, it's already the relative attenuation between like the low frequencies and the high frequencies is like more than 20 dB, which means if I had a high bandwidth signal that sort of almost filled the entire Nyquist zone, even if it didn't, cross the gaps, it would be completely like lopsided in the frequencies. So what can we do about that? Now it depends on the chip at hand. So some chips have a thing called mix mode, which I don't want to go into details. Like they have a way of sort of shifting the output response. So you end up with the red line. And you can see the red line looks much nicer in the second Nyquist zone, looks bad in the first Nyquist zone, but then you just select mix mode when you're in the second Nyquist zone and you don't select it when you're in the first Nyquist zone. So that already gives you a much wider range of available frequencies. And the other thing that some of these chips have is a thing called an inverse sinc filter, because like these red and blue lines, they are perfectly well known. We can predict them. So what we can do is say, well, we know what the DAC response looks like. So we can just invert that and then put that into a reasonably complex, into an FIR filter of reasonable complexity that sort of matches the inversion of that. And if we add them together, we get that orange line here, which is almost perfectly flat over 90% of the Nyquist zone. And if the chip is advanced enough, it'll do that both in the first and the second Nyquist zone. I have not yet seen a converter that does anything about the third Nyquist zone. And in fact, the ones that I've worked with, they have like something in their data sheet where it says, well, we don't really recommend going beyond the second Nyquist zone for transmit. But still, if you're running at 20 gigasamples or 28 gigasamples, like some of these chips do, that gives you a huge frequency range to work with. The last problem is not really a problem. It's more of a first world problem. I mentioned like we remove all the RF circuitry, and then what's left is whatever the converter gives us, which means the achievable frequency range of a direct sampling architecture is directly correlated with the available rates. Now, I only need high rates really for high bandwidths, not necessarily for high frequencies if I'm using a traditional approach. So if I want to do something like FR2 millimeter wave research, etc., like I would need a massively fast converter to achieve those frequencies in a direct sampling architecture. So that's not really feasible. I can't do millimeter wave and direct sampling at the same time. But I don't really think that's not a real problem, because even in the traditional approach, like the same RF circuitry that I'm using, say for like 0 through 6 gigahertz, like would not also be able to accommodate millimeter wave. So I'd need, 2 different circuits anyway. So I don't really want to call this a problem. The thing I'm trying to point out is it's not trivial for these designers of these high rate converters to, double or quadruple like the available converter rates like every few years, like Moore's law or something. That's not how that works. How much time do I have? 5 minutes? Okay, I'm almost done anyway. So this is just a sort of a footnote that I'm adding here. These high rate converter chips that you can buy, they usually have a whole bunch of other features, and the most important ones are mixing and digital mixing, that is, and resampling. And the digital mixing part is important because when we are doing, GNU Radio or SDR, we almost always care about complex IQ baseband samples. And even, with aliasing and undersampling, I don't actually move the signal to baseband to 0 hertz center frequency. I always need like a complex mixing stage afterwards to do that. But that's fine because almost all of these converters, like, they offer that. And it's, it comes through the API. You tell the chip which frequency the actual signal of interest has landed at, in this case F1, and it sort of undoes that, pushes it to baseband 0 hertz. Now you have a complex sampling signal, and now you probably want to decimate the sampling rate at least by 2, but maybe even more than that. And some of these chips even have fractional resamplers, or even completely advanced DSP operations, FFTs, or programmable DSP, programmable FIR filters, you name it. Depends on the chip. Like, this is not true for all of them, but some of them. All right, and that's my last slide. So direct sampling architectures have a bunch of downsides. So personally, I think the worst one is this bad correlation between available rates and center frequencies. But they are much simpler. The advantage of the simpler architecture is really massive. That's why I put it here 3 times. So there's a reason, like, the authors of these books, like, years ago said, well, this would be really nice if we could build these devices, and it is. It is really nice just because of the increased simplicity. Yeah, so direct sampling architectures, they have their upsides, have their downsides. Good old SDRs, still useful. We'll probably still have them for a long time. But yeah, this was sort of a general overview of direct sampling architectures for those who are interested. And that concludes my talk. Thank you very much.
Yeah, we do have 3 more minutes for questions, so are there any?
Hi, I didn't see the whole presentation, but I just wanted to ask about the sampling rate and if it's affected by the hardware that you're using.
Yeah, so of course, the like that's sort of the thing where, like, these big chip companies, that's like the arms race of these big chip companies in the converter space. So I mean, I don't want to, like, throw specs around. Like I said, there's not a sponsor talk, but like, we're talking of, like, the devices that you can buy these days, they have like 28 gigahertz sampling rates. Like the Xilinx ones a bit slower, but like, when I say slow, I'm talking like 4 to 6 gigahertz or something like that. And plus, they have this entire FPGA attached to it where you can do further processing. So it depends on this chip at hand, but like, the converter rates that you can achieve these days are like on the order of gigahertz. So you can do quite a bit with that.
Are there any other questions, or is the next speaker already in the room? Awesome.
Marcus, can I leave the stage, please?
You can leave the stage.
All right, thank you very much. Bye.
So, thanks. Well, it's an honor to introduce the next speaker. I think you're supposed to be William Blair, right? But you, no. No, you're not. Are you not? No, is it? I thought it was William Blair, but I'm not sure now. I mean, we can be flexible. Are your slides already with the AV people? Like, oh yeah. That, I think the next speaker is Mr. William Blair, who's gonna, I mean, GNU Radio is very much about implementing signal processing on general purpose CPUs. And I've been doing support for SDRs for quite a few years. And a very common question is like, what PC should I buy? And the usual answer is, you know, if you've got budget, spend it because you need it. So I'm very happy that someone, you know, cares about how to interpret benchmarks to predict how well some software implementation of things will work. So I'm very happy to have you on stage.
Hi, everyone. My name is BJ. I work at Andro Computational Solutions, sort of located in Rome, New York. I'm on the waveform development group there. And today I'm going to be talking about GPP predictors for software-based waveform performance. So at Andro, we implement waveforms which the entirety of waveform processing is done on a general purpose processor, or also known as the CPU. So because of that, the maximum data rates or symbol rates or throughput that you can achieve in real time are largely tied to the performance of the CPU you are using. So then a question becomes, when you're looking to acquire a CPU, how do you look for different properties on the CPU and decide which ones you think will give you better performance for your waveform? So for the higher end of CPUs, Moore's law is still in effect. Better CPUs are coming out every year, and the best consumer grade CPUs on the market are, constantly changing. Whereas for lower end, less performant CPUs, for like embedded devices and things, it's more important that you can be sure that your waveform will run it all in real time without overloading the processor. So to explore this, we took 3 different LDPC, FEC implementations and DVB-S2 waveform implementations, an Andro proprietary implementation, as well as 2 open source ones, AFF3CT and GNU Radio DVB-S2 RX, and we benchmarked them on 2 different current top-of-the-line consumer-grade CPUs, an Intel i9 and a Ryzen 9, and benchmarked them and reported the maximum throughput and symbol rate on each system. And for each benchmark, we did this with and without overclocking said systems. And so to see how each implementation and benchmark interacted with each CPU differently, we use mainly 3 different tools to analyze the programs. One of them was Intel vTune Profiler and GNU Profiler, both of which give you the kind of areas of the code that spent the most time in the CPU and pushed the CPU the most. The vTune Profiler also provides additional features, with the downside being that it runs mainly only on Intel CPUs, whereas gprof can be used on both Intel and AMD x86 systems. And then we additionally use cache grind, which analyzes how your program interacted with the CPU's cache. So as we go over the results of these benchmarks, kind of 3 takeaways we'd like you to keep in mind. First, we found that cache on a CPU is an important consideration besides just your CPU frequency in terms of speed for which one CPU may be better than another. A CPU having more cores than another is also not necessarily an indication that your waveform will be formed better on that CPU. And then finally, when comparing CPUs, it's important to consider overclocking ability on that system. So look into how others have been able to push the CPU past its base speeds. So like I mentioned, the 2 GPPs in question are a Intel i9 13900K specifically, and an AMD Ryzen 9 7900X. The screenshot here is from a Passmark software website, which is a commonly used user benchmark used to compare different CPUs and kind of see which one performs better on said benchmark. The very bottom number there, the overall CPU mark, one would expect the i9 to outperform the Ryzen 9 initially, simply because the reported number is higher. However, keep in mind some differences between the 2 systems. The Ryzen 9 has a higher base clock frequency at 4.7 gigahertz, while the i9 has a higher turbo clock speed at 5.8 gigahertz. And then for cache, the Ryzen 9 has twice as much L3 cache as the i9. And then finally, note the single thread rating of the i9 system is higher than the Ryzen. So for the LDPC benchmarks, one important finding was that for the AFF3 CT version, the default configuration had it use the number of threads equal to the number of cores on that system, which for our testing was 16. However, we found that by lowering the number of threads used to 4, we actually achieved a higher throughput, and those are the numbers reported in this graph here. And so for our comparisons between the i9 and the Ryzen, for the Andro implementation, we found we achieved higher throughput on the Ryzen system. For the AFF3 CT implementation, the Ryzen 9 initially outperformed the i9. However, after we applied overclocking, the i9 actually overtook the Ryzen in terms of the reported throughput there. And then finally, for XD-SOPL, which is the LDPC implementation used in the new radio DVB-S2 RX version, the i9 outperformed the Ryzen regardless. So each implementation performed kind of differently with both CPUs, which was interesting. So looking into why that was the case, looking at the vTune profiler outputs and comparing the Andro and XD-SOPL implementations, we find that the Andro version was more memory bound as opposed to CPU bound compared to the XD-SOPL version. So the top reported hotspot in terms of AVX intrinsics was a memory store operation, whereas for XD-SOPL it was a logical maximum operation. And then the reported memory bound percentages were much higher for the Andro version. And so tying that into why the Andro version seemed to do better on the Ryzen CPU, looking at the cache grind output, and as we mentioned earlier, the Ryzen had twice as much L3 cache. And additionally, the Ryzen cache type was direct mapped as opposed to associative, which from our research is faster. And then reading online, we also found reports that the Ryzen seemed to outperform the Intel versions in terms of cache bandwidth and speed. And then looking into AFF3 CT, the output here from GNU Profiler, we found the top reported function was a decode single iteration function, from which looking at the code seemed to be more CPU bound. So that would explain why the AFF3 CT version did better on the i9 after overclocking, due to the reported i9 single thread rating being higher. And also additionally, remember I had said that initially the AFF3 CT version performed better on the Ryzen system initially, but then after overclocking did better on the i9. Looking at the clock speeds before and after overclocking were applied, the Ryzen 9 initially had a higher clock speed, but then the i9 had a higher overclocking frequency afterwards. So that maps with the AFF3 CT doing better on one and then flipping. So again, the AFF3 CT version was tied more to clock speed and CPU core performance. So now moving on to DVB-S2. So for the results reported here, the Andro implementation was run on 2 X300 radios, and we manually increased the symbol rate until the waveform was no longer stably synchronized, which is why the numbers are so much more discrete compared to the other two. Whereas for the AFF3 CT and GNU Radio DVB-S2 RX versions, they were ran in simulation and ran as fast as they could on the given system and reported their symbol rate. So unlike the LDPC benchmarks, for DVB-S2, in all cases, the i9 generally outperformed the Ryzen in terms of maximum symbol rate. So the Andro implementation, remember for LDPC, did better on the Ryzen system, now did better on the i9. So comparing the vTune outputs for just the LDPC benchmark compared to the full DVB-S2 waveform benchmark, we find that memory boundness has decreased and now seems to be more CPU bound comparatively. So phase correction took up the top reported hotspot, and generally the memory bound percentages decreased. So that would explain the Andro version switching from being better on the Ryzen system to the i9 system, as it has become more CPU bound as opposed to memory bound. And then for AFF3CT and the GNU radio versions, similar to previous results, generally the i9 outperformed the Ryzen, and we found BCH decoding and simple synchronization to have the highest CPU usage, which again more CPU bound operations opposed to memory bound operations. So conclusions from looking at this data, general consumer benchmarks are not necessarily indicators that as one CPU will do better than another. So as we saw, the Andro implementation did better on the Ryzen system, even though the reported passmark benchmark had a higher result for the i9 system, at least for our LDPC. A CPU, again, having more cores than another CPU is not necessarily better. So as I mentioned previously, we actually found a higher AFF3CT LDPC throughput by decreasing the number of threads used. And in a similar findings, author Graver in 2019 in his DVB-S2 paper, where he tested scaling his DVB-S2 throughput with the number of threads on a given system, and found that cache memory available is more of a limiting factor rather than number of cores being available, because even if you have more threads, they are still contending for some shared resources that the CPU has. And so some general suggestions for comparing CPUs and selecting one over another, based on looking if your program or waveform is more memory or CPU bound. Using that information, you can kind of see and compare the strengths of that CPU, see if it's better more in the memory department as opposed to just clock speed or CPU thread department. And then finally, it's important to consider overclocking ability. So as we saw when we were overclocking the i9 versus the Ryzen, the i9 was able to be overclocked higher, and that allowed us to see higher throughput for the AFF3CT version switching from the Ryzen. So for future work, so I mentioned that the Andro implementation was ran in real time using X300 radios, whereas the other two implementations ran in simulation. We'd like to flip that and see how that affects results. And then the Andro LDPC implementation, it was single-threaded for these results. So applying threading to it, we could see how many scaling up the threads would hit that kind of sweet spot like AFF3CT did for using 4 threads. And then more on the operating system and software side, looking into how different settings such as scheduling, mapping threads to cores, see which of those have more of an effect on your waveform throughput would be interesting to see as well. And for that, that's the end of my presentation. Happy to answer any questions.
We do have time for one quick question.
Okay, I had a couple of real quick questions. Did you consider you talked a little bit about more cache memory. Did you consider taking a look at the X3D version of the 7900 AMD chip?
So we have not purchased that, although I think our Ryzen 9 is similar, but yeah, another coworker was mentioning that as well, because there's that, I think it has GPU memory in it, is that?
So that one specifically has more L3 cache.
Gotcha, yeah. So yeah, that would be interesting.
Okay, and
not done that.
Another quick question, when you were looking, especially when you were looking at overclocking, were you watching to see if you were getting into any thermal throttling, especially on the Intel chip?
No, we did not look at temperature as a kind of limiter for that. The overclocking for the Intel chip was actually done via a AI artificial intelligence feature built into the BIOS. So we kind of trained it using stress data, and then the AI selected how much to overclock it based on that.
Thank you again so much. Another round of applause for the speaker, please.
Thank you.
So up next is Raphael Turner, who's going to talk about automatic classification of FEC, which is kind of interesting because automatic classification of signals is one of the domains that we see the RF machine learning folks usually be very heavy in, but they just do modulations and you do error correction code. So this is going to be exciting.
Yeah, thanks. That's pretty much my first slide, actually. But no. It's very true. It's our second slide. So my name is Raphael. Thanks for having me. I work at Dedrone. We are a company that detects everything that flies, basically, primarily focused on drones. And understanding not only the wireless spectrum, but communication systems as a whole is very important to what we do. So as was mentioned, a lot of the machine learning applications in RF is very focused on modulation. There's books written on this. There's entire DARPA programs written on this. You know, this is very well explored. But what's not well explored is once you've actually decoded the signal and you get down to bits, what do you do? So these are 4 different forward error correcting codes. And hopefully by the end of this talk, you'll understand a method of distinguishing these. And so this is what we're trying to do. Okay. Oop. Do I point it? Oh. Well, now everyone has more time to figure out what the codes are. Okay, to keep this as self-contained as possible, we're going to just do a very, very quick deep dive into, or high level, not really deep dive into forward error correction. Okay, so what is forward error correction? So it's basically a method, a principled method of adding redundancy to your signal so that when the channel hits it, you can actually recover the data that was sent. For most of the techniques, there's references at the end of these slides for different ways of doing automatic forward error correction classification. But most of these principled methods derive on a very simple channel model where you have a probability that the bit goes to 0 and then the probability that the bit goes to 1. So that's our channel. Okay, so the most famous code that everyone first learns in the beginning is the repetition code, where we just repeat the data n number of times. So here, our forward error correcting code just repeats the data 3 times, goes over the channel, we see it's corrupted, and we can decode it just based on majority vote. So we just look at the 3 bits, and if the majority is 0, we say it's 0, majority is 1, we say it's 1. So this isn't great. So the efficiency is not really good, and it only is able to fix 1 error out of every 3, which is actually pretty fantastic. But the problem here is that we may not get every errors every 3 bits. We may know that we'll have far less errors. So now we start getting into the rate of the code and why this is important. So FEC, you want to add the minimal amount of redundancy required to get the most capacity out of the channel. And so we know based on Shannon's capacity theorem that there is a certain rate that you can reach in sending data. And so people were exploring how good can this actually get. And there are codes that essentially allow you to reach the capacity. These are called. Okay, so we're going to explore some of these. So the first step is to really be precise on what kind of function the encoder and decoder is. So one very common type, and I'll also talk about nonlinear codes, which are more machine learning based, but a very common type is what's called linear codes, where you simply create linear combinations of the data bits to form what's called the parity bits. So here in this slide, we see that if we want to add these parity bits in gray, we can write them as a linear combination of some other bits in orange called the parity bits. Okay, just for some definitions here for the math more oriented people, because towards the end it does get a little bit mathy. But so what is a code? Really, it's just a vector space or linear subspace of a vector space. This space can be really big, so recovering the code is actually quite challenging. To have a more concise representation of the space, we write it in terms of a basis. And given this basis, we construct what's called the generator matrix, which actually rewrites your data in terms of the basis code words. And there's a very common form that the generator matrix is normally written in, which is just identity matrix concatenated with this other matrix. Then if you get a code word, you can check if it's valid by hitting it with what's called the parity check matrix, which you construct from the generated matrix. So I know this is very quick. It's in quotes because this is all from Wikipedia, but just wanted to sort of very quickly get a sense. Okay, but what's the main takeaways? The main takeaway is we have a matrix called G that gives you code words. We have a matrix called H that checks the code words. You can do error correction with H. Yeah, let's just go through these. Okay, so like another way to view the repetition code, there's two ways I'll present it. The most common way is just, it's actually just a row of ones, and it operates on single bits, right? So it takes 1 bit and you multiply it with 3 ones and you'll get 3 bits. Another way to look at it is if you look at the repetition code acting on, let's say 10 bits. So here the repetition is 2 because we're just hitting it with the identity twice. So it just repeats the 10 word or the 10 dimensional code word twice. Another type of code that's actually just mentioned is called LDPC, low density parity check codes. And these codes are constructed from bipartite graphs with really desired for the check matrix H on the right is very sparse. Sorry, I know I'm going kind of fast here, but. Okay, this is, if anyone actually works with polar codes, please don't shoot me. Polar codes are designed where you keep some bits fixed and you have other bits that are free. And the idea is that the bits that are frozen, a priori what they are, and if those get corrupted, you have a better chance of correcting them. Okay, the reason I'm going through these is because these are the codes that the machine learning model is going to try to discriminate. So I just kind of wanted to get every sense of the backgrounds of what are the key players going on. So here on the right, we have the generator matrix for convolutional code. If you're familiar with convolutions, this should kind of look familiar as what's called a toplets or toplets matrix, which is a sort of a discrete form of a convolution. And so this actually really highlights maybe why it's called convolutional codes, because when you first learn about these, sometimes you learn about them in terms of like shift registers, and it's a little bit more complicated, but you can really honestly think of them as really just a convolution with a polynomial. And this is what this generator matrix looks like. Okay, so nonlinear codes, I kind of alluded to these. So everything before were linear codes. Everything but the convolutional code is what was called a block code, which means that we operated on just a fixed set of things, whereas a convolutional code, because it has this memory, operates on a stream. So one of the motivations for this talk is that there is an emerging research in automatically synthesizing error correcting codes. Just like there was an emerging research of automatically synthesizing modulation schemes, we're now starting to see synthesis of codes. And so what's getting kind of interesting here is that you can imagine a future where basically the whole DSP, receiver and transmitter is all machine learning based, which is kind of scary if you're trying to understand communication systems because they become very opaque, right? Because they're no longer based on theories that we really understand. Okay, so now we get to the fun part, I think. Okay, so remember this was the challenge. We had 4 error correcting codes. We wanted to figure out what they were. So past work in doing this is machine learning based, and what I'm going to present here, what we're doing is a little bit different. So in the past, a lot of people just took this data and fed it into a machine learning model and hope for the best. But the problem with these approaches is that they assume a fixed size of the vector. So if you had different code words of different dimensions, you would have to have multiple models because the machine learning model takes a fixed like input. And so the method I'm going to present was, well, what if we didn't want to do that, right? Because you don't know all these different dimensions your code words could be. So you want one model to handle them all. Another problem with this approach is if the model fails to classify one of these, it can be very hard to debug what's going on because this is what you gave the model and it's going to spit out a label, what's the function. So a problem with these approaches is they're not really interpretable. Okay, so like I mentioned before, getting the code is really hard because it's actually a whole space. So one way you can do it is instead of trying to recover the whole space, you try to recover vectors that are orthogonal to that space. And this is what's called the dual space. And the elements of the dual space are called dual code words, but that's just nomenclature, I suppose. And so if you can recover sufficiently number of these, dual code words, you can reconstruct the H matrix. And as we saw, very quickly from there, you can get the generator matrix. So how do you find elements of the dual space? Okay, so you're in a realistic environment, you're just going to receive a bunch of code words. They're going to be corrupted. We're going to form a matrix out of those code words called X. Now, kind of weird the slides, but hopefully you can follow. So if we had a dual code word and we multiplied it with X and there were no noise, then we would get 0. It would be perfectly valid. Since there is noise, we're going to have some error and that's going to be detected by the weight of this code word that results from H multiplied by X. And so you can come up with a formula that distinguishes a random vector versus an element of the dual space, and you can distinguish them in a distributional sense. Let's see here. Yeah, okay. And the next slide will hopefully make this clear what I mean by this. So the recovery part, you can break into 2 steps. One is enumerating low weight code words in the span of your received noisy messages. And then you keep or reject these dual code words based on some statistical test you perform. Okay, so how do you enumerate low weight code words, right? We just took a hard problem and seemingly made it harder. But fortunately for us, the enumeration of low weight code words is a well studied problem, not only in coding theory, but also in cryptography, where there are certain cryptographic systems that depend on the complexity of finding low weight code words. And so there's actually like an open contest that you can look up. It's called like the low weight code word challenge, where people try to find low weight code words. And there's a lot of really cool projects. This is just one of them that you can give it that X matrix and it will enumerate low weight code words. But now you have a bunch of these low weight code words and you want to distinguish which ones are part of the dual space and which ones are not part of the dual space. And so there is a statistical test that's based on the channel model I mentioned at the beginning that allows you to distinguish them with some probability of error. Okay. Why do I want to give you this slide? Okay, so so we have a bunch of these potential candidates of the dual space, and not all of them are valid. Some of them may be redundant. And so how do we remove this redundancy to get a basis for the dual space? We'll reform the spaces by performing Gaussian elimination. And what I want to really point out in this slide is that it's really small, so it's really easy to miss, is that Gaussian elimination is actually just a linear operation, and hence it's differentiable, and we can add it as a layer to the neural network. I think, okay. All right, so we do all this, what happens? These are the results. So you go through this process, and now it's very easy to distinguish what are the code words, right? Or sorry, what are the basis vectors of the different forward error correcting algorithms. So on the left is what came in. We go through the process I've described, and on the right is what you get. So here it's very visually apparent what are the different forward error correcting algorithms. Now, at this point, we haven't actually classified them. It's sort of like a modulation recognition. You still kind of have to know what QPSK looks like, kind of have to know what QAM16 looks like. We haven't actually taught the computer how to see. So how do we teach the computer how to see? And why do we want to do this? Well, I think this is a lot more interpretable than other methods, right? Where you actually use the structure of the forward error correcting algorithm to come up with a feature representation, right? That you can give to the deep learning model. So basically, this is exactly what we did. So you take a bunch of these dual code words that you found, you feed them into the Gaussian elimination layer, and then you can do traditional computer vision on top. The tests that we did is these are the 4 different forward error correcting schemes. These are the different rates that we used. The data bits are just how much data that were there, and then the observed is how many packets did you see. So did you see 10 code words, 50 code words, 60 code words, and that's what the model gets. So if we train the model, we hold out a test set, these are kind of the results. You can see that it struggles when you only have 10 code words, which is extremely difficult to discern what the actual forward error correcting algorithm is if you only have 10 code words. So the model gets very confused. In a nice way, I didn't go over polar codes, but if I showed you them, they would actually be hard to decipher. So just to go back for a second, the model sees what's on the right, but the data that we fed the system is on the left. So I just kind of want to make that clear. And the reason this works for arbitrary dimensions is if you use a computer vision model that's fully based on convolutions, then you don't have to worry about fixed dimensional input. Okay. I mean, I'm really happy it knows what LDPC is. That's kind of cool. Okay, so future work. We did hard decoding. I think this would be very powerful if you did soft decoding. The problem there is that when you do the Gaussian elimination, I forgot to mention this, but all these operations are done mod 2. But when you do soft decoding, it gets a lot more complicated. I'd like to really start analyzing these nonlinear neural network codes because I can see maybe in some crazy world those are actually deployed. They are kind of competitive. You can't really see on this slide, but they are getting competitive with other well understood handcrafted codes. I'd also like to expand the scope of the model. So here I assumed you have synchronized code words, which means that you know where the packet starts and ends. That's not always a valid assumption. And I'd also like to add different kinds of dual, like low weight code word enumeration algorithms directly in the neural network if possible. So this is kind of not really, I don't know how to say this. There is a lot of information out there, but they all just come from France. I guess that's maybe the way I'll say this. So a lot of the big references for finding low weight code words or recovering forward error correcting schemes, a lot of the mathematics has been worked out of various universities in France. It's getting more and more, I guess, public in different ways, but these are really good references if you're just looking for where to get started. I would highly recommend you start here, and this will save you a lot of time. If you're interested in stuff, machine learning, not a sponsor talk, but we hire, you can follow me in these places. Thank you for your attention.
Yeah, we do have time for a lot of questions, so I'll start over here. You're up next.
So at the real high level, why do you want to figure out what these are? Is it to help with figure out the modulation?
It's to help in the aid of understanding the system. So non-cooperative contexts at scale, you can't look at everything. So if you're trying to understand a system, and you receive things on the left, and you're trying to decode it, you want to figure out what this is. Otherwise, it's really hard to discern like what decoder to use.
But isn't that also tied to then figuring out, because all the modulations have predefined forward error correction, right? And so is the intent to figure out the forward error correction to figure out the modulation?
They're different. So you could have QAM modulation with LDPC. I would say the communication system has a family of forward error correcting codes and a family of recommended parameters. But every comm system is going to choose different things.
Okay.
So the idea is that if you were to reverse engineer a signal, and you just saw a bunch of random, and I also just mentioned for this test, the data is literally random. So it's like the worst case scenario. I mean, if it's structured data, then it's a little bit more obvious where the check bits are. But if it's just random data, you're just XORing random data with random data and you get random data. So it's the idea is really to understand what the forward error correction algorithm is.
So are you assuming, do you know the length of the code word?
No, that's you're assuming that you're synchronized. So in some sense, yeah,
You're synchronized.
That's what that is. But you don't know where the data bits and the parity check bits start and end. So I think, yeah.
But which means that if you know this, if you're synchronized, but you do not know the beginning and the end, this means that you're assuming that you are depending on multiple code words to receive.
Yes, yeah, and that's why in the test, yes, we let me go back here. For the test, that's what this observed is. So the model sees potentially 10 code words, 50 code words, up to some cases 1,000 code words. And in cases where you don't get a lot of code words, this is where the model really struggles. Oops, geez Louise. This is what this example is showing. So if you only get 10 code words, it's very difficult to decipher what the forward error correction algorithm is.
So what order of number of code words did you depend on roughly?
Well, that's what I'm saying is that some methods are, sorry, it's trained on all of them. So we have one model that's able to handle multiple different sizes of the code words. Yeah.
Are there any other questions? Yes, then I'll go and then you.
Are these only for systematic codes, or will this work for non-systematic codes?
It will work. This method will work where you can put the code in a form that you can start to visually discern the structure. The systematic codes have this nice sort of visual structure. I haven't tested on non-systematic codes, but the nice thing about systematic is that, right, when you do the row reduction, it really nice,
you see the identity.
Visual.
Yeah.
Yeah. And since we're relying on computer vision algorithms, that's kind of, yeah.
All right, thanks.
And
have you considered the more complicated codes where you have concatenation or rate or puncturing or rate matching?
So some of these, I didn't mention this, but some of these, this convolutional code has puncturing. I don't know about rate matching. I forget. I wish I had a slide on exactly how these are set up. But no, it's definitely not concatenated. Definitely not concatenated. But I think it wouldn't matter. I think if you concatenated, you'd still see the structure. But no, we didn't consider that.
okay, I do have one question. So how about scrambling interleaving? Is that eliminated by the Gaussian elimination, or?
No, not necessarily. I would suggest for that to look at, oh my gosh, I can't put it forward. There's a very beautiful dissertation that talks about this, but you can sometimes see through scrambling, but no, this method doesn't do that. If for interleaving, there's a really beautiful technique if it's a block interleaver where you essentially create different matrices of different hypothesized, I don't know what you want to call whatever that block size is that the block interleaver is using, and you can compute the rank of that matrix, and you kind of know you're in the right spot when the rank gets reduced because the code words, there's like elimination happening in the row reduction. We compute the rank.
Awesome. Thank you then very much.
Okay. Yeah.
Give another round of applause. And we have coming up next Shami Doli, I guess. Oh yeah, awesome. You're actually local, I guess. Yes. And you're gonna talk about, or this talk is gonna be about radar waveform design. So I'm really excited because a former colleague of mine is also in the business of doing joint waveform and for sensing and communications design. And this is really like an emergent and very important field for the future.
Hello everyone. Good afternoon. I'm Shammi Dolly. I'm a PhD student, third year PhD student from Arizona State University. I also work for wireless information system and computational architecture, WISCA, as a graduate research assistant. And yeah, so the title of my today's talk is GNU Radio Realizations for Waveform Co-Design for Joint Radar Communication Systems using some software-defined radios. So this is the outline of my today's talk. First, I will talk briefly about the research motivation and some key contribution that I have made on this work, and some prior research on joint sensing and communications, and how we replicate the receiver model, successive interference cancellation receiver model in GNU radio algorithm platform, and over the air, and some results. So the motivation of this research comes from, we all know that we are actually running out of the radio spectra because it's a natural resource, and we have to find some alternative use. How can we use alternatively, or how can we relocate the radio spectra or reuse the radio spectra? So the key contribution of this work is to pose the waveform design problem in GNU radio algorithmic development algorithm, and then we conduct a hardware in loop over the air experiment to demonstrate the feasibility of the proposed waveform design technique. As I mentioned earlier, then we replicate the receiver model in GNU radio, and we evaluate the performance of unoptimized waveform unoptimized waveform of BPSK and QPSK communication signal, and ASK radar waveform. So this is the some background of our joint sensing and communications waveform co-design problem. It's a multi-user system where two or multiple user can use the same resource, where in our case, we consider a radar and a communications user simultaneously using the same receiver to receive their waveform. And at the receiver end, we use the receiver model, which work on a very simple algorithm that the receiver has some prior knowledge of the radar return or the strongest signal, and then it can remove the strongest signal first and then decode and get the original signal, like the second signal back, which could be communication signal. So in my very first research, we posed the waveform design problem in a decision theoretic platform where we define the problem as a state and actions problem, and come up with a reward function with a combination of a radar estimation rate, which actually defines the performance of the radar system, and the communications, and also the other parameter is communications rate, RCOM. And we combine both rate with some weighting parameter that we call bending parameter. And the target was to maximize the reward function over the time. Then we, in the real world, we try to perform a real world experiment, and then so we use WISCANet over the air experiment, and we successfully showed that our algorithm is working over the air. And we published that paper this year at the radar conference. So this time we are trying to propose a simple method that, that we can use GNU radio to solve our problem. And as you can see in this system block, that we have two like a GNU radio platform. We are using two SDRs as a transmitting, one for communication transmitter, another one is for radar transmitter, and a joint receiver to receive both signals simultaneously. And then we implement the GNU, receiver model at the GNU radio, where we are using the third SDR for joint receiver, and then we are using correlation estimation and apply seek to separate the signals, and then we can do further processing in the communication receiving chain and the receiver chain, and you can get our desired information back. So, so this is the simple receiver model that we can see that successive interference cancellation receiver model. As I mentioned earlier, we have like a composite signals, and we can remove the first signal and we can get back the second signal again. So in the GUNO radio platform, what we did, we used the correlation estimator block to correlate the input signal with a reference signal and get the correlation sequence and the tag where we are actually getting the peak of the signal that we want to decode first. So in our case, we are considering radar signal is the strongest signal. So we are decoding, we are getting radar signal first, and then we can subtract the radar signal from the joint signal. We can get back our so we are actually considering radar signal is the strongest signal, and we are detecting the peak using the correlation estimated block, and we are passing that tag information to the our estimated peak removal block, and from there we are subtracting the radar return from the joint receiver, and we can get back the communication signal back. So this is the over-the-air experiment. We can see here that we have 3 SDR. The first SDR we are using as a communication transmitter, and with a horn antenna, and the second SDR we are using as a radar transmitter, and we're separating both the antenna with like a divider, and we have the third SDR where we are using that one as a joint receiver, and that's the flow graph, GUNO radio flow graph of the entire system. So as you can see here, like the waveform separation, like the first graph here, we can see the radar waveform here only, where we can see only the radar signals, and then the upper one we can see the estimated peak of the joint signal, and the left plot we can see that they are joint radar and communication signals, and after applying the seek we can only see the communication signals back. So this is at the receiving end where we can actually restore our communication signals back. So the BPSK signal we can see here, and then we have also QPSK signals. We tried also QPSK signal. So let me play this video. Yeah. So yeah, we can see here like the live results that so first so this is the receiving bandwidth, and this is the transmitting bandwidth, and yeah, the receiving bits on the other side, that after this post seek, and then we perform the receiving chain, like the equalizer and the other communication part, and then we can get back our communication signal back. So this is the like the overall of my today's talk. So the motivation of this research came from a spectrum congestions problem, and we come up with a simple model or systems that setup that can be used to test the joint radar communication performance of any type of waveform employed. And we pose the waveform design problem in a GUNO radio platform using software different radios, and we conduct a hardware in loop over the air experiment, and we also replicate the receiver model in GUNO radio algorithm development platform, and we evaluate some performance of unoptimized modulated communication signal and radar signals. So the future work, our plan is to use the real target detection, where maybe we can do some further processing in the radar chain, and we can see like the real target range or the Doppler processing. And also we have planned to evaluate the performance of optimized waveform too. Yep, that's all. Thank you.
So we have definitely time for a couple of questions. Oh yeah. Oh, sorry.
Hi, thanks for the talk. I was just wondering what kind of like dynamic range or like power level differences between the two signals you evaluated, because you almost have, I don't know if it's the right term, but like you almost have like a near far problem in terms of like the front end and those kind of challenges and like how your AGC is set up. So I was just wondering like how much of that you delved into versus just looking at like the interference cancellation aspect.
So like, are you asking about the gain, like how much gain we consider, like the?
Yeah, and like the difference between the communication signal power and the
Yeah,
power.
so yeah, we try to do the maximum gain, and just to see like since we are doing it, we perform the experiment in a short range, so it's really hard to get the any actual return. So we try like maximum power.
Okay, thanks.
Hey, I was wondering about the reward function you used. What motivated that reward function?
Okay. Okay, so the reward function is the combination of the radar estimation rate. So that's like a novel rate that come up with a Bliss lab that that can actually tell you about the performance of the radar system, maybe the radar range, target range, like range estimation, and with communication rate. Okay, so then you can combine those two rate with some blending parameter, and that parameter is like that will define you the shape of the waveform, like how much weight you want to put on your radar user and the communications user. So yeah, and you can maximize the reward over the time. So that parameter, the alpha parameter, that will come from the wave spectra, like the spectral weight that we are actually trying to optimize over the time. Mm-hmm.
Yeah, there's one more question over here.
On your conclusion slide, you, at the very end, you mentioned GNU radio was laggy. Could you elaborate on that?
Oh, well, that was my personal experience. So I first started using GNU radio and on Mac OS, and it didn't work for me. Like I really spent a lot of time. So if someone asks me, I will personally recommend to use Ubuntu, not Mac OS, not Windows. So yeah, and because it was laggy, it was like it's crashed every 2 hours or 3 hours without giving any notice. So I think we need to work on that.
I'd agree. Are there any other questions? If that's not the case, please give a warm round of applause. So this sadly ends the first day of talks as far as I can tell. I know there's going to be a meet and greet over at the end grant, which is at the end of the hallways, right when you exit this hall. From an talking about how things went, it's a bit cold. We're aware of that. We've been talking with facilities, and they are working on it. Might take a couple of hours to terminal systems are slow. So this might take till tomorrow until it's sorted out. We're hoping that it will be better tomorrow. Kind of sorry about that. We can't really do anything about it. Other than that, I hope we'll see you at the meet and greet. And other than that, we'll see you tomorrow morning, same time, same place. So I hope you've had a good time. If there's anything that you need to know, let the organizers know. As said this morning, anyone with a white lanyard is your go-to person for any concern. And if we don't know the answer, we are just sending you to someone else. So we will work it out. So thank you for being here.